Hi everyone, my name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. In this comprehensive video course, you will learn automation with Ansible. So whether you're a beginner or experienced DevOps engineer, in the next 9 hours you're going to master Ansible. We're going to talk about automating deployments, managing servers, securing sensitive data, and I will even show you how you can integrate Ansible with cloud services like Azure and VMware. You can find the timestamps for each specific topic down in the description. So if you want to see more free courses like this one, please subscribe to the channel, give thumbs up, and now let's get started.
Welcome to this, our first chapter in the second edition of Learn Ansible. Today we are embarking on an exciting journey into the world of Ansible, a powerful automation tool that's designed to make the lives of system administrators and DevOps engineers much easier. Whether you're managing a handful of servers or orchestrating clusters of virtual machines in the cloud, Ansible simplifies processes into manageable tasks. As we dive into this world, I'll share my experiences, insights, and yes, some occasional jokes along the way. Remember, if you don't find my jokes funny, you can always blame the internet connection. So, what is Ansible? Simply put, Ansible is an open-source automation tool that helps in managing configuration, orchestrating tasks, and deploying applications. But let's not stop at the surface level. I invite you to dig deeper with me. Imagine having the ability to define your infrastructure as code. This means that you can write scripts, known as Playbooks, to automate tedious tasks like setting up servers, deploying applications, and much more. No more logging into servers one by one. One of the strengths of Ansible is its agentless architecture. Unlike many other automation tools that require installing agents on each managed machine, Ansible uses SSH or WinRM to connect to the systems you want to manage. This approach not only simplifies management, but also reduces potential security vulnerabilities. By using existing protocols, you get to focus on what you do best, managing your infrastructure, while Ansible takes care of the heavy lifting in the background. So now, let's talk a little bit about why Ansible stands out among various automation tools available today. For instance, tools like Puppet or Chef have their own ecosystems with agents, which might introduce complexity into your environment. What if you could avoid that headache and manage everything over SSH? Yes, that's what makes Ansible appealing. Another aspect to highlight is that Ansible's declarative configuration language, YAML, is incredibly easy to read and write. Think of it like having a friendly conversation with your infrastructure. Instead of complex coding languages, you're just stating what you want your system to do in a way that's almost like English. If you've got a knack for a bit of storytelling, you'll feel right at home writing Ansible playbooks. Now let's look at this figure, which illustrates the results of 3 separate runs in a declarative Ansible playbook focused on user management. The figure is organized into 3 columns, each representing a different run of the playbook: Run 1, Run 2, and Run 3. In Run 1, we see 2 attempts to add a user, Alice, which ultimately fails, indicated by the red background. This highlights the challenges that can arise during automation. However, the subsequent command to create a group named Team is successful, as shown in the green box. Another attempt to add a user, Bob, also succeeds in this run. The last command regarding escalating privileges for Alice fails as well, reinforcing the idea that not every operation may succeed on the first try. Moving on to Run 2, we find that the attempt to add Alice as a user is now successful, backed by a green background. The attempt to create the group Team reports no changes, suggesting that it already existed from the previous run. The addition of Bob remains unchanged as well, illustrating Ansible's ability to recognize the current state and avoid unnecessary operations. Interestingly, the escalation of privileges for Alice succeeds in this run, demonstrating improvement and adaptability in the script. Finally, in Run 3, the figure shows a continued trend of recognizing existing states, with both the attempts to add users Alice and Bob resulting in no change. The group Team again shows no changes. The command to escalate privileges for Alice also confirms no change was necessary. This reflects the declarative nature of Ansible, allowing for clear outcomes based on existing conditions. Overall, this figure succinctly conveys the effectiveness of using Ansible for user management, showcasing how operations can evolve across multiple runs, while emphasizing the importance of error handling and state recognition. Before we delve deeper, let's make sure we have the groundwork laid out correctly. Ansible requires certain technical prerequisites before you can jump straight in. You'll need a machine or multiple machines that can run Ansible. This is usually either a Mac OS or a Linux system with an Ubuntu LTS release. But fret not, those of you who wield the power of Windows 11, I haven't forgotten you. You can utilize the Windows subsystem for Linux to run Ansible as well. Right now, if I can pause for a moment, let's think about the environment where you will step into the magical world of automation. Later, we'll set up a virtual machine to begin our hands-on practice with Ansible, which is going to be quite exciting. If you think about it, installing Ansible is even a breeze. By the end of this session, you'll have Ansible installed and running so seamlessly that you'd think it was always there. To install Ansible on Mac OS, you'll want to use the command brew install Ansible. Homebrew simplifies software management on Mac OS, allowing you to quickly install packages with just a single command. Once you run this command in your terminal, it will automatically fetch Ansible and all its dependencies, setting you up for automation tasks in no time. For those using a Linux environment, particularly on Ubuntu, installing Ansible is just as straightforward. The command sudo apt update ensures that your package list is current, pulling in the latest available versions of each package, and then sudo apt install Ansible will install Ansible itself. This two-step approach ensures you have the most up-to-date software. Lastly, Windows users can utilize the Windows subsystem for Linux, WSL, to run similar commands as those on Linux, making the installation of Ansible equally easy. Regardless of your operating system, these commands will equip you with Ansible, preparing you to dive into creating and managing playbooks effectively. In this example, we have a simple Ansible playbook defined using YAML syntax. It begins with a header that specifies the play, indicated by the 3 dashes, NAS. The play is named a simple playbook and targets all hosts with the directive hosts all. This means that the tasks defined in this playbook will be executed on every server listed in your inventory. The playbook contains one primary task. This task is labeled as output some information on our host. Here, we leverage the built-in Ansible module called Debug to output a message. The key aspect of this task is the use of Jinja 2 templating, which allows us to dynamically incorporate variables into our output message. In this case, the message will state the name of the node we are connecting to, as well as its distribution and version. Specifically, it uses the variables Ansible node name, Ansible distribution, and Ansible distribution version to fetch real-time information about each host. Overall, this playbook serves as a straightforward introduction to automating tasks with Ansible, illustrating how to provide valuable information about your environment in a clear and accessible manner. Now let's look at the figure illustrating the process of creating users in an imperative manner using Ansible. At the top, we see the title, Create Users Imperative, and a label indicating Run 1, which signifies this is the first execution of the user creation process. In the center of the figure, the first task, Create Group, is showcased. This task has a status of Success, indicating that the group named Team was successfully created. Moving to the right, we have 2 parallel tasks, Add User Alice and Add User Bob, both marked as Success. This demonstrates that the script executed without issues, adding these users efficiently to the system. Beneath these operations, there's a crucial tab labeled Escalated Privileges for Alice. This step also shows a status of Success, which indicates that Alice has been granted the necessary elevated permissions after her account was created. The flow from the top to the bottom clearly indicates the order of operations and highlights that all steps have been completed successfully. This figure encapsulates the straightforward workflow of user creation in Ansible, showcasing how the tool can automate group and user management effectively. In our next chapter, we will delve into Ansible Galaxy, where you'll discover a treasure trove of roles and collections shared by the community. Until then, I hope this introduction to Ansible excites you as much as it excites me. Remember, Automation isn't just about getting things done. It's about reclaiming your time and reducing the tedious parts of your job. And who wouldn't want more time for coffee breaks, right? Until next time, happy automating. To begin our journey into Ansible, the beloved automation tool that brings harmony to configuration management, let's dive straight in and install Ansible. If you're ready, grab your laptop, open a terminal, and let's get this show on the road. First things first, let's understand that installing Ansible can be done in different ways depending on your operating system. As you might guess, the method will vary for macOS, Linux, and Windows. Today we aim for a seamless experience, so let's ensure you have all the prerequisites in place. You don't want to be caught off guard in the middle of an installation process, right? It's like going to a buffet but realizing you forgot to wear pants. To install Ansible on your macOS using Homebrew, you'll need to run the command brew install Ansible in your terminal. This command is straightforward but powerful. When you execute it, Homebrew fetches the Ansible package along with all its required dependencies, ensuring that everything needed for Ansible to function correctly is gathered and set up. As the installation process proceeds, Homebrew keeps you informed with detailed output about the actions it's performing. You'll see messages indicating that the package is being downloaded, as well as any dependencies that might also need to be installed. This transparency is one of the key benefits of using Homebrew, as it not only installs the software, but also offers guidance on how to use it post-installation. Once the command is complete, you will have Ansible ready on your system, and you can begin to explore its capabilities. This installation step marks the beginning of your journey into automation with Ansible, enabling you to streamline your workflows efficiently. To begin, it's essential to check if you have pip installed on your system, as it is Python's package manager and a key tool for managing Python packages. You can do this by running the command pip version in your terminal. This command will return the version of pip that is currently installed, confirming that you have it ready to use. If this information is displayed, you can proceed confidently, knowing that pip is available on your system. Once you have verified the presence of pip, installing Ansible is straightforward. You can accomplish this by executing the command pip install Ansible. This command tells pip to download and install Ansible, along with all the necessary prerequisites required for it to function properly. The process is designed to be user-friendly, allowing you to quickly set up Ansible on your machine without excessive hassle. With these two simple commands, you're well on your way to utilizing Ansible for automation tasks. To upgrade Ansible when using Homebrew, you simply execute the command brew upgrade Ansible. This command ensures that you receive the latest updates for Ansible available through the Homebrew package manager, keeping your installation current and benefiting from the latest features and bug fixes. If you prefer to use pip for managing your Python packages, upgrading Ansible is done using pip install Ansible upgrade. This command fetches the latest version of Ansible from the Python package index, ensuring you always have the most up-to-date version directly from the source. In situations where you need to revert to a previous version of Ansible with Homebrew, you can uninstall the current version with brew uninstall Ansible and then reinstall a specific version. For instance, brew install Ansible at 2.0. Remember to replace 2.0 with the desired version number to meet your needs. For pip users, rolling back to a prior version can be done with the command pip install Ansible 2.3.1.0. This allows you to specify the exact version you want, enabling you to maintain compatibility or troubleshoot any issues with the latest releases. To begin the installation process on Ubuntu, the first step is to update your package manager's index. This is done with the command sudo h apt-get update. Running this command ensures that you have the latest information about the available packages and their versions in the repositories. Once the package manager is updated, you can proceed to install Python 3 pip, which is essential for installing Python packages, including Ansible. The command sudo h apt-get install Python 3 pip will install pip, allowing you to manage Python packages efficiently. Once pip is successfully installed, you can install Ansible using a simple command. By executing sudo h pip install Ansible, you instruct pip to download and install the Ansible package from the Python package index, PyPI. This method of installation is recommended as it typically provides the latest version of Ansible, which is important for utilizing the latest features and security updates. After initiating the installation, you should see messages confirming that the download and installation of Ansible are proceeding smoothly. Remember, if you need to upgrade Ansible in the future, you can rerun the same command with the upgrade flag. To begin the installation of the Windows Subsystem for Linux, WSL, you will need to open PowerShell and execute the command WSL install. This command initiates the installation of WSL, which allows you to run a Linux environment directly on your Windows machine without the need for a virtual machine. This step is crucial as it sets the foundation for the next stages of setting up your Linux environment. Once WSL is successfully installed, the next step is to choose a Linux distribution, such as Ubuntu, from the Microsoft Store. After installation, you can launch the Ubuntu terminal, where you will carry out the installation of Ansible. Start by updating the package list to ensure you have the latest information on available packages using the command sudo h apt-get update. After updating, you will install the necessary Python package manager, pip, with sudo h apt-get install python 3 pip. Finally, with pip installed, you can easily set up Ansible by executing sudo h pip install Ansible. This sequence of commands will successfully install Ansible within your WSL environment, enabling you to leverage its capabilities on your Windows system. To get started with multipass on a Mac, the first step is to install the tool by running the command brew install multipass. This command uses Homebrew, a popular package manager for Mac OS, to download and install multipass, allowing you to easily launch and manage virtual machines. For users on Ubuntu, the installation is straightforward as well. You can simply use the command snap install multipass, which utilizes Snap, another package management system, to install multipass. Once you have multipass installed on your system, you can launch a virtual machine with the command multipass launch-n Ansible VM. This command creates a new Ubuntu instance named Ansible VM, providing you with an isolated environment for testing your Ansible commands without affecting your local setup. After launching the virtual machine, the next step is to connect to it using the command multipass shell Ansible VM. This command grants you access to your newly created instance, welcoming you to your very own virtual machine where you can practice and develop your Ansible skills freely. To start linking your Ansible playbooks with the virtual machine, the first step is to obtain the VM's IP address. This can be accomplished by using the command multipass info Ansible VM, which retrieves various details about your virtual machine, including the IP address. Running this command in the terminal will give you essential information, particularly regarding the network setup of the VM. After acquiring the IP address, the next step is to prepare your inventory file. This file serves as a guide for Ansible, indicating where it should execute its tasks. The inventory file can be straightforward, comprising just a single line that includes the IP address of the VM and any relevant connection information. For instance, you would enter the VM's IP, such as 192.168.64.7, along with the SSH user that Ansible will use to establish the connection, which could be represented as Ansible user equals your username. Remember to update the IP address to reflect the actual address of your VM. This setup is essential for Ansible to operate effectively, enabling it to send commands to the correct host with ease. To run your first Ansible playbook and verify the setup of your virtual machine, you'll execute a simple command using Ansible. The command begins with Ansible, which is the command line tool that allows you to manage your inventory of resources and run tasks across them. Following that, you specify the inventory file with the -i flag. This file contains the list of your hosts where you want to apply your Ansible configuration. In this case, it points to your inventory file. Next, you denote the target machine with Ansible VM, which represents the virtual machine configured in your inventory. Here you'll replace Ansible VM with the actual name of your VM, as defined in the inventory file. The -m flag specifies the module you are using, and in this instance, you're using the ansible.builtin.setup module. This module collects and displays detailed information, known as facts, about the target host. By running this command, You are confirming that your Ansible installation is working correctly and that your virtual machine is properly configured to respond to Ansible commands. It's a crucial step to ensure everything is set up before proceeding with more complex automation tasks. We've covered quite a lot today, installing Ansible across different platforms and getting a feel for the environment where you're going to be doing your magical automation. You are now equipped with the tools to install Ansible anywhere, on any system, including a clean setup for virtual testing. As you embark upon this new chapter in your tech journey, never hesitate to explore and tinker. Ansible is a powerful ally in automation. It just takes a little setup to get started. Enjoy your newfound powers of automation and make your systems as delightful as a perfectly brewed coffee. Happy Ansibling, and may your playbooks always run without errors. Ansible is a powerful automation tool that simplifies IT tasks and configurations across multiple machines. In this section, we'll delve into what Ansible is, how to install it, explore some of its key components, and see how to use it for configuring a virtual machine. So buckle up as we embark on this exciting journey through the world of Ansible. Let's start off with a little background about Ansible. Ansible is an open-source automation platform that allows you to automate the provisioning, configuration, and management of systems and applications. Its declarative nature means you simply define your system's desired state, and Ansible will ensure that your systems are configured to meet that state. Imagine an orchestra conductor directing musicians to create a harmonious piece of music. That's essentially what Ansible does with your IT infrastructure. To begin the installation process, you need to ensure that Python and its package manager, pip, are installed on your system. You can verify this by running the commands python-version and pip-version in your terminal. If these commands return version numbers, it indicates that both Python and pip are ready to use. If not, you will need to install Python before proceeding. Once you have confirmed that both are installed, you can move on to the installation of Ansible. Open your terminal and execute the command sudo h-pip install Ansible. This command utilizes pip to install Ansible system-wide, which means you will be able to access it from any location on your machine. The use of sudo may be necessary to give the installation process the appropriate permissions. After the installation completes, you should verify that Ansible was installed correctly by running Ansible-version. If everything went smoothly, you will see the version number of Ansible displayed in your terminal. This confirms that you have successfully installed Ansible and are ready to start using it for automation tasks. In this section, we will look at a specific task you can include in your Ansible Playbook to ensure that the Network Work Time Protocol (NTP) package is installed on your target machines. The task begins with the directive to name the operation, which is install the latest version of NTP. This name serves as a label for the task, making it easier to identify during execution. The code utilizes the ansible.builtin.apt module, which is specifically designed for managing packages on systems that use the Advanced Packaging Tool, APT, such as Debian and Ubuntu distributions. The name parameter specifies the package to be installed, in this case, NTP. Setting the state parameter to latest instructs Ansible to ensure that the NTP package is always present at its most recent version. If NTP is not installed, or if an older version is detected, Ansible will take the necessary steps to update or install the correct version. By including this task in your playbook, you can automate the process of package management on multiple systems, ensuring consistent configurations across your environment. To launch a virtual machine using multipass, you'll execute the command multipass launch n-ansible VM. This command is essential as it initializes a new virtual machine instance and assigns it the name Ansible VM. Naming your VM is useful for identification, especially when managing multiple instances. Once you run this command, multipass will automatically handle the underlying configurations and provision the VM for you, allowing you to focus on deploying your applications. After launching the VM, the next step involves gathering important information about it. This is done using the command multipass info ansible VM. By executing this command, you'll retrieve various details about your newly created virtual machine, including its IP address. This IP address is crucial for configuring your inventory file, as it allows you to connect and manage the VM effectively from your local environment. Remember to keep track of the IP address provided in the output, as you'll need it in subsequent steps of your configuration process. To begin, we need to create an Ansible inventory file named hosts that will contain the IP address of the virtual machine you want to manage. Replace your VM IP in the file with the actual IP address of your VM obtained earlier. This inventory file will tell Ansible which host to target when running tasks. Next, we'll write a playbook to configure the time synchronization on our virtual machine. In the playbook, we specify a name for the task, the hosts to target, in this case, Ansible hosts, and that we want to execute the tasks with elevated privileges using become true. The first task in the playbook is to install the latest version of the Network Time Protocol (NTP) package, which is essential for synchronizing system time across machines. This task uses the Ansible built-in app module to ensure that the NTP is installed in its latest available version. Finally, to execute the playbook, you will run the command Ansible Playbook-I hosts playbook.yml in your terminal. This command tells Ansible to use the inventory file you created and to execute the tasks defined in your playbook against the specified virtual machine. As the playbook runs, you will see Ansible automatically logging into the VM and carrying out the installation. To verify the installation of the NTP service, you begin by accessing your virtual machine using the command multipass shell Ansible VM. This command allows you to enter the shell environment of the virtual machine named Ansible VM, enabling you to execute any necessary operations within that specific environment. Once you are inside the shell, you have full access to manage and check the services running on the virtual machine. After successfully entering the virtual machine, you can check the status of the NTP service by running the command systemctl status NTP. This command provides vital information about the NTP service's current state, including whether it is active, inactive, or failed. If the setup is correct, you should see the service status indicating that it is up and running. This step is crucial for ensuring that your time synchronization service is operational, which is essential for maintaining the correct system time across the network. Overall, these commands illustrate how easily Ansible streamlines the management of system services and configurations, making complex tasks more accessible for users. Now let's look at this figure that outlines the release cycle for Ansible Core. The flowchart illustrates the systematic approach to launching major versions of the Ansible Core software, highlighting the key processes involved. At the top, we see the launch of a new Ansible Core major version, which is the starting point for the entire cycle. Following the launch, there's a clear support strategy for the latest version, along with the two prior versions. This ensures that users can continue to rely on the stability and functionality of their current environments while preparing for upgrades. Next, the flow leads to a collection freeze in the Ansible community package, indicating a point where new features are paused to focus on stability and final testing. As we move down the chart, a new major version of the Ansible community package is released, which is essential for keeping the tools up to date. Continuous feature development in collections is emphasized next, signifying that improvements and enhancements remain an ongoing priority. The schedule for minor releases of the Ansible Core versions every 4 weeks ensures that updates are both timely and frequent, allowing the community to benefit from enhancements without long waits. Parallel to this, individual collections are highlighted, showcasing their capability to release both minor and major versions independently. This provides flexibility and encourages innovation within the community. Additionally, the chart indicates a feature freeze specifically on the Ansible Core, further underlining a phase of focus on stability before releasing new versions. Finally, the figure concludes with the release candidate for the Ansible Core and testing phases, culminating in the launch of the next major version. This comprehensive flowchart illustrates the dynamic and interconnected processes that make up the Ansible release lifecycle, emphasizing a structured approach to software development and community involvement. Welcome to our second chapter. Here we're going to be looking at the Ansible Galaxy command. We're going to be covering the features provided by the command and also discussing its importance in the development of Ansible over the last few years. Ansible Galaxy is an online repository of community-contributed roles. We will discover some of the best roles available, how to use them, and how to create your own role and have it hosted on Ansible Galaxy. By the end of the chapter, we will have worked through the following topics: the Ansible release lifecycle, introduction to Ansible Galaxy, what is a role, publishing to and using Ansible Galaxy roles, Ansible collections, and Ansible Galaxy commands. Before we dive into exploring Ansible Galaxy, let's take a closer look at what Ansible Galaxy is. It's more than just a command. It's a movement that encourages collaboration and sharing within the community. Imagine a bustling marketplace filled with a plethora of tools, each designed to help you accomplish various tasks with ease. That's what Ansible Galaxy is like for Ansible users. Now, let's look at the figure. This screenshot displays the Ansible Galaxy interface, which serves as a hub for finding and sharing Ansible roles and collections. At the top, you can see the navigation bar that includes links to essential sections such as Home, Search, Community, and Documentation. These elements help users easily access resources and find relevant content. In the central portion of the figure, there is a Most Popular section, highlighting various categories such as System, Development, Database, Security, Networking, Cloud, and more. Each category is visually represented with icons, facilitating quick identification and ease of use. This categorization allows users to navigate through the most sought-after roles and collections, making it simpler to locate tools that fit their automation needs. Below the Most Popular section, there are two buttons, Download and Share. The Download option encourages users to initiate their automation projects by accessing pre-packaged units known as roles and collections. In contrast, the Share section invites users to contribute to the community by sharing their own roles and collections, fostering collaboration and knowledge exchange among Ansible users. Lastly, towards the right side of the figure, there is a featured area that highlights upcoming events such as the Ansible Fest. This section emphasizes the importance of community engagement and continuous learning within the Ansible ecosystem, prompting users to participate in events that can enhance their skills and knowledge further. Overall, this figure encapsulates the collaborative and modular nature of Ansible as a tool for automation. Now that we have our timeline contextualized, let's shift the focus back to Ansible Galaxy. It's important to note that Ansible Galaxy is not just a repository, but a thriving ecosystem of collaboration and sharing. Notably, you can think of Galaxy as a library filled with roles that have been crafted by fellow users. These roles range from simple configurations to complex setups. What is a role, you ask? A role is simply a way to package and organize automation tasks. It can contain files, templates, tasks, and handlers that are all focused on a specific functionality. By breaking tasks into roles, you improve code reusability and maintainability. It's like having your own toolbox, with each role tailored for different jobs. To create a new role in Ansible, we begin by using the command Ansible Galaxy role init roles my first role. This command initializes a new directory structure for our role named my first role within a roles directory, ensuring that all necessary files are created according to established best practices. The role will contain essential components, including a README file for documentation and a main tasks file where the core functionalities of the role are defined. In the tasks main.yml file, we outline the steps for managing NTP configuration on a server. The first task utilizes the app module to ensure that the NTP package is installed, specifying its desired state as present. This guarantees that the necessary software is available. Next, we have a task that employs the template module to deploy a configuration file, ntp.donfit2, to the appropriate destination, which is /ntp.conf. This task also includes a notification to restart the NTP service whenever changes are made. Finally, we confirm that the NTP service is running by using the service module, setting its state to started, and enabling it to start at boot. This comprehensive approach ensures that NTP is properly managed on the server. To incorporate a role from Ansible Galaxy into your project, you'll need to use the Ansible Galaxy install command. This command is straightforward and serves as your gateway to accessing a plethora of predefined roles hosted on Ansible Galaxy. The syntax involves specifying your GitHub username followed by the name of the role you wish to download, formatted as yourusername.yourrolename. For example, if your GitHub username is John Doe and the role you want to install is called web server, the command would be Ansible Galaxy install johndoe.webserver. When executed, this command will search for the specified role on Ansible Galaxy and automatically download it into a designated directory on your local machine. It's important to remember that roles are stored in a hidden directory called /ansible/roles. This organized structure allows you to easily manage and share roles across various playbooks. By utilizing the roles you find on Ansible Galaxy, you can leverage community contributions, streamline your automation processes, and enhance the overall efficiency of your workflows. To manage Ansible roles efficiently, one approach is to create a requirements.yml file in your project directory. This file lists all the roles you want to install, making it easier to maintain dependencies. For example, your requirements.yml might contain entries like etnoc.updateubuntu, geerlingguy.nginx, and russamkendrick.ansible role learn Ansible example. This structured format allows for clear documentation of your project's dependencies. Once you have your requirements.yml set up, you can install the listed roles using the Ansible Galaxy install requirements.yml command. This command scans your requirements.yml file and installs any roles that are not already present in your specified roles directory, streamlining the process of setting up your environment. Additionally, when utilizing specific roles, you may encounter situations where additional libraries are necessary. For instance, if your playbooks make use of AWS modules, you will likely need the Bodo library. To ensure your playbooks run smoothly, you can install it using pip install -r Ansible Collections, Amazon AWS /requirements.txt. This guarantees that all essential libraries are in place, allowing for seamless execution of your Ansible workflows. As we round up our exploration of Ansible Galaxy, it's imperative we acknowledge its impact on the community. It fosters collaboration and contributes to an ever-growing knowledge base. With over 15,000 roles available, from managing Nginx to automating AWS deployments, the possibilities are endless. Playing a part in this community means not just using roles, but contributing back as well. When you create and publish roles, you're helping others in their automation journey. Every role you share can potentially save someone hours of work. In closing, Ansible Galaxy and the Ansible Galaxy command are powerful tools in your Ansible toolbox. They help you leverage the community's offerings, simplifying automation and enhancing productivity through shared knowledge. So go forth, explore, create, and share. In our next chapter, we'll dive deeper into Ansible commands and tools that ship as part of Ansible Core. Until then, happy automating. Using Ansible Vault for secure data management is an essential skill for sysadmins, developers, and anyone involved in automation tasks. Today, we're going to delve deep into how to leverage Ansible Vault to keep our sensitive data secure while still efficiently managing our configurations. Let's find those keys, decrypt those mysteries, and secure our secrets together. Ansible Vault is a powerful tool designed to encrypt and decrypt sensitive data in your Ansible projects. Why do we need this, you ask? Well, in any automation environment, especially those that involve collaboration, sensitive data such as passwords, API keys, and private SSH keys tend to slip through our fingers and end up in plaintext files. This is a recipe for disaster. Imagine someone accidentally checks in a variable file containing plaintext passwords into a public repository. Yikes. Not only are we looking at potential security breaches, but those passwords may become everyone's business in a matter of seconds. Ansible's answer to this problem is Ansible Vault, making sure that sensitive information remains confidential even when it's shared among team members. Using the Ansible Vault command, we can encrypt files, or even just specific variables, and have them decrypted during runtime in memory without exposing their plaintext version. To create an encrypted file, the first step is to ensure that you have Ansible installed on your machine. You can accomplish this easily by running the command pip install Ansible in your terminal. After installation, it's time to create a file containing sensitive data, which we will call secrets.yml. This file holds important credentials, such as database passwords and API keys, making it essential to protect this information. Once you have your secrets.yml file ready, you will use Ansible Vault to encrypt it. Navigate to the directory containing the file and run the command ansible-vault encrypt secrets.yml. Upon executing this command, the system will prompt you to set a password. This password is vital for decrypting your file later, so it's important to choose a strong and memorable one. After entering the password, you'll see that the contents of the file become unreadable, replacing sensitive information with a string of gibberish, effectively securing your credentials from unauthorized access. This method ensures that your sensitive data remains protected, allowing you to manage it safely. To begin, you'll want to inspect your encrypted file to understand its contents. This can be achieved by using the command ansible vault view secrets.yml. Executing this command prompts a password entry, specifically the one you set during the encryption process. This password acts as a shield, ensuring that only authorized personnel can access sensitive information, thereby preventing unauthorized users from viewing the file's contents. If you need to modify or add more sensitive data, you have two options. You can either amend the existing encrypted file directly or encrypt individual variables as needed. For quick encryption of a new string, such as a password, you can use ansible-vault encrypt string my new password-name dbpassword. This command outputs the encrypted string in the proper format for direct insertion into your variable file. For example, the output will look like db_password vault followed by a block of encrypted content. This method allows you to securely manage sensitive information without accidentally exposing it, ensuring that the context remains clear and safe. In this example, we have a simple Ansible playbook defined in a file called playbook.yml. The playbook targets the local host and utilizes an external file named secrets.yml to retrieve sensitive variables, such as a database password. Within the tasks section, there's a single task that employs the debug module to print out the value of database password. This approach allows us to keep sensitive information separate from our playbook, thus enhancing security. When executing this playbook, it's crucial to inform Ansible that we are working with an encrypted vault file. We achieve this by using the command ansible playbook playbook.yml-vault ID @prompt. The @prompt option instructs Ansible to request the vault password interactively when the playbook is run. However, for environments where automation is key, such as CI/CD pipelines, manually entering passwords can be cumbersome. To streamline this process, we can store passwords in a secure file, enabling automated access without frequent manual input while still maintaining security protocols. To securely manage sensitive data in Ansible, one effective method is to use a password file. By creating a text file named vaultpassword.txt and placing your encryption password inside it, you ensure that your secrets can be accessed programmatically. It's essential to restrict access to this file, as anyone who can read it will be able to decrypt any encrypted data you have. Once your password file is set up, you modify your Ansible command to include this file reference. The command ansible playbook playbook.yml vault ID vault file @path/to vaultpassword.txt specifies the playbook you wish to execute along with the credentials needed to decrypt any encrypted variables or files. By leveraging this approach, Ansible will read the password directly from the specified file, automating the decryption process without the need for manual input each time. This not only streamlines your workflows, but also enhances security by keeping sensitive information out of version-controlled scripts, thus maintaining a higher standard for automation within your deployment processes. Now, let's address the elephant in the room, committing encrypted files to a repository. Do it! Yes, you heard me right. You can freely commit your encrypted secrets file to your source code repository. Why? Because in its encrypted state, no one can touch your secrets. However, make sure that your plaintext password files never see the light of day in your source code repository. If you mistakenly commit them, it's time for a password reset. In scenarios where you're sharing the vault across the team, all users will need to know the password or have access to the vaultpassword.txt file. Ensure that the vault password is kept in a secured location, like a password manager or an encrypted secret store. Additionally, remember that whenever you add or modify the encrypted content in your files, always test that your playbook works properly before pushing any changes to avoid downtime once it's applied in production. Now that you've got a grasp of how to use Ansible Vault, you're ready to securely manage sensitive data in your automation workflows. Always remember the principle of least privilege. Only share Vault access with individuals or processes that genuinely require it. Ansible Vault is a robust and flexible solution for protecting your sensitive data. So there you have it, folks. Using Ansible Vault to secure your data is not only important, but it's also straightforward once you've practiced it a few times. Keep your secrets safe, your pipelines efficient, and your automation running smoothly. Happy automating. The LAMP stack is the term used to describe an all-in-one web and database server. Typically, the components are as follows. Linux is the underlying operating system. In our case, we will use Ubuntu 22.04. Apache is the web server element of the stack. MariaDB is what we will use as the database component of the stack. Typically, it is based on MySQL, which could also be used. PHP is the dynamic language used by the web server to generate content. Now let's look at the figure. This schema illustrates the proposed architecture for the LAMP stack setup, showcasing the various components and their interactions. At the top, we see the internet, which serves as the entry point for all incoming requests. This connection is represented as a flow from the DigitalOcean LAN, highlighting the infrastructural backbone that supports the web application. On the left side, two key elements are depicted: the Apache benchmark server and the web server. The Apache benchmark server is typically used for performance testing, ensuring that the Apache server can handle multiple requests efficiently. Meanwhile, the web server is central to processing these requests, providing a direct link to the application stack. The application stack on the right side features several crucial components stacked vertically. At the top is Nginx, serving as the reverse proxy, which plays a vital role in enhancing performance through caching. Below that, Apache is displayed as the primary web server handling dynamic content. Following Apache, PHP resides, enabling the execution of server-side scripts, which ultimately generates the content sent back to users. Finally, MySQL is represented at the bottom, functioning as the database management system that stores and retrieves all necessary data for the application. Lines and arrows demonstrate the connections and communication between the components, clarifying how data flows through the architecture. This visual representation not only illustrates the structure of the LAMP stack, but also emphasizes the relationships between each component, vital for a seamless web application experience. The architecture surrounding the LAMP stack is well structured. The operating system, Linux, provides the tools that create an efficient environment for running the web server. By choosing Ubuntu, a user-friendly Linux distribution, users can readily access a powerful foundation for their stack. Linux not only manages system resources effectively, but also offers a rich repository of software options. Installing Linux is akin to laying the groundwork for your sandwich. The better you lay the foundation, the better your subsequent layers will adhere. To begin installing Apache on your Ubuntu system, the first command you will execute is sudo apt update. This command updates the package index on your system, ensuring it has the latest information about available packages and their versions. Think of this step as checking the menu for the most current options before placing your order. It allows your system to be aware of any new versions or changes so that you can install software without any conflicts. Once the package index is updated, you can move on to the second command, sudo apt install Apache 2. This command is your direct request to install the Apache web server. Here, apt is the package management tool that handles the installation of software, while install signifies that you want to add a new package. The term Apache 2 refers to the specific version of the Apache server you are installing. By executing this command, you effectively place your order for the server, which then gets downloaded and set up on your system, ready to start serving web pages to users. To begin with, installing MariaDB is essential for setting up your database environment. The command sudo apt install MariaDB server is used to install the MariaDB server on your system. The sudo prefix ensures that you have administrative privileges, allowing you to perform the installation without running into permission issues. By using the app package manager, the system searches for the latest version of MariaDB available in the repositories and installs it along with any required dependencies, ensuring a smooth integration into your operating system. Once the installation is complete, it's crucial to secure your MariaDB setup to protect against unauthorized access. The command sudo mysql secure installation initiates a security script that guides you through various important configurations. This process allows you to set a root password, remove anonymous users, disable remote root access, and delete the test database, which is often unnecessary in a production environment. By completing these steps, you effectively lock your database, much like securing a fridge, to restrict access to only those who are authorized, thus safeguarding your valuable data. Scarily enough, unofficial access to your database can lead to a guest eating straight out of your fridge. Thus, securing your database with a strong password is paramount. During the secure installation step, it will prompt you to set a root password and configure various options to enhance security. To begin utilizing PHP alongside Apache, we need to install the necessary packages on our server. The command to achieve this is sudo apt install phplib-apache2mod php mysql. Each component of this command plays a crucial role in setting up a functional PHP environment. Starting with sudo, this part of the command gives us administrative privileges, allowing us to execute installation commands that affect system-wide configurations. This is essential for installing software on your system. Next, apt is the package manager for Ubuntu and other Debian-based systems. It's a streamlined way to fetch and install packages directly from the repository. The install keyword indicates that we intend to install the subsequent packages. The first package, PHP, is the core language itself, which will enable you to run PHP scripts and process dynamic content on your web server. The lib-apache2mod PHP package is the Apache module that integrates PHP with your web server, enabling Apache to process PHP files and serve them correctly to users. Lastly, PHP-PEL facilitates communication between PHP and MySQL databases, ensuring that your applications can perform database operations seamlessly. This installation command sets the stage for a dynamic and interactive web experience. Now let's look at the figure, which illustrates the directory structure for Chapter 04 of our tutorial. At the top level, we see a folder labeled Chapter 04. This serves as the root for various configuration files and subdirectories that are essential for our setup. Each element within this structure plays a significant role in ensuring seamless integration between services. Directly beneath the Chapter 04 folder, we find important YAML files: cloudinit.yaml, example key, and example key.pub. These files are pivotal for initializing cloud resources and establishing secure connections. The cloudinit.yaml file specifically contains configurations for cloud instance initialization, while example key and example key.pub are used for handling SSH keys, facilitating secure communication between servers. Moving into the group vars directory, there's a file named common.yml. This file is crucial as it houses variable definitions applicable to all hosts defined within the environment. These variables streamline the configuration process, allowing for more maintainable and reusable code. Next, we observe the hosts and hosts.example files. These files contain host definitions and inventory information, which are essential for Ansible to know which machines to connect to for various tasks. The organization here ensures that the configuration remains clear and accessible. Delving deeper, the roles directory branches out into several folders: Apache, Common, MariaDB, and PHP. Each of these directories corresponds to a specific service configuration. For instance, the Apache folder would contain files and scripts necessary for setting up the Apache web server. Similarly, the MariaDB folder is dedicated to configuring the MariaDB database, while the PHP folder holds everything related to the PHP installation and setup. Overall, this figure encapsulates a well-structured approach to organizing project files, emphasizing efficient communication between the web server, the database, and PHP. A common variation of the LAMP stack is called the LEMP stack, where we replace Apache with Nginx, a web server that handles web traffic with greater efficiency under high loads. If Apache is like a bustling restaurant with many waiters, Nginx is akin to a food truck that serves food quickly and efficiently, minimizing wait times. The beauty of the LAMP stack lies in its simplicity and flexibility. As we continue, we can expand the LAMP stack to include additional components for increased functionality. For instance, many developers opt to integrate frameworks like Laravel for PHP, adding even more zest to their web applications. Now let's look at the figure displayed on your screen. It presents a confirmation message indicating successful deployment of an HTML page. At the top, we see the bold word "success," which immediately suggests that the deployment process has been completed successfully. This positive feedback is essential as it confirms that the initial setup of our web server has been executed properly. The message informs us that this page has been deployed using Ansible, pointing out its application within the Ansible VM context. This indicates the use of automation tools for efficient deployment management. The user responsible for this deployment is specified as LAMP, which is part of the WW data group, highlighting the user permissions set for web server operations. Furthermore, the web root is noted as home/lamp/web, providing clarity on where our web content is stored. The default index file is identified as index.html, which is the primary file that the web server will serve to visitors when they access this domain. This information is crucial for anyone looking to manage or update their deployed content in this environment. Additionally, the figure offers links to access a PHP info file and an adminer application. These resources can be incredibly useful for developers wanting to review their PHP configuration or manage database operations efficiently. The presence of these links also acts as a prompt for further interactions, suggesting next steps for users who are ready to explore the capabilities of their newly set up LAMP stack. In this chapter, we're diving into the exciting world of deploying a LAMP stack using Ansible on a local multipass virtual machine. So buckle up and get ready for some serious automation magic. Now, if you're wondering what exactly a LAMP stack is, it stands for Linux, Apache, MariaDB, or MySQL, and PHP. It's the classic foundation for web applications, hosting everything from simple blogs to complex platforms. In the first step, we create a main directory called Chapter 04 to house our playbook and its components. This is an essential starting point that keeps our workspace organized. By changing the current directory to Chapter 04 using cd Chapter 04, we ensure that all subsequent commands are executed within this context, maintaining order. Next, we set up a group vars directory, which is pivotal for defining variables that apply to specific host groups within our playbook. To prepare for this, we create a file called common.yml that will hold shared variables for these groups. Following this, we create an empty production file, which will serve as our inventory list, detailing the servers involved in our deployment. Simultaneously, site.yml acts as the master playbook where we will orchestrate the installation and configuration processes. Lastly, we establish a roles directory and initialize a role named common using the Ansible Galaxy role init command. This role will encapsulate tasks, handlers, and defaults that pertain to the LAMP stack installation, fostering modularity and reusability in our automation efforts. Now that we have our structure laid out, let's dive deeper into what each component of our stack does. The first piece of our puzzle is our Linux operating system, specifically Ubuntu 22.04 in this case. It provides the environment where everything else will live. Next is Apache, which serves as our web server, handling requests from the browser and serving up the content. MariaDB comes next in line. This acts as our database server, where all our data will be stored and retrieved as needed. Lastly, we have PHP, which works behind the scenes to dynamically generate web pages. When combined, these technologies make up what we call the LAMP stack, and it's a powerhouse for web development. For this project, we'll create distinct roles for each component of the stack. We'll have a role for common tasks like setting up the server, another for installing Apache, one for setting up MariaDB, and the last for PHP. This modular approach allows us to manage each component independently, which is a fantastic way to keep everything organized, much like how you wouldn't pile everything in one drawer. In the provided code snippet, we define a task that is crucial for maintaining the health of our server environment. The task is titled Update apt cache and Upgrade Packages, reflecting its purpose of ensuring that all server packages are current. We utilize the Ansible.builtin.app module, which interacts with the Advanced Package Tool, APT, used in Debian-based systems for package management. The first parameter, name sure, indicates that we want to target all installed packages on the server. This is an effective way to ensure that every package is considered for updates. The subsequent parameter, state latest, directs the system to upgrade all these packages to their latest available versions. Additionally, we enable update cache true, which ensures that the apt package cache is refreshed prior to any upgrade operations. By doing this, we not only maintain the latest package versions, but also enhance security and stability, reducing the likelihood of potential vulnerabilities or compatibility issues down the line. This simple yet powerful task serves as an essential foundation for a well-functioning server environment. In this section, we focus on installing common packages that will enhance the functionality of our server. Within the main.yml file, we define a task named Install Common Packages, utilizing the Ansible built-in.app module. This task ensures that the specified packages held in the Common Packages variable are present on our system. By setting the state to present, Ansible will install any packages listed that are not already installed, thereby ensuring our server is equipped with the necessary tools. The Common Packages variable is defined in the roles/common/default/main.yml file and includes a list of essential utilities. This list comprises packages such as NTP and Git, which are crucial for time synchronization and version control, respectively. Additionally, tools like Vim and Unzip are included, offering basic text editing and file extraction capabilities. With these packages installed, we create a versatile server environment, allowing us to tackle various tasks as needed, much like having a well-stocked toolbox ready for any project. The first task we will undertake is the installation of the Apache web server. In our Ansible setup, this task is defined within the Playbook located at roles/Apache tasks/main.yml, ensuring that it is organized and manageable. The specific Ansible module we use for this task is Ansible.builtin.apt, which is designed to handle package management on Debian-based systems. We set the state of the packages to present, meaning that Ansible will ensure these packages are installed on the target server. The actual package names are referenced through the Apache Packages variable, which we'll define shortly. Next, to maintain clarity and modularity in our configuration, we will define the Apache Packages variable in the roles apache/defaults/main.yml file. Here, we specify the list of necessary packages that need to be installed for Apache to function correctly. This list includes Apache 2, Apache 2 SSL Dev, CA certificates, and OpenSSL. By utilizing variables, we can easily modify the package list if needed, and when the task runs, our server will be fully equipped to serve web pages efficiently. In this section, we are focusing on a crucial step following the installation of Apache, adding users to the appropriate group to ensure proper permissions. The code provided is an Ansible task designed to add a user to the Apache group, specifically the www data group, which is the default for Apache. This grouping is essential because it grants the user the necessary permissions to manage web content on the server. The task is defined with a name for clarity and uses the Ansible.builtin user module to manipulate user accounts. The parameters include the user's name, which is dynamically fetched from the item.name within a loop. The groups parameter specifies the group to which the user will be added, referencing the variable Apache group. By setting append true, we ensure that the user is added to the specified group without removing any existing group memberships. The loop iterates through a list of users designated by the user's variable, systematically adding each one to the Apache group. This simple yet effective process establishes proper access controls, akin to giving our users the right keys to manage web content securely. In this section, we are setting up a vital component of our web server, the document root. This is the directory where all our website files, including HTML, CSS, and PHP, will be stored. The specified location allows our server to locate these files efficiently whenever a request is made. The configuration uses Ansible, a powerful automation tool, to create this directory. By utilizing the ansible.builtin.file module, we can ensure that the directory is not only created, but also configured with the correct permissions. The dest parameter is dynamically assigned using the variable document root, ensuring that we have flexibility in defining the exact location. To maintain security and functionality, we set the directory permissions to 0755, which allows the owner full access while granting read and execute permissions to others. Additionally, we assign the created directory to the user specified in the users.0.name variable and group it under the Apache group. This setup ensures that our web server has the appropriate access to the document root, enabling it to serve our web content seamlessly. In the provided code snippet, we focus on the installation of MariaDB through Ansible. The first task in our Ansible playbook, labeled Install MariaDB Packages, uses the ansible.builtin.app module to ensure that the specified packages are present on the system. This is crucial for setting up an operational MariaDB server. The action specified is to install the packages defined in the MariaDB Packages variable, which is dynamically referenced using Jinja2 templating syntax. Next, we define the MariaDB Packages variable in the defaults file. This variable is a list that includes essential packages, namely MariaDB Server, MariaDB Client, and Python 3-PyMySQL. Each of these packages plays a vital role. The server component allows us to run a MariaDB database, the client facilitates interactions with the server, and the Python library enables Python applications to communicate with the database. Organizing our tasks this way ensures clarity and maintainability, allowing us to efficiently set up a robust database server with minimal effort. In this section of our MariaDB role, we focus on starting the MariaDB service and ensuring it is configured to start automatically during system boot. To achieve this, we utilize the ansible.builtin.service module in Ansible. The first line identifies the task, clearly stating Start MariaDB. This provides clarity for anyone reviewing the playbook, indicating that its purpose is to manage the state of the MariaDB service. The subsequent lines specify the parameters for this action. The name attribute is set to MariaDB, which indicates that we are targeting the specific service associated with MariaDB. The state parameter is critical. It is set to started, which means that the playbook will execute a command to initiate the MariaDB service if it is not already running. Additionally, the enabled parameter is set to true, ensuring that the MariaDB service is enabled to automatically start on system boot. By implementing these steps, we guarantee that our database service is up and ready to handle requests whenever our applications need it, promoting a reliable and efficient database environment. In this section, we focus on securing our MariaDB installation by performing crucial tasks. First, we set a root password to regulate access. The code uses the community.mysql.mysql user module with the task name setMySQL_root_password. Here we specify the username as root and assign the password through a variable called MariaDB root password. This step ensures that unauthorized users cannot access the database without the correct credentials. Next, we address the issue of anonymous MySQL users, which can pose a security risk. In the second task, titled Remove Anonymous MySQL Users, we again utilize the community.mysql.mysql user module. This time, we specify the user field as an empty string, indicating we are targeting anonymous users. By setting the state to absent, we ensure that any anonymous users are removed from the system. Implementing these changes enhances the overall security posture of our database, minimizing vulnerabilities that could be exploited by malicious actors, and ensuring a more secure environment for our data management. In this section, we focus on configuring PHP, a crucial element for dynamically generating content in web applications. We begin by ensuring that PHP and its essential modules are installed. The first snippet of code outlines how to achieve this using Ansible's apt module, which manages packages on Debian-based systems. The task named Install PHP Packages specifies that the state should be present, meaning the mentioned packages will be installed if they are not already available on the system. The actual packages to be installed are indicated by the variable PHP Packages. Next, we define the PHP Packages variable in the defaults section of our role. This variable is a list that includes essential PHP packages, PHP, which is the core PHP package, as well as PHP MySQL, PHP XML, and PHP MB string. Each of these packages provides important functionality, enabling PHP to interact with MySQL databases, handle XML data, and manage multi-byte strings respectively. With these configurations in place, we move closer to completing our web application setup. In our playbook titled site.yml, we define a task to install the LAMP stack, which stands for Linux, Apache, MariaDB, and PHP. The playbook begins by specifying the hosts it will run against, labeled as Ansible hosts. This choice of hosts is crucial as it directs Ansible to perform the tasks on our intended server, in this case, a multi-pass virtual machine. We enable fact gathering to automatically collect data about the managed nodes. This information can be valuable for making decisions in our playbook execution. Additionally, we use become true alongside become method, Ansible built-in sudo to execute tasks with super user privileges, ensuring we have the necessary permissions to install software on the target hosts. The vars files section includes a reference to group vars/common.yml, which allows us to define variables to be used throughout the playbook, maintaining organization and reusability. Finally, we define the roles, Common, Apache, MariaDB, and PHP, that break down our playbook into manageable components, each responsible for a part of the installation process, thereby enhancing modularity and clarity in our automation workflow. To initiate your deployment process, you simply execute the command ansible-playbook-i host site.yml. This command utilizes Ansible, a powerful automation tool that simplifies the process of managing and provisioning servers. The Ansible playbook command is specifically designed to run a playbook, which is a file containing the instructions for the tasks you want to automate. In this case, the -i host flag specifies the inventory file, hosts, which lists the servers on which the playbook tasks will be executed. This inventory tells Ansible where to deploy the defined configurations and applications. Following that, site.yml is the actual playbook file that contains the structured tasks that Ansible needs to perform. Once you execute this command, the system will spring into action, with tasks running, necessary packages installing, and services starting up as outlined in your playbook. The output displayed in your terminal will keep you informed about the processes taking place, giving you a real-time view of the deployment status and any important messages or errors that may arise. So there you have it, a full course on deploying a LAMP stack using Ansible. You've learned about the components of the LAMP stack, the essentials of playbook structure, and how to automate this entire process. If you follow these steps precisely, you'll end up with a working LAMP stack ready to serve your web applications. Remember though, every environment is unique, so take this as a starting point and tailor the playbook to fit your needs. Happy automating, and may your servers run smoothly. And don't forget, if you ever run into issues, you can always refer back to this script for guidance. It's like having a trusty toolbox next to you while you work. Before we embark on our journey into the world of WordPress deployment, let's quickly define what WordPress is. If you've ever browsed the internet, which, let's be honest, is probably all of you, you've definitely encountered a website powered by WordPress. It's an open-source content management system, a handy tool for easily creating and managing websites. It's estimated that approximately 43% of all websites on the internet use WordPress. That's nearly half. Quite impressive, isn't it? As we step into the realm of deploying WordPress, it's important to understand that this process requires a working environment capable of supporting it. Specifically, we need to set up a stack called LEMP, which stands for Linux, Nginx, MariaDB, and PHP. If you're scratching your head with the acronyms, don't worry, we'll break each component down. First on our list is Linux, the operating system that supports everything. We'll be utilizing an Ubuntu distribution for this deployment, and that's where our adventure begins. In the initial step, we create a new directory named Chapter 05, which will serve as the foundation for our deployment playbook. This command also establishes subdirectories, specifically group vars and roles, which are essential for organizing configuration variables and defining roles respectively. Proper organization at this stage will streamline our workflow as we develop the playbook. Next, we create several crucial files within the Chapter 05 directory. The command includes creating common.yml, which typically holds shared variables, hosts, used to specify our target servers, and site.yml, where we will define our Playbook's main execution logic. Having these files in place sets a solid groundwork for implementing our deployment procedure. Finally, we navigate into the newly created Chapter 05 directory with the change directory command. This positional shift allows us to effectively work within the directory we just set up, ensuring that subsequent commands we issue pertain to this Playbook framework. By following these steps, we are not only organizing our workspace, but also positioning ourselves for a more efficient and manageable deployment process. To create our Ansible role for installing the software components, we begin by using the Ansible command line with the command Ansible galaxy role init roles stack install. This command initializes a new role directory structure named stack install. This directory will house all the necessary tasks, handlers, defaults, and variables required for our installation process, organizing our project and making it easier to manage as we build our playbook. Next, we need to ensure that our system is ready for installation by updating the package cache and upgrading the installed packages. We accomplish this with an Ansible task defined in the main.yml file located in the roles/stackinstall/tasks directory. The task is structured to use the ansible.builtin.app module, which is essential for managing packages in Debian-based systems. By specifying the state as latest, the command ensures that all packages are upgraded to their most current versions. Additionally, setting update cache true ensures that the apt cache is refreshed before performing any installations, allowing us to pull in the most up-to-date packages. This step is crucial for maintaining a reliable and secure environment for our WordPress installation. To begin with, we need to establish some variables that will define the Nginx repository URLs. This is accomplished by defining repo keys URL and repo packages in the roles/stackinstall/default main.yml file. The repo keys URL variable holds the URL for the Nginx signing key, which is essential for verifying the authenticity of the packages we'll be installing. Meanwhile, the repo packages variable lists the repository for Nginx and its source packages, tailored for the specific Ubuntu distribution in use. Once these variables are set, we can proceed to add the necessary keys from the specified URLs. This is achieved using the ansible.builtin.apt key module, which ensures that the keys are present on the system by iterating through the URLs defined in repo keys URL. Following that, the ansible.builtin.app repository module is utilized to install the repository packages. This module also iterates over the repo packages, confirming their installation while updating the package cache to reflect these changes. With these steps, we lay a robust foundation for the subsequent installation of Nginx itself. Once Nginx is operational, the next task in our playbook is to install several essential packages. The Ansible task named Update Cache and Install the Stack Packages utilizes the ansible.builtin.app module to ensure that the packages we need are installed. By setting the state to present, we indicate that these packages should be installed if they aren't already present on the system. The update cache parameter is set to true, which allows the package manager to update its cache before performing the installation. The pkg parameter is dynamically populated with a combination of system packages, extra packages, and stack packages, allowing for flexible management of our software requirements. Following the installation of the primary components, we move on to configuring them. We initiate this process by creating a new role named stackconfig with a simple command using Ansible galaxy role init roles/stackconfig. This command sets up a directory structure for the role, which will house all configuration tasks necessary to optimize our server environment. In this role, we will configure Nginx according to WordPress best practices, ensuring high performance and security for our WordPress installation. In this snippet, we begin by adding the necessary user group for WordPress. The first task, labeled Add the WordPress group, utilizes the ansible.builtin.group module. Here, we specify the group name using the variable WordPress system.group and control its existence by setting the desired state through WordPress system.state. This ensures that the required group for WordPress is created or maintained in the desired state, providing the foundation for proper permissions and operations down the line. Next, we move on to create the user who will run the WordPress service. The task, described as Add the WordPress User, employs the Ansible.builtin.user module. We provide various attributes such as the user's name, group, comment, which typically contains a description, home directory, and state. By referencing WordPress system.user, WordPress system.group, WordPress system.comment, WordPress system.home, and WordPress system.state, we ensure that this user is correctly configured within the system. This setup is crucial for establishing a secure environment where WordPress can function effectively. The configuration provided outlines a basic server block for an Nginx web server. It begins with the directive server, which marks the beginning of a server block where specific parameters for handling web requests are set. The listen 80 instruction tells Nginx to accept incoming traffic on port 80, the standard port for HTTP requests. Next, the server name directive is crucial as it defines which host names or IP addresses will be handled by this server block. Here, Ansible node name is a placeholder that will be dynamically replaced with the name of the node as per the Ansible configuration management tool, allowing for flexibility across different servers. The root directive specifies the root directory from which Nginx will serve files. In this case, WordPress system.home is again a placeholder, indicating the home directory for a WordPress installation, which allows for easy adjustments based on the deployment environment. Finally, the index directive lists the files to be served by default when a directory is requested, prioritizing index.php, followed by index.html and index.htm. This setup provides a foundational structure for serving a WordPress site efficiently. In this section, we focus on creating the necessary database and user for WordPress within our MariaDB setup. The first task is to create a dedicated database for WordPress. This is achieved using the community.mysqldb Ansible module, which ensures that the specified database, indicated by the variable wp-database.name, is present in the MariaDB instance. By setting state to present, we are explicitly instructing the system to create the database if it doesn't already exist. Next, we create a user who will manage and interact with this WordPress database. This is handled by the community.mysql user Ansible module. Here, we define the username and password for the new user using the variables wp-database.username and wp-database.password. The priv parameter is particularly important as it assigns privileges. In this case, we are granting all permissions on the WordPress database with the syntax wp-database.name all. Lastly, similar to the database creation, the user's state is also set to present, ensuring that the user is created if they do not already exist. The first step in our playbook is to download the WordPress command line interface, CLI tool, which greatly simplifies the process of managing WordPress installations. We achieve this by using the Ansible.builtin getURL module to fetch the CLI from a specified URL and save it to a designated path with executable permissions. Once we have the CLI installed, we proceed to configure our WordPress installation. This involves running a command to set up the core configuration, specifying essential parameters such as the database host, database name, username, and password. We utilize the Ansible.builtin.command module to execute this configuration command, ensuring WordPress can connect to the intended database accurately. Finally, after the configuration is complete, we can install WordPress itself. We again use the Ansible.builtin.command module to run the installation command, providing necessary details such as the site URL, title, admin username, password, and email. By executing these commands in the correct order, we automate the setup of WordPress, making the process efficient and repeatable. With our WordPress installation complete, we can give ourselves a well-deserved pat on the back. You now have a fully operational WordPress site that you can access via the URL defined during installation. This entire process may seem like a mountain of tasks, but once you set this up, you'll find the steps can be easily replicated for other deployments. Once logged in, feel free to explore your new WordPress site and start creating. So in conclusion, deploying WordPress involves understanding its requirements and setting up a robust environment. Like building a house, a strong foundation leads to a lasting structure. And if anything goes wrong, you can always fall back on your trusty playbook to do it all over again. Happy blogging! In this snippet, we define configuration settings for a WordPress installation using Ansible. The foundational element is the WordPress key, which encapsulates several essential variables that will drive our WordPress setup. The domain variable is a formatted string that dynamically incorporates the variable WordPress domain, establishing the base URL for our WordPress site. Next, we specify the title, which presents a user-friendly description of the site, helping to clarify that this WordPress instance is managed by Ansible on a specified operating system family. For user management, the username, password, and email fields are critical. Here, we set default credentials for the WordPress administrator. The chosen password, while adequate for demonstration, should be modified for actual deployments to enhance security. Additionally, the plugins key lists several popular WordPress plugins within an array format, enhancing the website's functionality. These plugins, such as Jetpack and WP Supercache, serve various purposes, from performance optimization to security enhancements. Each of these variables can be tailored to meet specific needs, making the setup customizable and adaptable. In the provided code snippet, we are utilizing Ansible's stat module to check if WordPress files are already present on our domain. This is a crucial step in the installation process, as it helps us avoid redundant installations. The task defined within the snippet is named "Are the WordPress files already there?", which serves as a clear identifier when we view the output of our playbook. The stat module is executed with a specified path that points to the index.php file within the WordPress directory, denoted here as WordPress system.home index.php. This path is dynamically constructed using a variable WordPress system.home, which should be previously defined in your Ansible setup to indicate the home directory of the WordPress installation. By registering the results of this check under the variable WP installed, we can later refer to this data to determine our next steps. If the index.php file exists, it indicates that WordPress is already installed, allowing us to conclude the installation process. If the file is absent, we know to proceed with downloading and setting up WordPress, ensuring a smooth installation workflow. The code snippet provided serves to download the latest version of WordPress through an Ansible playbook. It begins with a task named Download WordPress, which utilizes the ansible.builtin.command module. This module enables executing shell commands on remote hosts, allowing for effective automation. The specific command in use is constructed with the WordPress CLI path variable, wp-cli.path, followed by the command core download. This command prompts the WordPress CLI to retrieve the latest WordPress package. To ensure the download takes place in the correct directory, the chdir argument is set to WordPress system.home, directing the operation to the specified location where WordPress files should reside. Moreover, to handle potential permission issues, the task is executed with elevated privileges. This is achieved through the become directive, which allows the task to switch to a different user specified by WordPress system.user. The final condition, when not wp installed.stat.exists, ensures that the download only occurs if WordPress is not already installed, preventing unnecessary overwriting of files and optimizing the process. In this Ansible task, we are focused on setting the correct permissions for the home directory of our WordPress installation. Proper directory permissions are essential for maintaining the security and functionality of the website. By ensuring that the right permissions are in place, we can avoid potential issues that may arise during the operational phase of the website. The task utilizes the File module, a powerful tool in Ansible for managing file and directory attributes, including permissions. Here, we specify the path to the home directory using the placeholder WordPress system.home, which dynamically references the appropriate directory for our WordPress setup. The mode is set to 07v5, a commonly used permission setting that allows the owner to read, write, and execute, while granting read and execute permissions to the group and others. Moreover, this task is conditional, executing only if the variable wp install.stat.exists evaluates to false. This condition ensures that we only attempt to set permissions when WordPress has not yet been installed, thus avoiding conflicts and ensuring a smooth installation process. In summary, this task is a vital step in preparing our server environment for a secure and operational WordPress site. The first part of the code checks whether the wp-config.php file already exists in the specified WordPress directory. This is done using the Ansible stat module, which retrieves the status of the specified file and registers the result in a variable called wp-configured. If the file is present, that means WordPress has already been configured, and we can proceed accordingly. In the next segment, we sort out the fundamental WordPress configuration if the wp-config.php file does not exist. The Ansible command module is used here to run a command line instruction that invokes the WordPress CLI, WP CLI. This command configures the WordPress installation by setting parameters such as the database host, database name, user, and password, which are pulled from predefined variables. The args section indicates the directory where this command should execute, ensuring that it runs within the correct context. Additionally, it uses become user to execute the command as the specified WordPress user and includes a conditional statement that only allows this operation if the wp-config.php file is absent, ensuring that the setup process is both efficient and logical. In this section of the tutorial, we are verifying whether WordPress has already been installed on the server. The task is defined under the name "Do we need to install WordPress?" and utilizes the Ansible command module to perform the check. The command executed is wp-cli.path core is installed, which calls the WordPress command line interface, wp-cli, to determine if the core files of WordPress are present and configured correctly. To ensure that this command runs in the appropriate context, we specify the c8dir argument, which points to the directory defined by wordpresssystem.home. This directs Ansible to change into the WordPress installation's home directory before executing the command. Additionally, we indicate that the command should be executed as a specific user by using the become_user directive, which references wordpresssystem.user. A crucial aspect of this check is the ignore errors true setting. This indicates that if WordPress is not yet installed, the command will fail without halting the entire Playbook execution. Instead, we can capture this error and use it as a trigger to proceed with the installation of WordPress, allowing for a seamless setup process. The result of the command is registered in the variable wp-installed, making it available for further processing in the Playbook. The provided code snippet is an Ansible task designed to install WordPress when it is not already present on the server. The task begins by invoking the Ansible command module, which allows the execution of arbitrary commands on the target machine. It utilizes the WordPress command line interface, CLI, to perform the installation, passing various parameters that have been predefined in earlier parts of the Playbook. Key parameters include the domain of the WordPress site, the title, and the administrative credentials. Using placeholders like wordpress.domain, the script dynamically incorporates the values set elsewhere in the Ansible Playbook, ensuring a flexible and reusable approach. The command also specifies the administrative user's username, password, and email, which are essential for the WordPress setup. The task is executed within a specified directory, indicated by the cdir argument, which is crucial to ensure that WordPress installs correctly in the right environment. Furthermore, it runs as a designated user through the become user directive, enhancing security by avoiding the use of the root account. Finally, this installation task is conditionally executed based on the result of a prior check, ensuring it only runs if WordPress is not already installed. The provided code snippet performs a crucial task in managing plugins for a WordPress installation. It begins by checking whether each plugin in the specified list is already installed. This is achieved using the ansible.builtin.command module, which runs the command line instruction to verify the installation status of each plugin listed in the wordpress.plugins variable. To execute the command, it changes the working directory to the WordPress home directory, ensuring that the command is run in the correct context. The script uses the variable wp-cli.path to reference the WordPress command line interface, followed by the command plugin is installed item, where item represents each plugin being evaluated in the loop. The with items directive iterates through the list of plugins, and any errors encountered during execution are ignored thanks to the Ignore Errors option. The result of each command is captured in the WP plugin installed variable, which can be further utilized to determine the next steps based on the status of each plugin, allowing for efficient management of plugins in the WordPress environment. In this code snippet, we focus on the dynamic installation and activation of plugins for a WordPress site using Ansible. The task is designed to check if specific plugins are missing and to install and activate them accordingly. Each entry in the plugins list is processed in a loop, courtesy of the with items directive, ensuring that every plugin is accounted for. The command executed is a call to the WordPress command line interface, WP-CLI, using the ansible.builtin.command module. This command attempts to install each specified plugin and immediately activate it. The chdir argument ensures that the command is run in the WordPress home directory, while the become user and become directives allow the task to run with elevated privileges under the specified user, which is crucial for making changes to the WordPress installation. The conditional statement, when, not WP plugin installed skip, acts as a safeguard, skipping the installation if the specified condition is met. In summary, this task streamlines the plugin management process, automating both the installation and activation phases efficiently. Now let's look at the figure displayed on your screen. This image showcases the login interface for a newly installed WordPress site. In the center, you can see fields designated for entering your username or email address and password. The default username is set to Ansible, which aligns with the automation we've implemented through the Ansible Playbook. Notice the prominent WordPress logo at the top, indicating the platform you're working with. To the right of the password field, there's an eye icon that can be used to reveal the password. This is a handy feature for ensuring you've entered it correctly before logging in. Below the login fields, there are additional options. If you happen to forget your password, a prompt is provided for assistance. There's also a checkbox labeled Remember Me, which, if selected, allows the browser to keep you signed in for future visits. Lastly, a link directs you back to the main WordPress page, confirming that this installation is running on Ubuntu 22.04. This figure encapsulates the straightforwardness of accessing your newly automated WordPress site. With your username and password at hand, you're ready to dive into managing your stunning new website. So far, throughout the previous chapters, we have been targeting a single operating system, Ubuntu, when running on our playbooks. As we journey into the topic of multiple distributions, we are set to expand our horizons. Now, what does it mean to target multiple Linux distributions? In simple terms, it involves crafting our playbooks and roles so that they can operate seamlessly across different types of Linux environments, notably those based on different package management systems and directory structures. Today, we'll delve deep into this intriguing world, and I promise to keep it both educational and engaging. Let's kick things off by appreciating the beautiful variety in the Linux landscape. When we discuss multiple distributions, we're primarily focusing on those derived from two major family lines, Debian and Red Hat. Each of these families host various distributions like Ubuntu, which springs from Debian, and Rocky Linux, a prominent descendant of Red Hat. So why is this lineage important as we work with playbooks? Well, the commands, structure, and even package management tools can differ significantly between these families. Debian-based systems generally use the Advanced Package Tool, or APT, while Red Hat-based systems deploy the RPM Package Manager and utilize tools like Yum or DNF. It's a bit like speaking different dialects. The core language is the same, but the choice of words can lead to confusion if you're not familiar with the variations. Embarking on this journey requires us to revisit our playbooks designed for WordPress installations. In our previous chapters, we've meticulously crafted our playbooks for Ubuntu, ensuring each command worked flawlessly with APT. However, as we move into the realm of multiple distributions, we'll need to adapt our code to accommodate Ubuntu and Rocky Linux. Fun fact, just like how some people refuse to eat pineapples on pizza, those in the Linux community can get quite passionate about their preferred distributions. But that's a story for another time. In the provided code snippets, we see how to install Nginx on different Linux distributions using Ansible, which is an automation tool designed for configuration management and application deployment. The first snippet specifically targets Debian-based systems, such as Ubuntu. Here, the apt module is utilized to manage packages. The code instructs Ansible to install Nginx and ensure it is at its latest version. The key condition for executing this task is checked with the when clause, which verifies that the operating system family is identified as Debian. The second snippet addresses Red Hat-based systems, exemplified by Rocky Linux. Instead of the apt module, it employs the DNF module for package management. Similar to the first snippet, this code also aims to install Nginx and ensures it is at the latest version. The task execution is contingent upon the check that the operating system family is Red Hat. By using these conditionals, the playbook effectively adapts to the underlying operating system, allowing seamless package installation across multiple distributions. The provided code snippet demonstrates how to dynamically include variable files in an Ansible playbook based on the detected operating system. By utilizing the ansible.builtin.includeVars module, the playbook attempts to load a specific YAML file that correlates with the operating system family being targeted. The placeholder Ansible core OS family is replaced at runtime with the appropriate operating system identifier, such as Debian, for Debian-based systems, or Red Hat for Red Hat distributions. This approach allows for a modular and clean configuration, separating the variable declarations according to different operating systems. Each system can have its own dedicated YAML file that contains relevant variables, such as package names or configuration settings tailored to that OS. Consequently, this makes it easy to maintain your playbook, as it can adjust its behavior based on the environment it's running in, without hard-coding values into the playbook itself. Overall, this method promotes reusability and organization, streamlining the management of diverse infrastructure with varying requirements. Now, let's transition from understanding to practical application. Once we gather our facts about the systems we are targeting, we can leverage these facts as conditions within our tasks. Ansible gathers system information when it connects to a host, supplying details like Ansible distribution, Ansible version, and most importantly for us, Ansible OS family. You might be asking why this knowledge is crucial. It allows us to tailor our commands perfectly for the environment at hand. For example, during a recent Playbook execution, we had to ensure that certain updates applied to Rocky Linux, but not to our Debian instance. By checking if Ansible OS family was Red Hat, Ansible can gracefully skip over tasks not applicable to that environment without causing errors or interruptions. Picture this as making sure each guest at a dinner party gets their dietary preferences catered to. It all comes down to careful consideration. In this snippet of Ansible playbook code, we are setting a dynamic variable that determines the correct path for the php-fpm configuration file based on the operating system in use. The command begins with a task named set the php-fpm config path. This serves as a clear label for what the action is doing, helping anyone reading the playbook understand its purpose. The setFact module is employed to create a new variable called php-fpm path. This variable will hold the appropriate configuration file path depending on whether the system is a Red Hat or Debian-based distribution. The conditional expression within the double curly braces evaluates the Ansible OS family fact, which Ansible retrieves from the managed node. If the operating system is categorized as Red Hat, it assigns the Red Hat path etc.fpm.wwconf to hp-fpm path. Conversely, for a Debian system, it defaults to the Debian-specific path /php@wm-fpool.bo.conf. By utilizing this approach, the playbook becomes more flexible and resilient, ensuring that it accommodates various system configurations without manual adjustments. In this code snippet, we are managing the firewall configuration specifically for Red Hat-based systems using Ansible. The task is structured to execute a series of commands through the command module. The key action here is to run firewall cman commands only if the firewall service is actively running. The check for the firewall's status is performed by inspecting the output of the firewall cmdat state command, which is captured in the variable firewall status. The with items directive allows us to iterate over a list called firewall commands, which contains the actual firewall commands that need to be applied. This approach not only simplifies the execution of multiple commands, but also maintains clarity and ease of management. Additionally, the when condition ensures that the commands will only execute if certain criteria are met. The firewall must be operational, the operating system family must be recognized as Red Hat, and there must be no pre-existing firewall configuration indicated by the absence of the firewall configured.stat.exists file. This conditional execution is crucial in ensuring that the firewall is set up securely and without existing conflicts. In this inventory file, we define a group called web servers that will help manage our server infrastructure more effectively. Each entry under this group designates a specific machine that Ansible will interact with. The first line, web servers, identifies the group name, which serves as a container for all servers listed under it. Following the group name, we have two host entries. The first entry, Ubuntu Ansible host equals 192.168.1.10, indicates that we have an Ubuntu server with the IP address 192.168.1.10. This line allows Ansible to connect to that server using the provided IP. The second entry, Rocky Ansible host equals 192.168.1.11, similarly describes a Rocky Linux server located at 192.168.1.11. By organizing our servers in this way, we can easily target all machines within the web servers group when executing commands or playbooks. This not only streamlines workflow, but ensures that all servers receive consistent configurations and updates, effectively orchestrating operations across different distributions within our infrastructure. Now let's look at the figure. This snippet captures terminal outputs showcasing the use of Ansible commands to check the operating system family of different hosts. The first command in the figure highlights how to retrieve the OS family for a host categorized under Red Hat. Here, the command uses the setup module combined with a grep filter to extract the Ansible OS family variable. The output confirms that this host indeed belongs to the Red Hat family, illustrating how specific commands yield pertinent details about the environment. Shifting attention to the next command, we see a similar approach applied to a different host, this time labeled as Debian. Again, the setup module is employed, followed by a grep to filter the same Ansible OS family variable. This time, the output reflects that the system is part of the Debian family. This clearly demonstrates how adaptable our playbooks need to be, serving multiple distributions without compromising efficiency or clarity. This figure effectively embodies the essence of systems management across varied operating systems. It emphasizes the importance of tailoring automation based on the underlying OS structure. By understanding the responses from these commands, we foster an environment that respects the unique methodologies required for each system type. Through this figure, we gain valuable insights, reinforcing the necessity of flexibility in our automation strategies. Adapting playbooks for distribution differences is a crucial aspect in the world of IT automation, particularly when dealing with configuration management tools like Ansible. In this script, we will dive deep into the methodology and best practices for adapting our playbooks to cater to different operating systems, particularly when we're working with distributions that are either Debian-based or Red Hat-based, like Ubuntu and Rocky Linux, respectively. Buckle up, because we're about to explore this exciting realm with a smidgen of humor and a lot of information. Let's start with a fundamental question. How do we build the logic into our roles to execute only certain parts of them on different operating systems? Picture this. You're a cook in a multicultural kitchen, and while you have a fantastic recipe for lasagna, guess what? You need to adjust it based on whether you're cooking for someone from Italy or another country where tomato sauce is viewed with skepticism. It's essentially the same concept. This adaptation process is vital because not all operating systems share the same package management systems, commands, or even file paths. The primary step is determining the operating system family, which we can ascertain through the Ansible OS family fact that Ansible collects via its setup module. This fact helps us create a tailored experience. For example, we have two hosts, one running Ubuntu 22.04 and another running Rocky Linux 9. We can identify their operating system families by executing the Ansible Ansible built-in.setup command, followed by grepping the Ansible OS score family. Ansible-I hosts Red Hat Ansible.builtin.setup, grep Ansible OS family. Ansible-I hosts Debian Ansible.builtin.setup, grep Ansible OS family. Running these commands should return the respective families for Ubuntu and Rocky Linux, which are Debian and Red Hat. With this critical observation under our belts, we can then branch into specific tasks for each operating system, ensuring that the right operations take place on the right distributions. This script outlines how to install WordPress packages on different Linux distributions using Ansible, a powerful automation tool. The play begins by defining the target hosts in the inventory file and specifying tasks to be executed based on the operating system family detected by Ansible. The first task is aimed at Debian-based systems, utilizing the apt module to install essential packages such as MySQL Server, PHP, and Nginx. A loop structure allows for efficient processing of multiple items, ensuring all necessary components are installed simultaneously. The conditional when statement ensures this task is only executed if the detected operating system family is Debian. Conversely, for Red Hat-based systems, the script employs the DNF module for package installation. Similar to the previous task, it also utilizes a loop for the same set of packages. The when condition is crucial here, as it checks if the operating system family is Red Hat before proceeding with these installations. By incorporating these conditional statements, the Playbook efficiently manages package installation tailored to different environments. In this section, we address the need to manage configuration files that vary between different operating systems, particularly focusing on the paths for MySQL socket files. To ensure our playbook remains adaptable, we introduce the inclusion of OS-specific variable files based on the detected operating system. This is achieved by using the include vars module, which dynamically incorporates the appropriate variable file corresponding to the system's family, such as Debian or Red Hat. Next, we define two separate YAML files, debian.yml and redhat.yml, housed within the vars directory of our Ansible role. In the debian.yml file, we specify the MySQL socket path as varsmysqld.sock and set the PHP service name to php 8.1-fpm. Conversely, the redhat.yml file defines the socket path as var libmysql.sock and sets the PHP service to php-fpm. This organizational structure not only streamlines the reference to these variables, but also minimizes potential conflicts that could arise from using hard-coded values, enhancing the maintainability of our configuration system. The provided code snippet is an Ansible task that checks whether the firewalled service is running on a Red Hat-based system. It begins with the task name, check if firewalled is running, which succinctly describes the purpose of the command that follows. The actual command executed is firewall cman-state, which queries the current state of the firewalled service. This is crucial because understanding the firewall status is a prerequisite before making any configurations to firewall rules. If firewall D is not active, any rules added would be ineffective. The result of the command is captured and stored in a variable called firewall status. This variable can later be used in the playbook to make decisions based on whether the service is running or not. Lastly, the task includes a conditional statement, when Ansible OS family = Red Hat, ensuring that this check is only performed on systems belonging to the Red Hat family. This targeted execution prevents unnecessary errors or attempts to manage the firewall on incompatible operating systems. Overall, this code effectively helps in establishing a proper security configuration by first verifying the firewall's operational status. To begin executing our tasks, we use the command to run the Ansible playbook specified in our inventory file. The command ansible-playbook I hosts site.yml indicates that we are utilizing the playbook defined in site.yml and targeting the hosts listed in the hosts inventory file. This command initiates the automation process where Ansible communicates with the specified systems to perform the defined tasks. As the playbook runs, Ansible gathers pertinent information, referred to as facts, about each target host. This intelligence allows Ansible to determine which tasks are applicable based on the operating system and configuration of each host. For instance, During the execution, we observe an output that indicates a successful update of packages on the Red Hat system, while the Debian system is appropriately skipped. The line changed Red Hat confirms that the task was executed, while skipping Debian denotes that Ansible intelligently bypassed running the task that was not relevant for that particular host. This selective execution exemplifies Ansible's efficiency and versatility in managing multiple distributions seamlessly. Now, let's ponder for a moment the importance of this conditional logic. By ensuring our playbooks are adaptable, we not only increase the efficiency of our deployment process, but also maintain the integrity of our systems. After all, nothing goes better with a well-running server than troubleshooting it before you even start. Humor aside, this adaptability is key to ensuring a smoother flow in managing diverse environments. The crux of adapting your playbooks for distribution differences lies in understanding the foundational aspects of your target operating systems and implementing logic that aligns with these differences. In summary, we explored how to identify different operating systems within our infrastructure using Ansible's built-in facts, how to separate our tasks based on those differences, how to structure our variables according to each distribution, and how to validate conditions before executing tasks. As you embark on your journey with Ansible and beyond, remember the parallels of cooking in a multicultural kitchen. Every dish might have its variations, but the core ingredients, automation, adaptability, and accuracy, remain the same. So, next time you fire up your Ansible playbook, take a moment to appreciate not just the output, but the logic, the adaptations, and yes, the reusability of your code that is making it all possible. Until next time, keep adapting and automating. In this chapter, we will explore the fascinating world of Ansible in the context of managing Windows-based servers. Picture this. You come from a predominantly Mac OS and Linux background, and suddenly, you're tasked with managing a Windows server using a tool that, let's be honest, isn't natively built for Windows. It might strike you as a tad peculiar, but fear not. By the time we wrap up, you'll see how seamlessly Ansible integrates with Windows servers, making it feel just as intuitive as working on a Linux box. Ansible offers an ever-growing collection of built-in modules designed to interact neatly with Windows. This means you can automate tasks, create users, install packages, and so much more, all from a lightweight command line interface. Why do I say this? Well, it's simple. Ansible was born out of a need for a straightforward automation tool that's both powerful and light on system resources. It manages servers using SSH or Windows Remote Management, WinRM, and makes orchestration a breeze, allowing for efficient management in mixed OS environments. Now let's look at the figure. This diagram illustrates the architecture of a Windows Server instance set up in Microsoft Azure. At the center, we have the virtual machine, which is the core element representing the server that you will be operating. This virtual machine is connected to several essential components necessary for its functionality. To the left, we see the disk, which is crucial for storage. This disk holds the operating system, as well as any applications and data you might need. It's essential for maintaining the integrity and availability of your server and ensures that all your data is stored securely. Moving to the right, we have the network interface. This component plays a pivotal role in connecting the virtual machine to the Azure network, allowing for communication with other resources and the internet. The network interface is instrumental in managing the data traffic going in and out of your virtual machine. Below the virtual machine, there are two important elements: the network security group and the virtual network. The network security group is important for managing security by defining rules that control inbound and outbound traffic to the virtual machine. This helps safeguard your server against unauthorized access while ensuring legitimate traffic can flow smoothly. Meanwhile, the virtual network provides a private network where your server resides, enabling secure communication between Azure resources. Lastly, we see the public IP address, which serves as the address that external services and users will use to access your virtual machine over the internet. This is critical for functionalities such as remote access to the server and hosting applications or services that need to be accessible globally. This figure encapsulates the primary architecture for deploying a Windows server in Azure, highlighting the essential components and their interconnections within the Azure ecosystem. To begin, the first line of code is designed to fetch your public IP address. By using the command curl https://apiip.org, the script sends a request to the API, which returns your public IP as a response. This value is then stored in a variable named myIP, allowing you to easily access your IP later in the script or for logging purposes. Next, the script generates a secure, random password for your Azure Virtual Machine VM. The command opensSL rand-base6424 creates a 24-character password that is both random and encoded in base64, making it suitable for use as a secure password. This generated password is assigned to the variable VM password. The final part of the script writes the generated VM password into a file named VM password using the command echo VM password. This file serves as an important reference for your host inventory, ensuring that you have easy access to the password you need to log into your Azure VM, much like having all your ingredients ready before you start cooking. This process emphasizes the importance of preparation when setting up your virtual environment. To create a logical container for our Azure resources, we start by executing the command to create an Azure resource group. By running the command with the specified name rg Ansible Windows UKS and location UK South, we establish a dedicated space that will house all related resources. Next, we need to set up a virtual network, VNet, that ensures our virtual machines, VMs, can communicate effectively with one another and access the internet securely. Using the command for VNet creation, we specify the resource group we just created, assign a name to our VNet, and define an address space of 10.0.0.024, which allocates a range of IP addresses. Additionally, we create a subnet named subVMS within this VNet, with a prefix of 10.0.027, allowing for a more organized network structure where our VMs will operate efficiently. This approach establishes a safe compartment for our VMs, and next we will work on creating a network security group to manage incoming and outgoing traffic, ensuring our network remains secure and functional. In this section, we will create a Windows Server Virtual Machine VM using the Azure CLI. The command begins with azvm create, which initiates the VM creation process within a specified resource group, in this case, rg Ansible Windows-Server UKS. Here, we provide a unique name for the VM as VM Ansible Windows Server UKS, along with a computer name, Ansible Windows, that serves as the internal identifier for the VM. One crucial aspect of this command is the specification of the image with the -image parameter, where we've chosen Win 2022 Data Center. This selection is akin to selecting a desired flavor when ordering ice cream, as it determines the operating system that will run on the VM. Additionally, administrative access is established through the -admin username and admin password parameters, allowing us to manage the VM later. The command also includes network configuration, using -vnet name to specify the virtual network and -subnet to define which subnet the VM will reside in. Lastly, we ensure a stable internet connection via static public IP by setting public IP SKU to standard and public IP address allocation to static. This comprehensive command effectively sets up our Windows Server VM in the Azure environment. To enable communication between Ansible and your Windows VM, you need to set up the Windows Remote Management (WinRM) protocol. The command you've entered is an Azure CLI command that applies a custom script extension to your VM. This extension will help automate the installation and configuration of WinRM on your instance. In this command, you specify the resource group and VM name where you want to apply the extension. The #name option sets the name of the extension to Custom Script Extension, which is specifically used for managing scripts. -publisher and @version specify the source and version of this extension, ensuring you're using a supported and stable release. Moving to the settings, the file URLs parameter points to a PowerShell script located in a GitHub repository. This script is designed to configure WinRM appropriately for Ansible to communicate with the Windows VM seamlessly. The command to execute parameter runs the script with unrestricted execution policy, allowing it to perform all necessary configuration tasks without being blocked by security constraints. This setup simplifies the process, taking the burden off your shoulders, allowing you to focus on your Ansible playbooks. To interact with your Windows server using Ansible, you can leverage the power of its modules to perform various tasks. In this scenario, we are using the WinPing module, which is specifically designed for Windows environments. The command you see is structured to facilitate a simple connectivity test between your Ansible control node and the Windows server, confirming that the server is reachable and properly configured for communication. The command starts with Ansible, which is the main invocation for running a command against managed hosts. Following this is the identifier for your target machine, in this case Windows Server. The MACI hosts option specifies the inventory file where you've defined your server's details. Lastly, the -m ansible.windows WinPing portion indicates the module being used, in this case WinPing, to execute the ping test. Once executed, if your environment is configured accurately, you should receive a Pong response, confirming that Ansible has successfully communicated with the Windows server, indicating that everything is functioning as intended. This establishes a solid foundation for proceeding with more complex automated tasks. In this section, we will enable Internet Information Services, IIS, on our Windows server using Ansible. The first line of the code specifies the task's name as Enable IIS, providing clarity on the action being executed. The Ansible module, Ansible@windows.win feature, is then used to manage Windows features. Within this module, the name parameter lists the features we want to install. The first item, Web Server, represents the core IIS feature, while Web Common HTTP includes essential HTTP functionalities that are often required for web applications. By specifying these features, we inform Ansible precisely what needs to be installed. The state parameter is set to present, which indicates that the specified features should be ensured to be installed on the system. If they are not already present, Ansible will add them. This approach encapsulates how automation with Ansible allows for seamless management of Windows services, streamlining the setup of web hosting environments while minimizing manual intervention. The code here exemplifies the simplicity and effectiveness of using Playbooks to configure server environments consistently. In this section, we focus on creating an HTML file using a Jinja2 template in an Ansible playbook. The task specifically named Create an HTML file from a template employs the Ansible.windows.win template module, which is designed for Windows environments. This module takes a source template file, in this case index.html.j2, and applies it to generate a destination file. The destination file, cnetpub.www.root ansible.html, is where the rendered HTML will be saved, making it accessible through the web server set up on the IIS. Using a Jinja2 template enables dynamic content generation by integrating variables directly into the HTML file. This capability showcases the power of Ansible, allowing you to customize your web content effortlessly. By simply adjusting the variables within the template, you can produce different outputs without manually editing the HTML, reinforcing the efficiency and flexibility of automation in managing web server configurations. Ultimately, this task ensures that our web server can serve customized content as intended, verifying that the entire setup functions correctly. In this playbook snippet, we define a task that leverages the Chocolatey package manager to install software on a Windows machine. The task is titled Install Software Using Chocolatey, and it uses the WinChocolatey module from the Chocolatey collection, which is specifically designed for managing software packages on Windows through Ansible. The primary action being performed here is the installation of Notepad++, a popular text editor, represented by the package name notepad++.install. By specifying the state as present, we instruct Ansible to ensure that Notepad++ is installed on the system. If the application is already present, the task will confirm that the desired state is met without any further action required, making it efficient. This approach allows for a seamless management of software installations directly from the playbook, without the need for manual interaction with Windows interfaces. The beauty of this task lies in its simplicity and effectiveness, as it exemplifies how familiar tools in the Linux world, like package managers, can be harnessed to streamline processes in the Windows environment. In closing, as we reflect on our journey through this chapter, we've learned the best practices for managing Windows servers with Ansible. It might have felt a little peculiar at first, but hopefully, you've started to see the valuable potential that exists when wielding Ansible for Windows tasks. The process remains mostly the same, familiar structures and modules that leave room for creativity and efficiency. As we look forward to the next chapter, where we will dive into networking modules available in Ansible, remember, the world of automation knows no boundaries, and with the right tools, you can make magic happen even in the most unexpected environments. The playbook for running Ansible on a Windows server requires a slightly different approach than we typically use for Linux. As we dive into our subject, let's consider the nuances of configuring Ansible for Windows and how it affects our playbook, particularly focusing on the parameters and roles we need for a successful execution. Understanding why the file site.yml omits certain settings at the beginning can set the stage for our understanding of how Ansible interacts with Windows. When targeting a Windows host, you often notice that you don't need configurations that apply to Linux hosts. For example, you don't need to specify the become or become method keys, mainly because Windows operates differently than Linux. This fact opens the door for a more seamless integration process when managing Windows servers. The opening part of our site.yml showcases a structure that determines the task being executed. The YAML file begins with a declaration of the playbook, identified by the series of dashes. The playbook is named installing.net, create user, install chocolatey, and display info, highlighting the objectives of this automation task. It specifies the hosts on which the operations will run, designated as Ansible hosts. Additionally, it is set to gather facts about the system, providing valuable information about the target environment before executing any tasks. The vars files section indicates that variables from group vars common.yml will be used throughout the playbook, enabling dynamic configuration based on the inventory group. Central to this playbook are the roles, which encapsulate distinct functionalities needed for the setup. In this instance, the roles listed, IIS.NET, User, Choco, and Info, each manage specific components of the Windows server. This structured approach allows for clean, modular scripting, transforming complex operations into easily manageable tasks, reflective of the best practices in infrastructure management. To execute the Ansible playbook, you would use the command ansible-playbook-i hosts site.yml. This command is structured to ensure that Ansible knows what inventory to utilize and which playbook to run. The -i hosts option specifies the inventory file named hosts, which outlines the target server hosts where the tasks will be executed as defined in site.yml. When you hit enter to run this command, Ansible begins its execution by reading through the site.yml playbook file. Playbooks in Ansible act as blueprints for what needs to be orchestrated on those servers. Think of it as script for a theatrical performance, where each role corresponds to a specific part or stage in the deployment process. As the playbook runs, Ansible will call upon the roles defined within the file, processing each step sequentially. This process provides immediate feedback on the actions being taken, much like a chef showcasing their culinary skills. The output shows how components are installed, configured, and validated, creating a sense of real-time engagement and clarity throughout the orchestration lifecycle. In this code snippet, we are using the Ansible module ansible.windows.win feature to enable the Internet Information Services IIS role on a Windows server. The task is named Enable IIS, providing clarity about its purpose. This is an essential step for setting up a web server using Windows because IIS is a required feature for hosting websites. The name parameter specifies which features to enable. In this example, we are enabling two features, Web Server, which is the core functionality of IIS, and Web Common HTTP, which provides support for HTTP functionalities. Specifying these features ensures that the web server has all the necessary components to run effectively. Finally, the state parameter is set to present, indicating that these features should be installed if they are not already present on the system. This approach automates the configuration process, removing the need for manual intervention through the Windows user interface. By using Ansible, system administrators can streamline the deployment and management of web servers, making the entire process significantly more efficient and manageable. In this section, we focus on enabling the .NET framework on our server, which is essential for running many web applications effectively. The first line indicates the task's name, enable.net, providing clarity on what this part of the script accomplishes. The subsequent instructions utilize the Ansible module specifically designed for Windows, ansible.windows.win feature, to manage Windows features on our server. The name parameter lists the specific .NET features we want to install, including Net Framework features, Web ASP.NET 45, and WebNet XT45. By specifying the state as present, we ensure that these features are installed and active. This is crucial for supporting ASP.NET applications and allowing them to function correctly on the server. Finally, the script includes a notification to restart IIS. This step is vital, as it prompts the Internet Information Services (IIS) server to restart, thereby applying any configuration changes made during this process. This approach not only simplifies deployment but also enhances system reliability, ensuring that our web applications perform as intended without any hitches. In this code snippet, we are using Ansible to manage user accounts on a Windows system. The task is defined with a name, ensure that the Ansible created users are present, making it clear that the primary objective is to create or ensure the existence of specified user accounts. The module ansible.windows.winUser is employed to handle user management. The key parameters include name, which is assigned the value of the variable ansible.username. This variable allows for flexibility, as it can be adjusted according to the specific user you wish to create or manage. Next, the full name parameter takes the same username but transforms it by capitalizing the first letter. This is a good practice for user account management as it enhances readability. The password parameter utilizes the variable ansible.password, ensuring that any password complexity requirements can be easily addressed across different environments by simply updating this variable. Finally, the state parameter is set to present, which indicates that the user must exist. Additionally, users can be assigned to specific groups through the groups parameter, ensuring that they have the appropriate permissions relevant to their roles. This approach adheres to best practices in security and user management. In this code snippet, we are utilizing the Chocolatey Package Manager to install software on a Windows machine. The task is labeled Install Software Using Chocolatey, which serves as a clear indication of its purpose. The code leverages the WinChocolatey module provided by the Chocolatey Ansible collection. This module allows for seamless integration of Chocolatey into our Ansible Playbook, enabling efficient software management. The key parameter in this task is name, where we see apps used as a variable. This notation signifies that we have defined a list of software packages elsewhere in our playbook, which will be dynamically substituted at runtime. This approach promotes flexibility, allowing users to specify multiple applications without altering the core task structure. By setting the state parameter to present, we ensure that the specified applications will be installed on the target machine if they are not already present. This desirable configuration not only simplifies the installation process, but also guarantees that the software environment remains consistent, adhering to the desired state defined in our playbook. Now that we've harnessed various roles to sculpt our playbook, and we've seen how the playbook operates against a Windows machine, remember to honor the underlying principles of automation and orchestration. Following these principles, one can create repeatable and reliable deployments as a core skill in today's tech landscape. As we wrap up today's session, think about how all these pieces come together. With a little humor added during our coding ventures, remember, if coding were easy, everyone would do it. By embracing Ansible's robust infrastructure automation capabilities, we can efficiently manage our Windows environments and guarantee our workloads are not only prepared, but also sustainable. Now, go forth and deploy. Before we close, don't forget to explore the plethora of resources available for further learning. Ansible's documentation is incredibly comprehensive, and communities abound where you can learn, share, and query the collective knowledge of fellow DevOps enthusiasts. It's been a pleasure guiding you through the ins and outs of running an Ansible playbook on a Windows server. Until next time, happy automating. Welcome to Chapter 8. Today we're diving into an often overlooked use case for Ansible and exploring its expansive community of networking modules. It's like finding a hidden gem in a treasure chest overflowing with tools. If you've ever found yourself scratching your head, pondering how to manage your network devices more efficiently or automate processes in networking, then you're in the right place. Let's first acknowledge that networking is the backbone of any IT infrastructure. It's where all the magic happens, transferring data, connecting users, and enabling communications. However, managing and configuring network devices can often feel like an uphill battle. That's where Ansible comes into play with its comprehensive suite of networking modules that make these tasks effortless and organized. Now let's look at the figure, which illustrates the architecture of Ansible. At the center, we have the Ansible management node, which serves as the core component for managing network devices. This node sends commands and configurations to various hosts, making it the control point of the entire process. The management node communicates with hosts using SSH, as indicated by the connections depicted in the diagram. This SSH protocol ensures secure communication between the Ansible management node and each target host. Notice that the hosts are categorized into groups, such as Group A and Group B, represented clearly in the inventory section at the bottom of the figure. This organization helps streamline management by allowing batch operations on multiple devices simultaneously. Moving to the left side of the figure, we see two essential components, the Playbook and the inventory. The Playbook is where the instructions for automation are defined. It contains the tasks that Ansible will execute on the targeted hosts. The inventory, on the other hand, specifies the devices that will be managed, listing hosts under their respective groups. This clear delineation of playbooks and inventory allows for effective orchestration and management of diverse network devices, ultimately enhancing operational efficiency and reducing the risk of errors. The streamlined flow depicted in this figure highlights how Ansible revolutionizes network management by utilizing a unified approach. Instead of dealing with the complexities of various command line tools, users can leverage the power of Ansible to manage multiple devices efficiently. This reduces the overhead of switching interfaces and allows for a more consistent and reliable configuration process. In this Ansible playbook, we begin by defining a task titled Gather Facts from Cisco iOS Device. The playbook targets a group of hosts classified as Cisco, indicating that the Ansible commands will be executed on devices running Cisco iOS. The Gather Facts No directive signifies that we do not want to collect default system facts from the hosts, which streamlines our execution time and focuses solely on the tasks we intend to perform. Within the task section, there is a single task named Gather Device Facts. This task utilizes the iOS Facts Ansible module, specifically designed for Cisco devices. By invoking this module, we can extract detailed information about the current state and configuration of the targeted network device. This information can include interface statuses, device model, and configured protocols, among other data. Utilizing the iOS Facts module is particularly beneficial for network auditing and compliance, as it enables network administrators to collect and maintain a comprehensive catalog of device configurations with minimal manual effort. Now you might be wondering, what types of devices can I manage with Ansible? Well, let's dig deeper into some of the most prominent collections offered. The Ansible community has put together a vast array of collections that encompass support for many different vendors. For example, let's talk about Arista's Extensible Operating System, EOS. The collection named arista.eos provides over 30 modules. With these modules, not only can you manage access control lists and BGP settings, but you can also gather facts and execute arbitrary commands on your devices. Imagine having the power to configure virtually every facet of your network fabric with just a few lines of code. Moving on, we encounter Checkpoint's modules, which are associated with over 250 commands for managing firewalls using the Web Services API. Now, I know what you're thinking, but how can we keep track of all these modules? Fear not, the Ansible documentation does a stellar job of maintaining an index for these collections. So anytime you need to refresh your memory on a module's capabilities, you can go right into the documentation. In the provided playbook snippet, we focus on configuring access lists on a Cisco router using Ansible. The playbook begins with a name that describes its purpose: configure access lists on Cisco router. This gives a clear indication of what the tasks will involve. The hosts directive specifies the target devices, which are categorized under the Cisco namespace. This indicates that the tasks will be executed on devices that fall within this category, allowing for easy management of multiple Cisco devices in a single go. Within the Tasks section, we see a task named Add an Access List entry. This encapsulates the primary action we want to perform, which is to modify the router's configuration by adding an entry to an access list. The module used for this task is ioconfig, a specific Ansible module designed for Cisco iOS devices. The critical part of the configuration happens under the lines attribute, where we define the actual command to be executed. Access list 100 permit IP any. This command grants permission for all IP traffic, effectively allowing any source to communicate freely with any destination within the network constraints defined by the access list. This example showcases how Ansible streamlines the process of network configuration, ensuring consistency and reducing the potential for human error. In the context of securing your Ansible playbooks, the command Ansible vault encrypt secret file.yaml is instrumental. This command utilizes Ansible Vault, a powerful feature designed specifically to protect sensitive information integrated within your playbooks. By using this command, you can encrypt a file named secretfile.yaml, ensuring that it contains confidential data such as passwords, API keys, or SSH keys securely hidden from unauthorized access. The encryption process encapsulates the data within a secure layer, making it accessible only to individuals who have the correct password to decrypt it. This is a crucial practice in network management, as it helps you maintain the integrity and confidentiality of your critical infrastructure while still leveraging the automation capabilities of Ansible. It is vital to remember that you, as the administrator, are responsible for safeguarding the vault password to prevent unauthorized users from accessing your encrypted data. By employing Ansible Vault, you effectively add a robust layer of security to your automation strategy, allowing you to manage your infrastructure with confidence. Let's shift gears for a moment and discuss the process of using these modules in your daily tasks. When you sit down to create a playbook to automate network tasks, you can follow a structured approach. Start with building your inventory file, which lists all your network devices along with their connection details. Then, begin crafting your playbook to include tasks you wish to automate. By utilizing the Ansible.net Common Collection, you can also run general commands and even ping devices to check their availability before diving into configurations, which is quite handy during troubleshooting. In this script, we define a playbook aimed at configuring multiple devices simultaneously, which greatly enhances efficiency in network management. The playbook begins by specifying the name and the hosts it targets, in this case, all devices listed in our inventory. This broad targeting allows for a cohesive configuration process across various network devices, eliminating the need for repetitive manual interventions. The main task is described as Configure Interface, indicating that our focus is on updating network interface settings. Within the task, we employ the iOS config module, specifically designed for managing Cisco iOS devices. Here, we define the commands that will be executed on the targeted devices. The commands include setting the interface to Gigabit Ethernet 00, assigning it an IP address of 192.168.1.1 with a subnet mask of 255.255.255.0, and enabling the interface by using the no shutdown command. This level of automation not only simplifies configuration, but also ensures consistency across devices, making Ansible a valuable tool for network engineers looking to streamline their workflows and reduce operational overhead. In summary, Ansible network modules provide a robust framework for managing and automating your network infrastructure. They offer a standardized way to interact with a myriad of devices, liberating network engineers from the tedious manual processes of the past. Whether it's gathering facts, managing configurations, or executing commands, Ansible brings an organized and efficient approach to the networking field. So, whether you are a seasoned network engineer or just starting, I encourage you to dive deep into Ansible's capabilities. Play around with the modules, experiment with your playbooks, and watch as your workflow becomes smoother and your efficiency skyrockets. And there you go. That wraps up our overview of Ansible network modules, an exciting journey towards automation and efficiency in network management. Remember, every network is unique, so leverage these tools, adapt your techniques, and don't hesitate to share your discoveries in the community. The adventure has only just begun. So far, we have been looking at modules that interact with servers. But before diving into the more cloud-based environments, it's crucial that we understand manufacturer and device support. This topic is fundamental as it sets the groundwork for how we can manage various network devices with ease and efficiency using automation tools. By understanding the modules and collections we can use, we become capable of controlling complex network devices through simple, readable scripts. Imagine this. Instead of manually logging into each device and making changes, you can run an Ansible playbook that communicates with all your devices in one go. Pretty neat, right? Let's explore how these modules and collections work, the devices they support, and how we can leverage their capabilities to enhance our network management. First things first, let's discuss the types of network devices Ansible supports. The modules we've mentioned are designed to handle everything from top-of-rack switches and firewalls to load balancers and more, really giving us the ability to manage a comprehensive mix of hardware. What makes this even better is that Ansible supports an enormous range of manufacturers. We're talking about everything from open-source virtual appliances to high-end hardware solutions, some of which can cost over USD 500,000. When we think about what all these devices have in common, they interact with a core element of any IT infrastructure. They manage connectivity. Anything that connects to a network relies on these devices to work effectively. So, how do we get our hands on them without needing to be a command line ninja? Let's break down how Ansible interacts with these devices. This playbook snippet illustrates the process of enabling an interface on an Arista device using Ansible. The first line specifies the name of the play, which is simply a human-readable label for the task being performed. Here it is configure Arista device. The hosts line indicates the target group of devices, in this case, the group labeled Arista. By setting gather facts to false, we streamline the playbook by skipping the default data collection about the target devices, optimizing execution time. Within the tasks section, we define what actions will be performed on the target device. The first task is titled Configure Interface, and it utilizes the Ansible module arista.eos.eos interface. This module is specifically designed to interact with devices running Arista's EOS. The key parameters include name, which specifies the interface to be configured, in this case Ethernet 1, and enabled, which is set to true, indicating that the interface should be activated. Finally, the description parameter provides a label for this interface, while state being set to present ensures that the configuration is applied if it isn't already in place. Of course, managing network devices is not all sunshine and rainbows. One downside of using Ansible is that the host running these playbooks needs a line of sight to the management interface or API on the devices. This can bring some security concerns to the forefront. Security in networking is no joke. A misconfigured firewall can leave you vulnerable to attacks. Thus, while the convenience of managing network devices remotely is fantastic, you must thoughtfully implement your automation strategy. It's essential to ensure secure communication channels are established and access controls are strictly enforced. The provided code snippet demonstrates a simple Ansible playbook aimed at managing a Cisco iOS device. It starts with the play definition, where the play is named Manage Cisco iOS Device and specifies the target hosts under the group named Cisco. This organization allows for flexibility in targeting specific devices within your network. Within the tasks section, a single task is defined to configure an interface on the Cisco iOS device. The task is titled Configure Interface, indicating its purpose clearly. The module used here is iOS config, which is specifically designed for making configuration changes on iOS devices. The configuration commands are laid out under the lines key, where the first line adds a description to the interface, labeling it as Internet Connection. This descriptive labeling is crucial for network management and documentation. The second line assigns an IP address of 192.168.1.1 with a subnet mask of 255.255.255.0 to the interface. To ensure that these configuration changes are properly applied, the before parameter specifies that the task should be executed before applying the configuration to interface gigabit Ethernet 0/1. This methodical approach enhances clarity and control over network configurations. Each manufacturer's modules offer unique functionality tailored to their specific feature sets. For example, Fortinet's FortiManager has thousands of modules designed to cover everything from antivirus settings to internet service applications. There are over 1,100 modules at your disposal. The sheer volume allows for granular control over the devices. Similarly, if you're dealing with checkpoint devices, the collection consists of over 250 modules. Each module enables you to handle various settings from rules to administrators through the Web Services API. This flexibility means you can script bulk changes or even automate the reporting of device status. What if I told you you could automate your entire firewall configuration? Imagine running a safety check every hour, approving changes with a quick approval workflow, all via Ansible Playbooks. Now let's look at this figure, which illustrates the key components of Ansible's automation framework. At the center, we have Ansible's automation engine, a crucial element that facilitates communication and orchestration among various components. This engine is the hub that connects users and automates interactions with the network devices. To the left, we see the user component, representing the individual or team initiating the automation tasks. The user engages with Ansible primarily through the Ansible Playbook, found at the bottom of the figure. This playbook contains the directives that instruct Ansible on what tasks to perform across the network devices, effectively serving as a blueprint for automation. Moving towards the center, we see inventory, a component that stores information about the network devices. This inventory is vital as it allows Ansible to understand which devices are available for management and automation tasks. Adjacent to the inventory is the API, enabling programmatic access to Ansible. This API serves as a bridge between Ansible and other applications, facilitating seamless integration and interaction. Next, we encounter modules, which are reusable scripts that carry out specific tasks on the network devices. These modules enhance the capabilities of Ansible by providing a wide array of functions tailored for different use cases. Alongside the modules are plugins, which extend Ansible's functionality, allowing users to customize and enhance their automation workflows based on their unique requirements. On the right side of the figure, we see the hosts representing the actual network devices managed by Ansible. These are the endpoints where the automation tasks are executed. Above the hosts, we also see a reference to networking, indicating that Ansible's automation capabilities extend to various networking environments. Finally, at the top of the figure, we have the CMDB and public-private cloud components. The Configuration Management Database, CMDB, is essential for maintaining an up-to-date inventory of the IT environment, while the public and private cloud references illustrate Ansible's capability to manage infrastructure both in-house and across cloud platforms. Overall, this figure provides a clear visual representation of how Ansible orchestrates its components to achieve efficient automation across network devices. Understanding this framework will allow you to leverage Ansible effectively, minimizing configuration errors and enhancing overall productivity in your automation practices. The collections available are vast and cover an array of vendors and devices. From Huawei to Juniper, each network device manufacturer is represented with dedicated modules that extend Ansible's abilities. This gives network professionals the power to enforce policies and configurations across their environments without falling into the trap of inconsistency. In fact, if you're curious, I encourage you to explore the Ansible Collection Index online because it's continually updated with new modules and capabilities. You might find functionality that you've never even thought possible. Let's not forget about the community aspect. The Community Network Collection is like the cherry on the sundae. If there's a network device that isn't covered by one of the well-known manufacturers, This catch-all collection enables you to find a suitable module to manage it. It's a boon for any network engineer dealing with less common devices. In conclusion, having a strong grasp of manufacturer and device support within Ansible opens up a world of possibilities. Understanding how to operate various devices through straightforward playbooks allows you to simplify even the most complex network environments. As you progress in your career, harnessing these automation tools will not only make your life easier, but also revolutionize the way your organization approaches network management. So, ready to dive deeper into the world of Ansible playbooks and automate your networks? Stay tuned as we will begin discussing cloud-specific capabilities and how they can redefine your network strategies in the following chapters. In 2008, Microsoft took its first significant step into cloud computing by introducing Windows Azure, a cloud-based data center service. This launch marked a pivotal moment in what many people saw as a traditional software company's history, signaling a strategic shift toward cloud computing. Developed under the internal Project Red Dog, Windows Azure represented Microsoft's answer to the growing demand for scalable, accessible, and flexible computing resources. Microsoft Azure was initially rolled out with 5 core components, each designed to offer distinct capabilities within the cloud computing spectrum. Microsoft SQL Data Services provided a cloud version of Microsoft's SQL database, simplifying the complexities associated with hosting and managing databases in a cloud environment. Microsoft .NET Services, as a platform-as-a-service (PaaS) offering, enabled developers to deploy their .NET-based applications within a Microsoft-managed runtime, streamlining the development process. Meanwhile, Microsoft SharePoint and Microsoft Dynamics offered cloud-based versions of the company's renowned intranet and customer relationship management (CRM) products, effectively enhancing collaboration and customer engagement. At the core of the original Azure platform, Infrastructure as a Service (IaaS) provided users with the ability to create and control virtual machines, along with essential storage and networking services necessary to support diverse compute workloads. The underlying architecture of Azure was based on the Red Dog operating system, a specially modified version of Windows NT, ensuring efficient delivery of data center services. This robust foundation laid the groundwork for Azure's evolution into the comprehensive cloud platform recognized today. Fast forward to 2014, and Microsoft made a strategic decision to rebrand Windows Azure as Microsoft Azure. This renaming highlighted an expanded range of services reflecting a growing emphasis on Linux-based workloads, showcasing Microsoft's adaptive approach and commitment to open-source technologies. At this time, the platform shifted towards more inclusive offerings, allowing a broader palette of development tools that catered to diverse developer preferences and project requirements. By 2020, it was evident that Microsoft Azure had fully embraced a more inclusive approach, showcased by the fact that over half of its virtual machine cores and a significant number of Azure Marketplace images were Linux-based. This strategic pivot toward Linux demonstrated Microsoft's broader embrace of open-source technologies, positioning the company to compete effectively in a rapidly changing cloud landscape. The focus on open source was not merely a trend, but a foundational aspect of Azure's modern service offerings, reflecting a deep understanding of various organizational needs across industries. To understand how to get started with Microsoft Azure, let's take a look at the basics of establishing an Azure environment. First, you'll need an Azure account, which can be created easily through the Azure portal. Once your account is set up, navigating the Azure portal will provide you access to a wealth of resources and services, including virtual machines, databases, storage, and a range of other services. Now let's look at the figure presented. This image showcases a Microsoft Azure resource group named RG Learn Ansible WordPress Prod EUW. At the top, we can see essential details including the subscription under which the resource group resides and its associated subscription ID. Tags are also provided, indicating the project focus, environment, and deployment method, which in this case is specified as being deployed by Ansible. In the main section of the figure, a list of resources is displayed. These resources include various components essential for hosting a web application, specifically a WordPress instance. Each resource is categorized by type, highlighting their roles within the infrastructure. For instance, the load balancer is critical for distributing incoming traffic, while the network interface connects virtual machines and the public IP address facilitates external access. Additionally, the figure indicates the location of these resources, which is set to West Europe. The resources are neatly organized, allowing users to filter and manage them easily. This kind of layout emphasizes Azure's intuitive design, aimed at simplifying the management of cloud resources. Each item in the list is accompanied by a corresponding type designation, making it clear how each component contributes to the overall application architecture. As we examine the recommendations section, it suggests best practices or enhancements for the current setup. This feature underlines Azure's commitment to providing users with insights that can help optimize their deployments, further illustrating the platform's user-friendly approach. Overall, this figure encapsulates the core functionalities of Azure Resource Management, making it easier for users to navigate and utilize the platform effectively. Another critical aspect of utilizing Microsoft Azure is the concept of resource groups. Resource groups serve as a container that holds related resources for an Azure solution. They enable an organized way to manage and maintain those resources, making deployment, monitoring, and management tasks significantly easier. Grouping related resources simplifies access control, resource organization, and billing allocation for various projects within Azure. When working within Azure, understanding Azure Resource Manager, ARM, is crucial. ARM is the deployment and management service for Azure. It enables you to create, update, and delete resources in your Azure account. Additionally, it provides capabilities for managing resources through templates, which are JSON files that define the infrastructure and configuration for your project. These templates allow for infrastructure as code practices, greatly enhancing the efficiency and reliability of your deployments. The first step in provisioning a virtual machine on Microsoft Azure is to log into your Azure account using the Azure CLI. The command azlogin prompts you to authenticate and gain access to your Azure resources. Once authenticated, you can manage your resources effectively. Next, you'll create a resource group, which is a container that holds related resources for an Azure solution. This is done with the command azgroupcreate, name myResourceGroup-location Istas. Here, a new resource group named myResourceGroup is created in the Istas region, providing a structured way to organize and deploy resources. After establishing the resource group, you can proceed to create the virtual machine. The command azvmcreate initiates this process. You specify the resource group, the name of the virtual machine, myVM, and the desired operating system image, which in this case is Ubuntu LTS. The command also requires an admin username, here designated as AzureUser, and it automatically generates SSH keys for secure access to the virtual machine. This process encapsulates the simplicity and power of launching a virtual machine in Azure using the CLI. Now let's look at this figure, which illustrates the various compute options offered by Azure. In the center, we see the prominent label, Azure Compute, denoting the umbrella under which all these services are categorized. Surrounding this central element are 6 key components that highlight the diversity of computing resources available in Azure. On the top left, we have the virtual machine icon. This represents traditional computing where users can create and manage virtualized environments, providing flexibility for various applications. Next to it, on the top right, is the remote app icon, indicating a service that allows users to run Windows applications in the cloud and access them remotely, enhancing accessibility and collaboration. Moving to the bottom left, the Cloud Service component signifies Azure's Platform as a Service, PaaS, offerings, which enable developers to build and host applications without having to manage the underlying infrastructure. Below that, we see Azure Serverless Computing, which represents a scalable and event-driven computing model, allowing users to run code without provisioning servers, focusing solely on their application's functionality. On the bottom right, we encounter the Azure Batch icon, reflecting Azure's capability for large-scale parallel and high-performance computing tasks. This service efficiently manages the execution of applications across a pool of virtual machines, optimizing resource utilization. Finally, the cloud service icon ties together these compute options, illustrating how Azure provides a comprehensive suite of services tailored to varied workloads and application architectures. This figure encapsulates Azure's compute offerings, showcasing how they align with the needs of modern application development and deployment, emphasizing flexibility, scalability, and efficiency. In summary, Microsoft Azure represents a robust and flexible cloud platform that has fundamentally transformed how organizations deploy and manage their IT infrastructure. By leveraging Azure's comprehensive service offerings, businesses can enhance their operational efficiency, decrease overhead costs, and accelerate their digital transformation journey. With its continuous evolution and growing support for diverse platforms and technologies, Azure is well positioned to meet the demands of the modern cloud landscape. By the end of this introduction to Microsoft Azure, we hope you'll feel excited to explore the myriad of opportunities available, whether it's deploying new applications, enhancing existing workloads, or engaging in innovative solutions. Stay tuned as we dive deeper into more specific aspects of Azure and how you can make the most out of this powerful cloud platform. Now let's look at this figure, which outlines the comprehensive guidance available for your cloud journey using Microsoft's resources. In the center, we have a circular model representing the core components of the cloud adoption framework. This includes 6 key stages: govern, plan, define strategy, adopt, manage, and ready. Each element is interconnected, emphasizing the cyclical nature of successful cloud adoption. Surrounding the main framework, we can see the various ways to enhance your skills and optimize deployment. To the left, the icon representing Microsoft Learn highlights the importance of skill building within your team. This resource provides foundational knowledge necessary for team members to navigate cloud technologies effectively. Next, the reference architectures icon illustrates how you can accelerate your cloud deployment. These architectures serve as templates that guide you through best practices, reducing time and effort in launching your projects. By leveraging these reference points, you can achieve more structured and efficient deployments. Moving on, the figure indicates the significance of optimizing workloads through Azure well-architected methodologies. This ensures that your applications not only perform efficiently, but are also cost-effective, available, and secure. The next icon emphasizes the application of best practices to expedite onboarding processes. This element is crucial for ensuring that new team members quickly adapt and align with your cloud strategies. Finally, the figure highlights the importance of reviewing technical documentation. This ongoing process helps teams to stay informed of the latest features and updates in Azure products, ensuring that your cloud strategies remain current and effective. Together, these elements provide a roadmap for effective cloud adoption, reinforcing the notion that having a clear strategy and resource access is vital for a successful journey in the cloud. Launching a virtual machine in Microsoft Azure using Ansible is an exciting journey into the world of cloud computing. If you followed along in Chapter 7, where we explored the Ansible Windows modules, you will already have a basic understanding of launching virtual machines, VMs, using the Azure CLI. Now, let's open the door to automation with Ansible to make this process more efficient and scalable. To begin setting up our Ansible environment for Azure, the first command we need to execute is related to installing the Azure collection for Ansible. By running Ansible Galaxy collection install azure.collection, we are retrieving a collection of modules specifically designed to interact with Azure resources. This collection is essential because it includes the various tools necessary for managing Azure resources efficiently, making our automation tasks much simpler. Once the Azure collection is installed, we move on to the next command: pip3 install -stroke ansible/collections ansible collections/az collections/requirements-azure.txt. This command ensures that we have all the necessary Python modules that facilitate communication between Ansible and Azure APIs. Installing these dependencies is crucial because they enable Ansible to correctly interact with Azure services and perform the desired tasks. Although this step might appear tedious, it plays a fundamental role in preparing our environment so that we can automate the provisioning and management of virtual machines in Azure with ease. Each module in this requirements file provides vital functionality needed for a successful integration. To start, ensure you're logged into your Azure account by executing the command az-login. This command will either open a browser window for you to enter your credentials or prompt you directly in the terminal to log in. Once your login is successful, it's advisable to check your current subscriptions to verify that you are working with the correct one. You can do this with the command az-account-list output table, which will display all your subscriptions in a user-friendly table format. If you find that you need to switch to a different subscription, you can set it using the command az-account-set subscription ID. Be sure to replace subscription ID with the actual ID of the subscription you want to switch to, which you obtained from the previous command. Keep in mind that this subscription change is temporary. If you close and later reopen your terminal, you will likely need to set your desired subscription again. This practice helps you stay organized and ensures that your commands affect the intended Azure resources. In our playbook, we first define a crucial variable called app, which stores essential details about our application. Within this variable, we specify vital attributes such as the application's name, its location, and the public DNS name. For example, we set the app's name to Learn Ansible WordPress, indicating the specific project we are working with. Additionally, the location West Europe signifies where the resources will be provisioned, and the public DNS name Learn Ansible allows easy access to the application once deployed. Next, we introduce the common tags variable, which assigns tags to every resource we create in our infrastructure. Tags are valuable for identification and organization within a project and helps to manage resources effectively. In this section, we associate the project tag with the app's name. The environment tag is set to prod, reflecting the production setting, and we include a tag for deployed by, assigned as Ansible. This structure not only streamlines our deployment process, but also enhances our ability to monitor and manage resources efficiently across different environments. The code snippet provided is responsible for creating a resource group in Azure, which serves as a foundational element to organize and manage resources effectively. The task is labeled Create the Resource Group to ensure clarity in what the playbook is doing. It utilizes the azure.azcollection.azure.rm resource group module, which is specifically designed for interacting with Azure Resource Manager. Within this task, several parameters are specified. The name parameter assigns the name of the resource group dynamically from the variable resource group name, allowing for flexibility in naming conventions. The location parameter indicates where the resource group will reside geographically, sourced from the variable location. Additionally, the tags parameter enables the assignment of metadata to the resource group through the common tags variable, facilitating better management and categorization. A critical component in this code is the register keyword. By using register resource group output, the outputs from this task, including details about the resource group creation, are captured and stored for later use within the playbook. This step is vital for maintaining context and reusing information in subsequent tasks, much like ensuring all your keys are organized in one place. The code snippet provided outlines the process for creating a virtual network in Azure using Ansible, a powerful automation tool. The task begins with defining the action as Create the Virtual Network, which is crucial for establishing a communication channel between virtual machines, VMs, within Azure. The module being used here is Azure RM Virtual Network, which is specific to Azure's resource management. The first parameter, resource group, references the resource group where this virtual network will be deployed. It utilizes a variable, resource group output.state.name, to dynamically fetch the name of the already created resource group, ensuring that the network is organized within the correct context. Next, the name parameter is assigned the value of virtual network name, a variable that should hold the desired name for the new virtual network. The address prefixes parameter specifies the CIR block for the virtual network, drawn from the variable vnetconfig.cir_score block. This defines the range of IP addresses that will be allocated within the network. Additionally, tags are applied using the variable common tags to facilitate management and categorization. Finally, the command registers the output of this task in virtual network output for potential use in subsequent tasks. In this segment, we focus on adding subnets to the existing virtual network. Subnets are critical for managing network traffic efficiently, allowing for better organization and security. The script begins with a task labeled Add the subnets to the virtual network, indicating its purpose clearly. The code utilizes the Azure.acollection.azure.rm subnet module, which is designed specifically for interacting with Azure subnets. It takes several parameters: resource group, which specifies the resource group containing the virtual network; name, which assigns a name to each subnet based on the iteration variable; and address prefix, which designates the range of IP addresses for the subnet. A key feature here is the use of with items, which enables looping through a list of subnets defined earlier in the configuration specified by vnetconfig.subnets. This approach provides flexibility, allowing the addition of multiple subnets in a single task efficiently. The results of this operation are stored in the subnet output register, which can be utilized for further processing or verification later in the script. Overall, this modular approach enhances scalability for future networking expansions while maintaining a clean and organized structure. In this section, we outline the creation of a network security group, NSG, within our established network. The code snippet uses the Azure.acollection.azure.rm security group module, which is specifically designed for managing security groups in Azure. The first step is to specify the resource group, which is dynamically referenced from a previously set variable, resource group output.state.name. This approach ensures that the NSG is created in the correct resource group. Next, we define the name of the NSG by utilizing the variable NSG name. This promotes reusability and clarity in our code, allowing us to easily manage the NSG name from a central location. The rules attribute is populated with the NSG rules variable, which contains the traffic control rules that dictate the allowed and restricted ports, a crucial aspect for maintaining security integrity. Finally, the tags attribute, represented by common tags, helps in categorizing the NSG for easier identification and management in the Azure portal. To complete the operation, the result is stored in NSG output, enabling further actions based on the NSG's properties. This concise yet powerful code snippet is essential for configuring network security effectively. In this section, we will create a public IP address essential for our load balancer. The code uses the Azure Ansible module, specifically Azure RM public address, to facilitate this process within a designated resource group. We reference the resource group name dynamically using resource group output.state.name, ensuring that it adapts to our specific setup. The allocation method is set to static, which is crucial for maintaining consistent access to our resources. By using a static IP, we prevent the address from changing, thus enabling reliable connectivity for any domains or services associated with this IP. The name of the public IP address is derived dynamically from the variable load balancer public IP name, allowing flexibility in naming conventions based on our configuration needs. Additionally, we specify the SKU as standard, which provides enhanced features and reliability compared to basic options. Finally, the result of this operation is registered in the variable public IP output, which can be used later in the playbook for further configurations or outputs. This step ensures our load balancer can efficiently interact with external traffic through a stable entry point. In this section, we focus on creating an Azure load balancer to optimize traffic management for our application. The first task is to define the load balancer in our configuration file. We do this by using the Azure.acollection.azure.rm load balancer module, specifying the resource group where the load balancer will reside. This is crucial to keep our resources organized and managed effectively. Next, we assign a name to our load balancer, which helps in identifying it within the Azure portal. We're opting for the standard SKU, which is suitable for production workloads, providing improved performance and features. The front-end IP configuration is vital, as it dictates how incoming traffic connects to our load balancer. Here, we set up a configuration that includes a public IP address, which we previously created. This connection enables the load balancer to direct traffic to the appropriate virtual machines, ensuring they operate smoothly, even under heavy user requests. In summary, This code sets up a scalable and reliable entry point for our application, maximizing availability and performance. In this section of our tutorial, we focus on creating a network interface for our virtual machine, specifically tailored for a WordPress setup. The code snippet illustrates an Ansible task that employs the Azure RM resource module to define the network interface's characteristics. We start by giving the task a descriptive name, create the network interface for the WordPress VM, which helps clarify its purpose. The task specifies the API version we want to engage with, ensuring compatibility with Azure's current features. Next, we identify the resource group in which the network interface will reside by dynamically referencing the previously defined resource group output.state.name. This approach allows our playbook to remain flexible and reusable across different environments. We then clarify the type of resource being created, in this case, a network interface, by setting the provider, resource type, and finally the resource name, which is generated by combining values from the dict.network interface along with the name of our virtual machine. By employing idempotency set to true, the task will only create the resource if it doesn't already exist, preventing unnecessary duplicates and ensuring our infrastructure remains clean and efficient. This code snippet is responsible for creating an administrative virtual machine in Azure. It utilizes the Ansible module Azure RM Score Virtual Machine, which allows for seamless management of virtual machines within Azure. The first step involves specifying the resource group, which is pulled from a variable that reflects the output of the resource group creation. The virtual machine's name is set using another variable that designates the desired name for your VM. Next, you'll notice the configuration for the admin username, which is sourced from the predefined configuration variable. This is crucial for accessing the virtual machine later. The code also includes a section for SSH public keys, ensuring secure access to the VM. You'll provide the key path and key data through additional variables. Furthermore, the virtual machine size is specified, which determines the resources allocated to your VM. The managed disk type is also defined, allowing for optimized storage options. Lastly, the network interface is linked to the virtual machine, ensuring it can communicate within the Azure environment. The image section wraps up the configuration, defining the operating system and version that will run on the virtual machine. The code provided performs an essential function in ensuring that the virtual machine VM is accessible before proceeding with further configurations. It utilizes the Ansible.built-in wait-for module, which is designed to pause the execution of playbooks until a specified condition is met. In this case, the condition is the successful availability of the VM's SSH service. The host parameter is set to retrieve the public IP address of the VM using the provided variable public IP output.state IP address. This dynamic reference ensures that the wait command targets the correct machine, particularly useful in environments where IP addresses may change. The port parameter specifies which port to check for accessibility, here determined by loadbalancer.ssh port, setting the stage for SSH connections. To manage retry intervals, the delay is set to 10 seconds, allowing some time after the VM is initiated before checking its status. Finally, the timeout value of 300 seconds provides a maximum waiting period, preventing indefinite waits and ensuring that the process remains efficient. This thoughtful configuration allows smooth and reliable access to the VM for subsequent tasks while embracing the virtue of patience. With the VM up and running, we can turn to bootstrapping our applications, such as WordPress. This is where you step back, reflect on your well-laid foundations, and build your applications on top of this infrastructure confidently. To summarize, we just launched a fully fledged virtual machine in Azure using Ansible, involving a series of calculated steps from setting up the cloud environment to deploying your application. Rinse and repeat these steps for other applications or VMs, and you'll find this process becomes second nature. Now let's look at the figure. This excerpt displays the output from an Ansible playbook that runs handlers for restarting services. At the top of the figure, we see that two handlers are being executed. The first is for restarting Nginx, and the second for restarting PHP-FPM. Each handler indicates that a change has occurred on the specified host, 13.93.65.208.22, highlighting the effectiveness of the tasks executed. Moving down to the Play Recap section, we can observe a summary of the Playbooks results. The host 1393.65.208-22 has 42 tasks in total, with 29 of them resulting in a change, while there are no unreachable or failed tasks, which reflects successful execution. The output also notes that one task was skipped, suggesting that certain conditions in the playbook were not met for this host. Additionally, the local host results are shown, indicating that there were 13 tasks executed, with all resulting in changes and no failures. This information in the figure emphasizes how Ansible efficiently manages task orchestration and provides feedback on task execution, allowing users to understand the state of their deployment and configurations in real time. Together, this figure serves as a visual representation of task management success and the overall efficiency of using Ansible in a cloud environment. Now that we have an access key ID and secret access key for a user with the permissions, we can launch our virtual private cloud, VPC, using Ansible. But before diving into the actual playbook, it's crucial to understand how to configure our environment securely and efficiently. You might be wondering, what's with all the security fuss? Well, in the cloud arena, your credentials are like golden tickets, and we need to keep them under lock and key. Let's start this adventure of configuring security groups and access keys, shall we? In this section, we're using Ansible to create a security group in AWS. The process begins with specifying the name of the task, which is to create the security group. This makes the playbook clearer and easier to understand. The Amazon.ec2 security group module is utilized here, which is specifically designed for managing security groups in AWS. The first parameter is the name, set to My Security Group. This name provides an identifier for the security group within your AWS account, making it easier to manage later. Next, we provide a description that offers insight into the purpose of the security group. In this case, it's designated as Security Group for my Ansible Managed VPC. Clear descriptions help in identifying the function of various resources in your cloud environment. We also need to specify the region where the security group will be created, which here is set to US East 1. Choosing the correct region is essential for resource management and optimization. The state is set to present, indicating that this security group should exist after the playbook runs. Lastly, the VPC ID parameter ties the security group to a specific virtual private cloud, and tags are included for easy identification and organization within your AWS account. In this section, we focus on defining a rule for our security group to allow HTTP traffic. The code specifies the action of adding an HTTP rule using the Ansible module amazon.aws.ec2 security group rule. This module takes parameters like group ID, which references the security group we created earlier, along with the protocol, from port, and to port settings. By setting both the from port and to port to 80, we open this specific port for TCP traffic. Notably, the CIDR IP parameter is set to 0000/0, allowing traffic from any IP address. While this configuration can maximize accessibility, it's often advisable to limit access to certain IP ranges to enhance security. Alongside these security rules, managing access keys securely is critical. The next part of the code demonstrates how to export your AWS access and secret keys as environment variables, which is a best practice. By executing the export commands in your terminal, you allow Ansible to use these credentials during the session. However, it's crucial to note that these variables only persist for the current terminal session, requiring you to set them again if the terminal is closed. In this Ansible playbook, the configuration focuses on managing AWS security groups, which are essential for defining security rules around your virtual private cloud, VPC. The playbook starts by defining key variables, such as the AWS region and the VPC ID, both crucial for the resource management tasks that follow. By specifying the region as US East 1 and assigning a placeholder for the VPC ID, the structure ensures that these values can be easily modified as needed. The first task is to create a security group named My Security Group. This is done through the amazon.aws.ec2 security group module, where the playbook outlines parameters for the security group's name, description, region, state, and associated tags. Notably, the use of variables for the region and VPC ID enhances reusability and clarity. Following that, the Playbook adds an HTTP rule to the security group using the amazon.aws.ec2 security group rule module. This rule allows inbound TCP traffic on port 80 from any IP address, thereby permitting web traffic. This approach simplifies security management, making it easier to adapt rules without getting lost in complex configurations, ultimately bolstering security in the cloud environment. At this point, you might be feeling like a certified AWS security architect. We've created a security group and configured access rules while utilizing best practices for managing our access keys. It's essential to continuously review and update your security groups to reflect your current needs. Periodic audits will help to ensure unauthorized access is minimized and that compliance regulations are met. Let's wrap up our discussion on security groups and access keys by highlighting the importance of thorough documentation. Keep track of your access key generation, usage policies, and any changes made to security groups. This approach not only promotes transparency, but also helps when troubleshooting issues or preparing for security assessments. And there you have it. Your journey into configuring security groups and access keys is just the tip of the iceberg. The cloud is ever evolving, offering new features and capabilities. As you continue down this path, keep exploring and refining your skills. After all, tomorrow's cloud experts are shaping the landscape today. Consider this your starting point. Who knows where each new project will take you? So go forth, configure those security groups, secure those access keys, and make excellent use of Ansible. Happy automating. Now that we have all the roles needed to deploy our resources into AWS, we can run the playbook. This statement marks a pivotal moment in our journey towards establishing highly available cloud deployments. To start, let's break down the process step by step, ensuring that we understand both the conceptual framework and the practical execution involved in running a playbook in AWS. In the realm of cloud computing, particularly within AWS, the goal of achieving high availability encompasses designing systems that remain operational and capable of handling user requests even in the face of failures, whether those failures are due to individual component malfunctions, network outages, or even entire data center failures. Running an Ansible playbook is a strategic way to automate the deployment of resources that are designed with high availability in mind. To begin deploying with Ansible, we first need to establish the necessary environment variables that link our local setup to AWS. This is accomplished by exporting the AWS access key and secret key within our terminal session. The syntax for this is straightforward. You use the command export, followed by the variable name and its corresponding value. It is crucial to replace your access key and your secret key with your actual credentials. This step is fundamental, as it ensures that the Ansible playbook has the appropriate permissions to manage resources within your AWS account. Once we have set up our environment variables, we proceed to run the Ansible playbook. For this, we use the command ansible playbook-i host site.yml. Here, -i hosts specifies the inventory file, which lists the servers that Ansible will interact with. And site.yml is the main playbook that defines the tasks and roles required to set up a highly available WordPress installation. As the command executes, Ansible interprets the playbook's instructions, orchestrating the necessary actions to provision and configure the resources on AWS, bringing our project to life. The provided Ansible playbook begins with a key directive: mash name, deploy and configure the AWS environment. This line serves as a descriptive label for the task that will be executed, offering clarity about the playbook's purpose. Following this, the host's localhost specification indicates that the playbook will be executed locally, targeting the machine where Ansible is running rather than remote servers. This is particularly useful for scenarios where local deployment and configuration are necessary. Next, the connection local setting reaffirms that Ansible should run the tasks on the local machine instead of connecting to remote hosts over SSH. This is useful in environments where you may be setting up infrastructure using API calls rather than SSH into instances. Finally, The gather facts true directive instructs Ansible to collect details about the local machine and target AWS environment before executing any tasks. This fact-gathering phase is crucial as it provides vital information that informs subsequent configuration steps, ensuring the playbook runs smoothly and effectively. This line of code refers to a specific role in an Ansible playbook, designated as ELB, which stands for Elastic Load Balancer. By incorporating this role, we instruct Ansible to manage the functionality associated with AWS Elastic Load Balancers. The role encapsulates all the necessary tasks and configurations required to set up and manage an ALB, aligning with our objective to efficiently handle incoming traffic to our EC2 instances. When the role is executed, Ansible will automatically determine the best approach to provision the load balancer according to the desired state defined in the playbook. This abstraction simplifies the process, also ensuring that configurations are consistent and repeatable across different environments. By leveraging this role, we are able to direct incoming requests intelligently, thereby preventing any individual instance from becoming overwhelmed. This helps maintain system stability and uptime, which is crucial for the user experience. All in all, implementing the ELB role is a vital step in our overall infrastructure deployment, making sure that traffic management is both efficient and reliable. In this configuration, we define two key roles: the Amazon Relational Database Service, RDS, and the Amazon Elastic File System, EFS. First, the RDS role is essential for setting up a managed database for our WordPress application. By utilizing RDS, we not only benefit from automated backups, patching, and scaling, but also enhance our database's availability through a multi-AZ deployment. This setup ensures that even if one database instance encounters an issue, the other can take over seamlessly, mitigating downtime and minimizing the risk of 500 internal server errors for users. Next, we introduce the EFS role, which plays a critical part in managing shared storage. By implementing EFS, we create a centralized location for all instances of our WordPress deployment to access. This is particularly important for applications like WordPress that rely on multiple instances to function cohesively. With EFS, we ensure that content and media files are consistently accessible, promoting a seamless user experience across all instances. This dual approach of using RDS for database management and EFS for shared storage effectively lays the groundwork for a robust and resilient WordPress deployment. In the code snippet provided, the line NAS role EC2ME indicates a specific role assigned within the context of an automation or orchestration tool, likely for managing cloud resources. This role is related to Amazon EC2, or Elastic Compute Cloud, and it suggests that the task at hand involves managing or deploying Amazon Machine Images, AMEs. By defining the role as EC2 AME, the script is instructed to utilize the capabilities of EC2 in the context of AMIs. Creating an AMI from an EC2 instance is crucial because it allows for the preservation of the instance's configuration, applications, and data. This AMI acts as a snapshot or template that can be used to launch new EC2 instances quickly, facilitating scaling and recovery processes. This automated approach to managing AMIs ensures that developers and system administrators can maintain high availability in their architecture. If a running instance encounters issues, the ability to spin up a new one directly from an AMI guarantees minimal downtime and business continuity, reinforcing the resilience of the overall system. In this script, we define a role for auto-scaling, indicated by the line role auto-scaling. This role is crucial as it allows the automation of scaling EC2 instances based on the demand. The auto-scaling group, ASG, monitors the performance metrics of your applications and can automatically adjust the number of running instances to maintain optimal performance. When traffic increases, the ASG detects this change and launches additional instances to handle the load. Conversely, if the traffic recedes, the ASG can terminate excess instances, ensuring that you're not incurring unnecessary costs. This dynamic scaling ensures that your infrastructure remains efficient, responsive, and cost-effective. Furthermore, integrating auto-scaling into your deployment strategy is a critical step towards enhancing the overall reliability of your system. By diminishing single points of failure, you create a highly available environment capable of providing continuous service to users, even during unexpected spikes in demand. This approach not only optimizes resource usage, but also supports your application's performance and availability goals. The first piece of information we have is the estimated monthly cost associated with maintaining the setup, approximately $61.83. It's crucial for users to be aware of potential expenses, as cloud resources can add up quickly based on usage patterns. This figure encompasses standard operational costs, but could fluctuate depending on scaling needs, additional instances, or various levels of redundancy you might implement. As you conclude the use of your AWS setup, managing those costs effectively becomes paramount. Fortunately, with the Ansible playbook you've utilized, decommissioning all resources is straightforward. The command you will run is ansible-playbook die hosts destroy.yml. This command efficiently dismantles everything created during the playbook execution. Think of it as a cleanup crew that ensures all remnants of your setup are removed, preventing any unnecessary charges from lingering resources. By running this command, you ensure not only a tidy end to your deployment, but also a proactive approach to managing cloud expenses. Now let's look at this figure. It presents the security group's interface within the AWS Management Console, showcasing critical components for managing network access in your cloud environment. At the top, we identify various security groups, including a selection highlighted for further examination. This section is crucial for setting rules that allow or restrict traffic to and from your resources. Specifically, the figure highlights the Learn Ansible-RDS Security Group, which is vital for managing access to your Amazon RDS instances. It displays relevant details such as the security group ID tied to this group, emphasizing its importance in isolating and protecting your database layers. Below this, we see inbound rules, which outline how traffic can flow into your resources. The inbound rules section details the specific configurations, including the allowed protocols and ports. In this instance, traffic is permitted over TCP on port 3306, which is typically used for MySQL Aurora databases. Understanding these rules is fundamental in ensuring that your database services are only accessible by the intended clients, thus enhancing security while maintaining necessary accessibility. By effectively managing these security groups and their associated rules, you can ensure a robust architecture that complies with security best practices and supports the demands of your applications. This figure serves as an essential reference as you navigate the complexities of cloud deployments, providing a visual representation of key elements involved in maintaining high availability and security. Before diving into the playbooks, we should get an idea of what we are trying to achieve. Understanding the goals of our cloud deployment is crucial as it sets the foundation for all subsequent actions. In our case, we are building a highly available WordPress installation on AWS. This entails not only deploying the WordPress application, but also integrating various AWS services to ensure reliability and efficiency. Our deployment will include multiple EC2 instances for load balancing, Amazon RDS for database management, and EFS for shared storage across instances. Now let's look at the figure. This diagram illustrates the virtual private cloud architecture that we will be setting up for our deployment. At the top, you can see the Internet Gateway labeled Learn Ansible-Pro-Internet-Gateway, which facilitates external access to the resources within our VPC. This is a critical component that allows communication between our internal network and the outside world. To the left of the diagram, we find the Elastic Load Balancer, ELB, identified as Learn Ansible Prod-ELB. This element is essential for distributing incoming application traffic across multiple targets, ensuring that no single instance is overwhelmed with requests. Accompanying the ELB is its security group, Learn Ansible ELB Security Group, situated within the designated DMZ subnet EUW1 AZ13. This clearly shows how security is layered within our architecture, protecting the ELB from unauthorized access. In the upper right section, we observe the RDS instance labeled Learn Ansible Prod RDS. This relational database service is crucial for managing our application's data. The corresponding security group, Learn Ansible RDS Security Group, is also displayed in this region, ensuring that access to the RDS instance is securely controlled. All these components are located within the RDS subnet EU1-AZ1 demonstrating the subnet organization that enhances security and management. Next, focus on the lower section of the figure, where we see the auto-scaling group, ASG, with two EC2 instances represented by T2. This setup is vital for load balancing and ensuring high availability. The security group for the EC2 instances, Learn Ansible EC2 Security Group, is also defined here, placed within EC2 subnet EUW1.AZ13. This arrangement allows our instances to scale up or down based on demand, while keeping them protected. Finally, to the right, we have the Amazon Elastic File System, EFS, labeled Learn Ansible Prod, EFS. Designed for shared storage, EFS spans multiple availability zones, enhancing our application's resilience and performance. Its security group, Learn Ansible EFS Security Group, is available here as well, ensuring that stored data is secure and accessible only to authorized instances. The EFS is situated in the EFS subnet EU1-AZ1, completing the architecture of our robust and secure VPC environment. Now let's consider the cost implications of our deployment. It's important to budget appropriately to avoid sticker shock later. The estimated monthly costs for our deployment in the EU West 1 region is as follows. EC2 instances, T2.micro, 18 and 40. RDS instance, 2 micro, 13. Application load balancer, 2424. EFS, 4 full. Total, $61.83. This is just an estimate based on the basic usage model. Be mindful that while costs can escalate with additional features, such as enhancing RDS to a multi-AZ deployment for better redundancy and performance, we want to keep things simple for now. You wouldn't want to add complexity right before your big plans, would you? Let's shift our focus to the figure displayed here. This diagram illustrates the deployment architecture crucial for our application, highlighting the distinct subnets and components involved. At the top, we see the public internet, which interfaces with the external firewall, providing a protective layer for our system against unauthorized access. The diagram features a load balancer prominently positioned at the top, which ensures that incoming traffic is effectively distributed to the appropriate systems. Below the load balancer, in the gateway service subnet, we find various systems such as the SRA gateway and the Access Manager SDK. This subnet plays a key role in managing requests and securing access to our application resources. Moving down, we enter the portal service subnet, where multiple load balancers are in place. These manage systems like the portal server and the application server, both of which are vital for delivering our application services. The application server operates in a clustered environment to enhance scalability, while the load balancers here ensure even distribution of traffic across these servers. Additionally, within this subnet, we have critical components like the message queue and database, which are essential for handling data operations and maintaining the application's performance. The internal firewall provides another layer of security, further segmenting the network to protect sensitive information and resources found in the directory service module, which includes the LDAP store for user authentication. Overall, this figure provides a comprehensive look at the organized structure of our deployment, showcasing the interactions between various components and their roles in maintaining a robust and secure application environment. Now that we have the ELB set up, it's time to deploy our RDS instance. The RDS instance must be available before launching the WordPress installation because we need to create the database that will store all our user and post data. And then we need to provision EFS, our shared storage. Just like making sure the pantry is stocked before you start a cooking project, EFS needs to be ready to hold our application files. Following this, we will need to launch our EC2 instances. The deployment of 2 instances helps ensure that our WordPress installation can operate redundantly. Given that they will serve the front end of our application, balancing their load is essential. Now let's look at the figure. This diagram outlines the multi-environment structure of the deployment process, highlighting the development, testing, and staging phases. Each phase is represented by specific data sources: dev data source for development, quit data source for testing, and got data source for staging. These data sources are critical as they ensure that each environment can function independently with its respective configurations. Focusing on the myejb.jar components, you'll see that it interacts with the respective environment configurations through the weblogic-ejbjar.xml files. Each of these files contains reference descriptors that link to the appropriate data source for that environment, ensuring a clean and predictable setup. Notably, the reference descriptor for development points to dev data source, underscoring how isolated environments maintain their unique settings while employing the same core application logic. Moving to QA, the figure illustrates the QAplan.xml file, which acts as a configuration plan for the testing environment. Here, a variable named myResource is defined, which is set to QA data source. This clear definition allows for fluid transitions from one environment to another without confusion, promoting a systematic approach to testing and validation. Finally, in the staging environment, we observe the productionplan.xml file, which reflects changes made specifically for the production phase. This file similarly defines a resource variable, myResource, but it connects to GADDataSource. Importantly, it also includes an additional variable for handling a timeout setting. All these components work in harmony, emphasizing the necessity of comprehensive documentation and configuration management in maintaining efficiency and reliability during deployment. In this snippet, we outline a playbook with the primary objective of deploying and configuring the AWS environment. The playbook specifies that the target hosts are set to localhost, indicating that the execution will occur on the local machine. It employs a local connection, which allows tasks to run without needing to connect to a remote server, making it efficient for this type of infrastructure setup. The Gather Facts option is enabled, allowing the playbook to collect information about the system's configuration and environment automatically. This data can be useful in tailoring subsequent operations based on the local machine's parameters. The vars section introduces a variable named state, which is set to present, signifying that the desired state of the resources being configured should exist. Next, the vars files directive points to an external variables file, groupvars/common.yml, which contains commonly used variables throughout the playbook. Finally, the roles section specifies a list of predefined roles, such as VPC, subnets, and security groups, that modularize and organize the tasks related to different AWS components, promoting clear structure and reusability in the deployment process. In the provided code, we begin with a task labeled Install and Configure WordPress. This task is designed to target a specific group of hosts, referred to as VM group, which signifies the machines where the WordPress application will be deployed. The Gather Facts True directive indicates that before executing the tasks, Ansible should collect detailed information about the remote hosts, which is critical for making informed decisions during the playbook execution. The Become True statement illustrates that the following tasks will be executed with elevated permissions, necessary for operations that require administrative access. The Become method, ansible.builtinsudo, specifies that the sudo command will be used to escalate privileges. Within the vars files section, two YAML files are included, groupvarscommon.yml and groupvarsgenerated8osendpoints.yml. These files are used to define variables that are essential for the configuration and installation process. Finally, the roles section calls upon three predefined roles: stack install, stack config, and WordPress. These roles compartmentalize the tasks associated with setting up the WordPress stack, streamlining the installation and configuration process to ensure a smooth deployment. The code snippet provided is an Ansible playbook designed to create an Amazon Machine Image, AMI, of a configured EC2 instance and subsequently update the auto-scaling group. The playbook runs on the local host and uses a local connection, which means it executes commands directly on the machine where Ansible is being run rather than on a remote server. The playbook starts by declaring necessary variables, such as the desired state of the AMI, which is set to present. This indicates that the playbook is intended to ensure the AMI exists. It also references an external variables file, groupvars/common.yml, which likely contains environment-specific configurations. The roles section specifies two roles, EC2MI and autoscaling. The EC2MI role is responsible for handling the creation of the AMI based on the current state of the EC2 instance, while the autoscaling role manages updates to the autoscaling group to ensure that it accommodates any new AMIs created. Overall, this code efficiently captures the current state of an instance and prepares the system for scaling as needed. At its core, planning the deployment goes beyond merely knowing our resources. It involves orchestrating them so they work together cohesively. After executing the playbook, it's prudent to check our AWS console to ensure every service we intended to deploy is functioning correctly. You wouldn't want to be caught off guard with surprise charges at the end of the month because a resource was left running without purpose. As we wrap up our deployment process, the importance of continuous monitoring cannot be overlooked. Keeping an eye on system performance allows us to react to any potential issues proactively. And just like in any good adventure story, having a plan and being prepared for twists and turns along the way can make all the difference. In conclusion, planning the deployment is a multifaceted exercise requiring an understanding of both the components and their interactions within the AWS ecosystem. With the right preparation, we can create a resilient, scalable, and efficient WordPress environment that not only meets user demands, but does so with elegance and reliability. This is just the beginning of our journey. With the groundwork laid down, we can focus on optimizing our deployment for future needs. Thank you for joining me on this tutorial regarding the planning phase of deploying a highly available WordPress environment on AWS. Stay tuned for the next segments where we dive deeper into the playbook execution and detailed configurations. With over 25 years of history, VMware has evolved significantly from its origins as a stealth startup. Initially, the company may have started with a simple vision of bringing virtualization to servers, but it has now transformed itself into a crucible of innovation, providing solutions for businesses around the globe. You may be wondering, what exactly is VMware? Well, it's primarily known for its hypervisors, which allow multiple virtual machines, or VMs, to run on a single physical machine. This capability has become a staple in most enterprises, enabling administrators to deploy virtual machines rapidly across various standard x86-based hardware configurations. Now, let's dive deeper into what a hypervisor actually does. A hypervisor is essentially an abstraction layer between the hardware and the operating systems that run on top of it. By allowing multiple operating systems to run concurrently on a host machine, it maximizes the utility of physical hardware. Picture it this way. If you have a robust physical server, why not split its resources, like CPU, memory, and storage, across several different operating systems? It's just like having multiple apps open on your phone. Each one runs on the same hardware, but functions independently. The magic happens thanks to the hypervisor, which allocates resources and ensures that each VM operates smoothly without interfering with others. VMware's popular products, such as VMware vSphere, vCenter Server, and VMware Cloud Foundation, offer remarkable features for managing these virtual environments effectively. vSphere is a platform that allows you to deploy, manage, and migrate VMs, while vCenter Server provides a centralized platform for managing the vSphere environment. VMware Cloud Foundation brings together vSphere with additional offerings like NSX for networking and vSAN for storage, creating an integrated cloud platform to run your applications seamlessly. Now let's look at the figure. This diagram illustrates the Azure VMware solution and the interconnected infrastructure that supports it. Central to the figure is the Azure VMware Solution Cloud, represented by the cloud icon with the Azure logo. This solution provides a robust platform for deploying and managing VMware environments within the Azure ecosystem. To the left, we see Microsoft-owned or operated data center facilities. These facilities contribute to the infrastructure reliability and performance, ensuring that your workloads benefit from the scalability and redundancy of Azure's vast network. Adjacent to this, third-party data center facilities are highlighted, indicating that additional options are available for hosting resources that leverage the Azure VMware solution. In the center of the figure, the dedicated ExpressRoute Edge is depicted. This connectivity option allows for a private connection between your on-premises infrastructure and Azure, enhancing performance and security. The ExpressRoute Gateway is illustrated further down, showcasing its role in facilitating this private connection and managing data traffic efficiently. Moving to the right side, we notice the Hub Virtual Network. This network acts as a central point of connectivity, allowing multiple resources, including virtual machines, to communicate seamlessly. From this hub, there are connections to various virtual machines represented by the blue icons, demonstrating how resources can be organized within the network. At the bottom of the diagram, we find details of the ExpressRoute MeetMe location, which is a carrier-neutral facility. This setup allows different communications providers to connect to Azure, promoting flexibility in how you manage your network connections. Finally, the figure concludes with customer-managed ExpressRoute circuits and customer premises, illustrating the integration between your local infrastructure and the Azure cloud environment. Overall, this figure effectively encapsulates the architecture of the Azure VMware solution, providing a clear visual representation of how resources can be interconnected to build a comprehensive private cloud environment. As exciting as all of this sounds, it's worth mentioning that VMware recently underwent some significant changes. In late 2023, it was acquired by Broadcom, which has since implemented a subscription-based model for VMware's products. This shift aims to align with contemporary cloud consumption trends and improve customer experience. Through this model, users can expect continuous innovation and quicker time to value, even if it requires bidding farewell to those perpetual licenses we've grown accustomed to. Speaking of innovation, let's now explore the various modules in the VMware ecosystem. The VMware REST modules are particularly noteworthy. Imagine being able to interact with your VMware resources seamlessly through Ansible. With around 30 products in the VMware range, both administrators and developers can leverage these modules to orchestrate tasks, automate deployments, and manage resources. The flexibility these modules provide comes from their reliance on the VMware REST API, allowing you to interact with your infrastructure irrespective of the medium, whether through CLI, web interface, or automation scripts. Now let's look at this figure, which illustrates the AT RESTful facade structure. At the top, we see the content negotiation filter, which is essential for managing how different types of data are served based on client requests. This component acts as a mediator, determining the appropriate response format depending on the client's specifications. Beneath the content negotiation filter resides the RESTful servlet. This pivotal element interacts with incoming HTTP requests, processing them to trigger the correct handlers below. Within this layer, the RESTful handler chain is illustrated, which serves as a collection of handlers that facilitate various operations such as authentication, resource retrieval, and request processing. Adjacent to these components, we find the Jersey servlet, a framework that simplifies the development of RESTful web services. This servlet handles the integration of JAX-RS resource classes, which encapsulate the core business logic and resource management. The JAX-RS resource classes are critical because they define the REST endpoints, mapping HTTP requests to Java methods. At the bottom of the figure are the EJB stubs, which link the RESTful components to enterprise Java beans, allowing for robust back-end processing capabilities. Together, these elements create a comprehensive structure that empowers developers to build effective and efficient RESTful services. Finally, the figure also shows the WADL, Web Application Description Language, arrow, indicating the service's interaction documentation, which further facilitates client integration. In this snippet, we are defining a task to create a new virtual machine using the vCenter VM module. The primary objective is to specify the placement and configuration for the VM. First, the placement field is outlined, where we designate the cluster, folder, and resource pool for the VM. The cluster is dynamically retrieved using the lookup function to get the corresponding Managed Object ID, MOID, for the specified cluster path. This ensures that the VM is placed in the correct environment. Next, we define the VM's name as Learn Ansible VM and set the guest operating system to Ubuntu 64, indicating that the VM will run a 64-bit version of Ubuntu. The hardware version is specified as VMX11, which relates to the virtual hardware version, aligning it with the compatibility for the selected OS. Memory settings are also configured. We have enabled hot add for memory, allowing the VM to dynamically increase its memory allocation while running. The total memory is set to 4000 MB providing sufficient resources for the application being tested. Finally, the output of this operation is registered under the variable Learn Ansible VM output for further use or verification within the playbook. In the code snippet above, you can see how simple it is to create a VM with a few lines of code. The VMware.VMware.REST.vCenter VM module allows you to specify parameters like memory size, the operating system, and the resource pool. The elegance of this approach lies not just in its simplicity, but also in the capacity to later extend and customize the configuration to meet the specific requirements of your environment. Moving ahead, something that deserves your attention is the robust ecosystem that VMware offers around automation and orchestration. With all the modules encompassing various aspects of virtual machines, networking, and data storage, a VMware administrator can build playbooks that help manage resources across their physical and virtual infrastructure seamlessly. To illustrate this, you might have a playbook that not only provisions a VM, but also sets up networking and storage policies, streamlining processes that would typically take hours, if not days, to complete. But don't rush in just yet. Just like walking into a fine dining restaurant, you want to know the menu before you order, right? The same applies to working with VMware. Before diving into any automation or orchestration, it's critical to familiarize yourself thoroughly with the VMware product landscape, understand client requirements, and review the latest documentation available for the modules you intend to use. As we conclude our introduction to VMware, it's important to remember that this is just the tip of the iceberg. The landscape of virtualization and cloud computing is vast and continually evolving. With VMware laying the groundwork for significant advancements in IT management, there's an exciting journey ahead. Whether you're an IT professional looking to enhance your skills or a business owner considering deployment in VMware, the potential benefits are high, pending that you stay updated with the latest trends and best practices. Now let's look at this figure, which illustrates the architecture of VMware's virtualized environment. At the top, we see the VMware vSphere platform, where various virtual machines, VMs, are categorized into different tiers: bronze, silver, and gold. This tiered structure allows organizations to allocate resources based on their specific needs and priorities, ensuring optimal performance of their virtual machines. The vSphere section is linked to two virtual data stores, labeled as Virtual Data Store 1 and Virtual Data Store 2. These data stores serve as storage repositories that hold the virtual machines and their associated files. The connection between vSphere and the data stores indicates how VMware efficiently manages storage allocation and access for VMs, providing a seamless experience for users. Moving down in the figure, we find the various storage protocols employed, including Fiber Channel, FCOE, iSCSI, and NFS. These protocols facilitate communication between the virtualization layer and the physical storage infrastructure, ensuring that data is transmitted reliably and efficiently. This is crucial for maintaining performance in dynamic virtualized environments. At the bottom, we see two storage containers, each containing multiple virtual volumes. These containers represent logical groupings of storage resources, which can be managed independently. The storage volumes are used to hold the actual data from the virtual machines, further showcasing VMware's flexibility in handling different storage schemes while maintaining organization and accessibility. Finally, to the left of the figure, we see the integration of the VASA, VMware APIs for Storage Awareness Provider, and its APIs. This component enhances the management of storage resources by providing critical visibility into the underlying storage capabilities and metrics, which can be leveraged by the storage monitoring service linked to the vSphere platform. This integration is vital for ensuring that organizations can monitor and manage their storage resources effectively within their virtual environment. As always, if you have any particular questions or want to dive deeper into certain aspects of VMware, drop your comments below and let's keep the conversation going. Now, let's get to virtualizing our dreams. As you can see, there is comprehensive support for managing your virtual machine resources using the VMware.VMware REST collection. And what's better is that the modules are all designed to consume the official REST API, meaning that you can safely mix and match how you manage your resources within VMware, regardless of whether you use the CLI, web interface, or Ansible. Now, let's take a dive into what it really means to manage virtual machines with Ansible, especially within the context of VMware. Imagine a classroom bustling with activity, where students sit eagerly as their excited teacher prepares to unfold an extraordinary journey into the realm of virtualization. Today, we are unraveling how tools can integrate with VMware to streamline tasks that might otherwise feel a lot like herding cats. You may be wondering, why Ansible? Simply put, it's like that reliable friend who helps you get through all the chores. Ansible is a powerful automation tool that not only simplifies cloud management, but also ensures you can control your entire virtual infrastructure with ease. If you've ever felt overwhelmed managing multiple virtual machines across different environments, fret not. Ansible steps in as your superhero, waving its wand of automation over everything else, helping you command your virtual machines effortlessly. With the advent of VMware's REST APIs, it allows us to bring an excellent blend of infrastructure management together with Ansible's Playbooks. This provides an easy way to define the state of your environment and ensure your virtual resources are configured and running smoothly. It's like turning on an automation machine and watching all your virtual needs get handled with just a flick of your wrist. In the provided code snippet, we define a task to create a virtual machine using the VMware.VMware REST module in Ansible. The task begins with a name attribute that clearly indicates its purpose: create a virtual machine. The core of the task utilizes the vCenter VM submodule to manage the configuration of the new virtual machine. We specify the placement options, which include the cluster, folder, and resource pool. Each of these parameters utilizes the lookup function to dynamically retrieve the managed object IDs, MOIDs, required for correct resource allocation. For instance, the cluster memoid is fetched from a specified path, host learn Ansible cluster, ensuring that the VM will be placed in the right cluster. Similarly, paths for the folder and resource pool are provided to pinpoint their respective MOIDs accurately. Further down, we define additional essential attributes for the virtual machine, such as its name, which is set to Learn Ansible VM, and specify the desired guest operating system and hardware version. The memory configuration not only sets a size of 4000 MB, but also enables hot add, allowing for memory to be added while the VM is running. Finally, the result of the VM creation is stored in a variable called Learn Ansible VM output, which can be used for further operations or logging. Once the virtual machine is created, Ansible can assist you in managing its state. Think of it like a guardian who watches over and nurtures your newly created pet, or VM in this case. Whether you require guest customizations, modifications to the file system, or changes to the network configuration, each piece can be managed with its dedicated module. You have the likes of vCenter VM Guest Customization, which applies custom scripts or configurations to the VM once it's powered on. It's like giving the VM a personalized touch, making it feel right at home. You might also need to check on your VM's networking settings. All you need to do is call upon the vCenter VM Guest Networking Info module. It's intelligent enough to interrogate your VM and return details of its network configuration. Have you ever watched a detective movie? That's exactly what happens here. The module is unraveling the mystery of your VM's network context. In this section, we will explore how to update the hardware settings of a virtual machine using the vCenter VM hardware module from VMware's Ansible collection. The provided code snippet demonstrates a playbook task specifically designed to adjust the VM's configuration. First, we start by naming the task Update VM Hardware Settings, which clearly indicates its purpose. Next, we define the module to be used, VMware.VMware REST.vCenter This module is responsible for managing the virtual hardware settings of a VM in a VMware environment. The next crucial part of the code is specifying which virtual machine we want to modify. We do this by referencing its unique identifier, stored in Learn Ansible VM output.id. This ensures that the task targets the correct VM. Then we move on to the actual adjustments. We increase the memory allocation by setting size MIB to 8192, which gives the VM a total of 8 GB of memory. Additionally, we specify the CPU configuration by setting count to 4, thereby allocating 4 CPU cores to the VM. This simple yet effective task showcases how easily one can modify VM hardware settings using Ansible. But what's a virtual machine without some proper software on it? If you wanted to install software, you could even make use of the Ansible roles to manage configurations like installing VMware tools, which enhances the VM's performance and compatibility with the hypervisor. The vCenter VM Tools Installer module attaches the VMware Tools Installer within the VM for running the necessary installation. Voila! Your virtual machine is all set to go. But remember, like a good manual, Ansible needs some reference. The role of documentation cannot be overstated. For every automation script you write, ensure you document your process. Great documentation is like a roadmap. It allows others to follow your journey easily. Now, let's look at this figure that illustrates the architecture of a robust Ansible automation setup. At the top, we see the connection to Red Hat services, specifically the Red Hat Insights and the Automation Hub, managed by a load balancer that distributes traffic effectively between Ansible Site 1 and Ansible Site 2. In the center, Ansible Site 1 is designated as the active site, featuring an automation controller that orchestrates the automation processes. Within this site, we have a cluster of nodes, specifically 3 nodes working in tandem to enhance performance and reliability. Each node is essential for executing tasks and managing resources. Moving to Ansible Site 2, which operates in a passive mode, we can observe a similarly structured private automation hub and an automation controller. This setup mirrors Site 1, with its own cluster of 3 nodes, ensuring that there is a backup available for seamless operation and high availability. Both sites include PostgreSQL databases that maintain the essential data and configurations. The figure also highlights an automation mesh, which facilitates communication between execution nodes in both sites. This mesh allows for dynamic load distribution and enhances the overall efficiency of the automation processes. Additionally, at the bottom of the figure, we have Git repositories linked to each automation controller and private automation hub, demonstrating how version control integrates into the automation framework. Webhooks are utilized for replication between these databases, ensuring data consistency across the sites. Centralized logging is also illustrated, showcasing how logs from various nodes and sites are collected, helping maintain oversight and facilitate troubleshooting in the complex automation environment. Now, before we wrap up, I'd like to squeeze in a little humor here. Have you heard about the IT engineer who always carried a ladder? He wanted to elevate his skills. Well, hopefully, after this session, you're feeling elevated in your understanding of VM management with Ansible too. In conclusion, automating the management of VMware virtual machines with Ansible not only saves time, but ensures that your environment remains consistent and dependable. So go ahead and take the plunge into the fabulous world of virtual machine management with Ansible. With every playbook you write, you're not just automating tasks, you're building a more efficient world of technology, one virtual machine at a time. There's a lot more up our sleeves as we continue this journey into automation, but for now, give it a spin, try the examples provided, and play with the settings. Like any good recipe, adding your own twist can lead to delicious results. Happy Ansibling! Welcome, everyone. Today, we're diving into an exciting topic that's essential for anyone working with Ansible playbooks, scanning them for issues using 2 fantastic third-party tools, Checkov and KICS. Throughout this tutorial, we'll break down what's involved in scanning, why it's necessary, and how to effectively implement these tools in your workflow. First things first, let's consider why you would want to scan your Ansible playbooks. As we go deeper into cloud deployments, it becomes increasingly important to ensure that the configurations in your playbooks adhere to best practices. Imagine you're launching a virtual machine with SSH access that's available to anyone on the internet. Yikes! That's a potential entry point for attackers. By scanning your code, you can identify and resolve such vulnerabilities before they become a serious threat. Now let's look at this figure, which presents a KICS report for a recently conducted scan. At the top, we see the report header indicating the version of KICS used, along with relevant details such as the scan paths and platforms, which in this case is Ansible. The report was generated on January 28, 2024, and it specifies both the start and end times of the scan, providing a clear timeline of when the analysis took place. Moving further down the figure, we encounter the vulnerabilities section. This is crucial information as it summarizes the findings of the scan. The icons represent different levels of severity: high, medium, low, and informational. Here we observe that there are 4 high-severity vulnerabilities, 1 medium, 3 low, and a total of 11 informational alerts, culminating in a total of 19 vulnerabilities identified. This visual representation helps users to quickly assess the overall security posture of their Ansible configurations. Finally, we focus on a specific vulnerability highlighted in the report: EFS not encrypted. This entry indicates that the Elastic file system must be encrypted to meet security best practices. It specifies the platform and category, which are crucial for context. The report also includes a link to the Ansible documentation, providing resources for remediation. This level of detail equips users with both a summary of vulnerabilities and actionable guidance to enhance their infrastructure security. To begin with Checkov, the first step is to pull the Docker image using the command docker image pull bridge crew/Checkov latest. This command downloads the latest version of the Checkov image from the Docker Hub repository, allowing you to use it without needing to install the tool directly on your system. By leveraging this method, you ensure that you have the latest features and fixes in Checkov. Once the image is ready, you can scan your Ansible project by navigating to your project directory and executing the next command: docker container run --tty volume /ansible workdir angcrew/checkov directory /ansible. This command runs a new Docker container from the Checkov image. The --rm flag ensures that the container is removed after the scan completes, keeping your environment clean. The -volume plot Ansible flag mounts your current project directory into the container, making your Ansible code accessible. The -workdir /ansible sets the working directory inside the container to your project folder, and the final part specifies the directory to scan. This efficiently conducts the static analysis on your code within the isolated environment of a Docker container. To begin using KICS, the first step is to pull the latest Docker image from the checkmarks repository. This is accomplished using the command docker image pull /KICS latest. This command downloads the KICS image to your local machine, ensuring that you have the most up-to-date version available for scanning your code. Once the image is successfully downloaded, navigate to the directory where your Ansible Playbook is located. You will need to change your working directory accordingly. With your Playbook in place, you can initiate a scan by executing the command docker container run rm-ty volume /ansible /kics scan -path ansible. This command runs a Docker container that mounts your current directory where the Ansible files reside and executes the KICS scan. The options used ensure that the container is removed after the scan is complete and allows for real-time output. As the scan runs, KICS provides immediate feedback, indicating the progress with messages such as "Preparing scan assets done." When the scan is finished, you will receive an overview that highlights the total number of files scanned and the checks performed, offering insights into your Ansible configurations and security posture. Let's dive into what happens next after the scans. Reviewing the results is crucial. Both tools provide detailed feedback on the checks performed. For instance, in Chekhov's output, you'll see something like passed checks 5, failed checks 3. Each result will specify the checks that passed, failed, or were skipped, along with references to best practices to address any issues. The failures will typically point out potential misconfigurations or missing elements in your playbook. For example, Checkov might alert you that an EC2 instance shouldn't have a public IP address, or that you are using an insecure URL for a GET request. In this section, we focus on enhancing the security of your deployment by ensuring that the Elastic file system, EFS, is encrypted. The code snippet provided demonstrates how to configure this setting within an Ansible playbook. Specifically, the community.aws EFS module is utilized to create an EFS file system. The key parameter here is encrypt, which is set to true. This straightforward adjustment guarantees that your EFS file system will have encryption enabled by default, aligning with best practices for securing sensitive data. By implementing this change, you not only meet compliance requirements, but also boost the overall security posture of your infrastructure. It's important to note that while addressing any compliance issues is essential, there may be instances where certain checks might not be applicable to your scenario. For example, if you're using a temporary instance and choose to disregard a specific check, both Checkov and KICS offer mechanisms to suppress those warnings. You can simply add a comment in your playbook instructing the tool to skip that particular check, allowing for greater flexibility in your deployment strategy. After completing the necessary modifications to your code, it's crucial to rerun your scans to verify that all issues have been addressed. This iterative process often involves going back and forth between running your tools and fixing identified problems. Even after making adjustments, it's common to scan again to ensure everything is in order and to achieve a clean bill of health. In the context of KICS, once you resolve the issues, running the scan once more will yield results that indicate the current status of your code security and quality. The results summary provides a clear overview of findings across different severity levels: high, medium, low, and info. In this particular instance, the summary shows 0 issues across all categories: high, medium, low, and info, culminating in a total of 0 findings. This outcome is highly satisfying, resembling a gold star for your code, signaling that your modifications have effectively addressed all previous concerns and that your code is now clean and secure. The provided command utilizes Docker to run a containerized instance of KICS, a tool designed for scanning code for vulnerabilities. The command begins with docker container run, which initializes a new container based on the specified image, in this case, checkmarks KICS. The flags nasrm and nashti are used to automatically remove the container once it completes its task and to allocate a pseudo terminal for interactive use, respectively. Next, the command specifies the volume mount option, nas volume // Ansible, which maps the current directory of your host system to the /Ansible directory within the container. This allows the KICS scanner to access your files for scanning. The core scanning operation is initiated with scan path Ansible /, instructing KICS to analyze the files located in the mounted directory. A key feature of this command is the inclusion of the -report formats HTML flag, which specifies that the scan results should be output in HTML format, making them easier to read and share. Lastly, the -output path Ansible / option indicates where to save the generated report, allowing users to access and review it directly from their project directory. This setup promotes effective reporting and collaboration within development teams. In conclusion, scanning your Ansible playbooks with tools like Checkov and KICS is crucial in building secure and compliant cloud infrastructure. They identify misconfigurations that could lead to vulnerabilities, and they help ensure that your deployment adheres to best practices. By integrating these tools into your development workflow, you can catch issues early and often, making your deployments not only smoother, but more secure. And there you have it. You've learned how to scan your Ansible playbooks using Checkov and KICS, analyze the results, and take corrective actions. With the right tools and approach, your efforts to secure your infrastructure will yield significant rewards. Happy coding, and remember, keep your playbooks clean and secure. Thank you for joining this tutorial, and until next time, keep learning. Now, let's dive into the world of security scans using Checkov and KICS, 2 powerful tools for ensuring the security and compliance of your infrastructure as code. Throughout this tutorial, I'll guide you step by step and inject a little humor along the way. So, grab your favorite beverage, settle in, and let's get started. To start, make sure you have Docker installed, as both Checkov and KICS will run as Docker containers. If Docker isn't your friend yet, don't worry, you can get it running in no time. Just Google Install Docker Desktop for your platform, Windows, Mac OS, or Linux, and follow the straightforward instructions. I would recommend pouring a cup of coffee while waiting for the installation process to complete. After all, security should be fueled by caffeine. To get started with our security scans, we need to clone the repository that contains the Ansible playbooks. By executing the command git clone http://github.com/russmkendrick/learnedansible-2nd edition scan.git, you are pulling the repository from GitHub onto your local machine. This action is akin to bringing home a new puppy, exciting and full of potential. After cloning the repository, it's essential to navigate into the directory using cd Learn Ansible 2nd Edition scan. This step prepares you to work within the project files and sets the stage for the upcoming security processes. Next, we will ensure that we are equipped with the best tools for the job. This is achieved by pulling the latest container image for KICS from Docker Hub, using the command docker image pull /KICS latest. Much like opting for a fresh croissant rather than a stale one, this command guarantees that you are utilizing the latest version of KICS, enabling you to leverage the most up-to-date features and security checks available. By following these steps, you'll be fully prepared to perform effective security scans. To initiate a scan of our Ansible playbooks using the KICS Docker image, we execute a specific command. The command begins with docker container run, which is responsible for creating and starting a new container from the KICS image we pulled. By including the -rm option, we ensure that once the scan completes, the container is automatically removed, preventing any clutter from leftover containers. The -tti option enhances our terminal interaction, allowing us to see the scan's output in a user-friendly manner. Next, we mount our current directory, where our Ansible playbooks are stored, into the container with volume-ansible. This action gives KICS access to our playbooks so it can conduct the necessary scans. Finally, we direct the scan to our playbooks by specifying -path Ansible, which tells KICS exactly where to look for the files. With this setup, KICS can efficiently process our code and provide us with the scan results. The code snippet illustrates the summary output generated by the KICS scanning tool once it completes its analysis of the designated files. The first part of the output, preparing scan assets, done, indicates that the initial setup and preparation for the scan have been successfully completed. Following that, executing queries, 100.000% conveys that all the queries necessary for the scanning process have been executed, with a completion status of 100%, suggesting an efficient scanning operation. Next, the output provides statistics on the scanning process itself. The line files scanned number reveals the total count of files that were analyzed during this operation. Similarly, parsed files number indicates how many of those files were successfully parsed for relevant information. An essential part of the output is queries loaded number, which shows how many queries were ready for execution, while queries failed to execute 0 confirms that there were no execution failures. This detailed summary helps users to quickly assess the effectiveness of the scanning process and the overall health of the codebase being analyzed. In the provided code snippet, we see a description highlighting a potential issue related to file permissions. This is a common concern in software development, where certain modules may inadvertently create files on a disk with overly permissive access rights. When file permissions are too open, it can lead to security vulnerabilities, as unauthorized users might gain access to sensitive information or disrupt normal operations. The description serves as a warning, indicating that the configurations can either be too permissive or unpredictable, which is not ideal for maintaining security best practices. Just as leaving a front door wide open can invite unwelcome visitors, overly open file permissions can result in unauthorized access to critical system resources. To mitigate these risks, it's essential to regularly review and adjust file permissions, ensuring that they are set to the minimum necessary level. Organizations should also stay informed about specific vulnerabilities related to file permissions, as this knowledge empowers developers and teams to implement safer practices and maintain the integrity of their systems. To run Checkov, you'll need to pull its Docker image using a straightforward command. The command docker image pull bridgecrew/check latest is the key here. This command tells Docker to retrieve the latest version of the Checkov image from the Docker Hub, which is a cloud repository for container images. By specifying bridgecrew/Checkov followed by latest, you're instructing Docker to fetch the most recent build of Checkov available, ensuring you have all the latest features and bug fixes at your fingertips. This simple action of pulling the Docker image means you'll create a consistent environment for running Checkov, making it easier to analyze your infrastructure as code. Think of it as downloading an application, but in this case, it's a containerized version of Checkov that will allow you to perform static code analysis on your infrastructure definitions. With this command successfully executed, you're one step closer to becoming adept at using Checkov and enhancing your skills in containerization and infrastructure management. To execute a security scan with Checkov, we leverage Docker to run the Checkov container. The command begins with docker container run, which initiates the Docker container. The flags -rm and -i serve essential purposes. -rm ensures that the container automatically cleans up after it finishes running, preventing clutter on your system, while ttty enhances the output readability by allocating a terminal for the container. Next, we specify -volume./Ansible, which mounts the current directory, where your code is located, into the /Ansible directory inside the container. This setup allows Checkov to access the files it needs to scan for security vulnerabilities effectively. The -workdir/Ansible flag sets the working directory within the container to /Ansible, ensuring that all subsequent commands run in the context of this directory. Finally, bridge crew Checkov indicates the Docker image we are using, which contains the Checkov tool. The directory's Ansible argument instructs Checkov to scan the specified directory for any security issues. By executing this command, you'll seamlessly integrate security scanning into your workflow, helping to identify potential vulnerabilities in your infrastructure as code. The code snippet you see provides a clear summary of the results generated by Checkov after it processes your codebase. It categorizes the checks into 3 distinct groups: passed checks, failed checks, and skipped checks. Each category is critical in assessing the security posture of your code. The passed checks signify the number of security checks that your code has successfully met. This is a positive affirmation of coding practices and indicates the aspects where your code adheres to security standards. Think of these as the gold stars you earn in school, evidence of a job well done. In contrast, the failed checks highlight areas needing attention and improvement. These checks are an opportunity for growth, reminding you that, much like in any learning environment, it's normal to stumble. Recognizing these failures allows you to proactively address security vulnerabilities in your code. Finally, skipped checks refers to the checks that were not processed, either due to specific reasons in your configuration or other factors. Understanding these metrics collectively offers an essential overview of your code's security health and what steps to take next for enhancement. The output message indicates a failure related to a specific resource in your Ansible playbook. tasks.ansible.builtin get URL download wp-cli. This task is intended to download the WordPress command line interface, CLI, which is an essential tool for managing WordPress installations via the command line. However, the process has failed due to a security concern. The root of the issue lies in the use of an insecure HTTP URL for the download. In the context of web security, using HTTP rather than HTTPS poses significant risks, as it does not encrypt the data being transmitted. This vulnerability could potentially allow attackers to intercept the data, leading to man-in-the-middle attacks, where malicious actors can manipulate or eavesdrop on communications between your system and the server. To resolve this failure, it is critical to ensure that the URL used for the download is a secure HTTPS link. By doing this, you protect your system from potential threats and maintain the confidentiality and integrity of your data. Remember, security is paramount, and taking simple steps to secure your connections can make a substantial difference. Now, let's look at this figure. It presents the KICS report generated from the security scan performed on the specified paths in an Ansible environment. The report is time-stamped, marking the start and end times of the scan conducted on January 28, 2024. This level of detail helps you track when the scans were executed and ensures that you are looking at the most recent findings. The vulnerabilities section is the core of this report. It categorizes detected issues by severity: high, medium, low, and info. In this particular instance, you can see that there are no vulnerabilities flagged in any of these categories. Each one shows 0 counts. This is a favorable outcome, indicating that the scan did not detect any significant security risks across the scanned paths. Additionally, the report highlights that KICS is open source, emphasizing its commitment to transparency within the software development community. This feature allows you to review the scanning engine and security queries used in the process, ensuring that you can trust the results and methodologies employed during the scan. As you proceed with your security measures, rely on this report to identify any areas that may need attention, knowing that currently, no issues have been reported. As a quick recap, we've successfully set up and run KICS and Checkov to scan our Ansible playbooks using Docker. Each tool has its strengths and can complement the other, reinforcing the security of our infrastructure. If there's one thing you should take away from this tutorial, it's that proactive security measures will save you time and headaches in the long run. Regularly running security scans as part of your CI/CD pipeline will become a best practice you won't want to skip. Now, you're well on your way to becoming savvy at utilizing Checkov and KICS. If you're looking to further enhance your pipeline security, consider integrating these tools into your CI/CD processes. It's like having your security guard on duty 24/7. That's all for today. If you found this tutorial helpful, give it a thumbs up, and don't forget to subscribe for more tutorials that keep your skills sharp while ensuring your infrastructure is as secure as Fort Knox. Until next time, happy scanning. In this chapter, we generated a playbook to remediate any CIS Level 1 non-compliance errors found during a scan. By utilizing Ansible, we gain a powerful tool that not only automates server hardening, but also ensures that the compliance status of your servers is regularly monitored and corrected without manual intervention more efficiently than doing it manually. Picture this. You are the system administrator of a growing company, and let's say you've got a dozen servers. Each minute you spend manually checking compliance is a minute that could be spent on more innovative projects. That's where automation comes in, and in this case, Ansible takes the lead. Before we dive deeper, let's familiarize ourselves with the CIS benchmarks. The Center for Internet Security, CIS, provides a set of guidelines to secure IT systems and data. The Level 1 benchmark is essentially the minimum security configuration for systems. It's crucial for ensuring essential defenses are in place. To begin automating the remediation of compliance issues, we first need to ensure that the necessary tools are installed. The command provided, sudo apt-get update and in sudo apt-get install -y ansible OpenSCAP utils, serves this purpose. The sudo apt-get update command refreshes the local package index, ensuring that our system is aware of the latest available packages and their versions. This is a crucial step before installing new software, as it promotes a smoother installation process. Following the update, the command proceeds with the installation of both Ansible and OpenSCAP utilities. The install command, accompanied by the Y flag, automatically confirms the installation prompts, allowing the process to run without further user interaction. Ansible is a powerful automation tool that enables us to define infrastructure as code, while OpenSCAP provides the capabilities to assess and enforce compliance with security standards. Together, these tools will enable us to create an Ansible playbook that automates the remediation of any compliance findings, streamlining our efforts to maintain security compliance across systems. The Ansible playbook begins with a specific declaration, indicated by the name Audit and Remediate CIS Level 1 Compliance. This name sets the intention for the playbook, which focuses on ensuring compliance with CIS Level 1 standards. The target hosts specified as Yorker target hosts determine where the tasks will be executed, making it essential to replace this with actual host names or groups defined in your inventory. To facilitate the execution of tasks that may require elevated privileges, the directive Become True is included. This allows Ansible to run the subsequent tasks with superuser permissions when necessary, ensuring that actions such as creating directories can be performed without permission issues. The first task in the list is crucial. It verifies and ensures the existence of a designated output directory for audit results. The task is named Ensure the local output directory exists, and it utilizes the Ansible file module. The defined path, /scap results, is where the results of the compliance checks will be stored. Setting the state to directory confirms that the directory will be created if it does not already exist, while the specified mode of 0755 ensures appropriate permissions for accessibility and security. To generate your remediation playbook with OpenSCAP, you first need to gather necessary model definitions. This involves accessing the SCAP security guide that corresponds to your operating system. For Ubuntu, you can find the relevant model definitions stored in XML files on your system. The command you need to execute is oscapinfo/usrshare xml/scap ssg ubuntu 2004-.xml. When you run this command, OpenSCAP retrieves important information about the SCAP content, specifically the document associated with Ubuntu 20.04. This includes available compliance profiles, which define various security benchmarks that your system can adhere to for compliance verification. After executing the command, you will see a list of all the profiles available for your use. You can select a suitable profile based on your specific security needs or operational requirements. For example, xccdf.org.ssg project.content profile cs level 1 server is a commonly used profile that focuses on securing server environments according to the CIS standards. This selection process is crucial for creating an effective remediation playbook tailored to your system's security posture. The command you will be using to assess your system's compliance is structured to leverage OpenSCAP's powerful evaluation capabilities. In this specific case, the command initiates an evaluation against the predefined profile, which is identified as xccdf.org.ssg project.content profile cs level 1 server. This profile is tailored for benchmarking against the security standards established for level 1 server configurations, making it a suitable choice for enhancing the security posture of your systems. The command has two key outputs. It generates an ARF assessment results format, file named arf.xml, and a detailed HTML report called report.html. The ARF file provides a structured representation of the evaluation results, which can be useful for automated processing or integration with other tools. On the other hand, the HTML report presents the results in a user-friendly format, allowing for easier human review. This report will help you quickly identify both compliant areas and those that require attention, offering actionable insights to improve your system's security compliance. Overall, this tool is invaluable for maintaining and demonstrating compliance in complex IT environments. To create a remediation playbook using OpenSCAP, we employ a specific command that generates an Ansible playbook tailored to address compliance issues identified during a security assessment. The command begins with oscap xccdf generate fix, which indicates that we are using OpenSCAP's functionality to generate a fix based on the xccdf specification. The use of generate fix signifies our intention to create a remediation solution. We include the option --fetch remote resources to enable OpenSCAP to automatically download any required resources that might not be available locally. This ensures that the playbook is comprehensive and can execute all necessary fixes. The next portion of the command, fix type Ansible, specifies the type of output we desire, indicating our choice to produce an Ansible-compatible playbook. Ansible, being a powerful automation tool, allows us to implement the required changes efficiently. The result ID parameter remains empty here, which implies that it is not being used to filter or specify a particular result from a compliance check. Finally, we direct the output to a file named remediationplaybook.yml, which will contain all the remediation tasks derived from the compliance findings, enabling us to streamline the process of bringing our systems into compliance. In the provided snippet of the remediation playbook, we see a specific Ansible task that focuses on ensuring proper file permissions for the /etc/passdolt file. The task is labeled ensure permissions on /s/passdolt are correct, which clearly indicates its purpose. The code under this task uses the ansible.builtin.file module, a core module in Ansible that manages file properties. In this instance, the task specifies the path to the file, which is /at/passdolt, a critical file in Unix-like systems that contains user account information. By setting the owner and group parameters to root, the playbook ensures that only the root user has ownership over this sensitive file. Additionally, the mode parameter is set to 0644, which permits the file's owner to read and write while allowing group members and others to read but not modify it. This configuration aligns with the CIS benchmark recommendations for securing system files, helping to minimize potential security vulnerabilities related to unauthorized access or malicious alterations. To execute your remediation playbook, you will use the command Ansible Playbook remediation playbook.yml. This command is fundamental in leveraging Ansible's automation capabilities. By running it, you instruct Ansible to apply the configurations defined within the remediation playbook.yml file to your target environment. Before you execute the command, ensure that Ansible is properly configured on the target host. This involves setting up the Ansible control node and ensuring that the target machines are accessible and correctly defined in your inventory. Once you have navigated to the directory where the playbook resides, executing this command becomes a straightforward process. As the playbook runs, it automates various tasks to bring your environment into compliance based on the configurations specified in the YAML file. This automation significantly reduces the time and effort involved in manually adjusting settings, enabling a more efficient management of your infrastructure. Consequently, by relying on this playbook, you can maintain the desired state of your systems with improved consistency and reliability. After you've completed your remediation process, it's essential to verify that all previously identified vulnerabilities have been addressed. This is where the OpenSCAP tool comes into play. The command you'll employ is structured to evaluate your system's security compliance against a specific profile. The command begins with oscap xccdf eval, which indicates that you are evaluating an xccdf extensible configuration checklist description format document. Next, you specify the profile you wish to use for the evaluation. In this case, xccdf.org.ssgproject.content.profile sys level 1 server is chosen, which aligns with the CIS level 1 benchmark for Ubuntu servers. This ensures that you're assessing your system according to recognized best practices. Additionally, the command outputs results to two files, arf.xml, which contains the scan results in the automated reporting format, and report.html, a more human-readable format for easier review. Finally, the command specifies the path to the SCAP data stream, located at /us/share xml s//ssg ubuntu 2004.xml, which contains the rules and checks that will be used during this evaluation. By running this command, you're effectively capturing the current compliance state of your system and setting a baseline for improvement. Before concluding, I find it noteworthy that Ansible not only allows you to remediate existing issues, but also provides a framework that enables continuous compliance monitoring. By integrating features like Ansible Tower or OX, you can schedule these compliance checks, alerting you whenever new non-compliance issues arise. Then again, you might also leverage CI/CD pipelines to ensure that your configurations are compliant before pushing code to production. So, here we are, master tutors of our servers. Ansible, paired with OpenSCAP, allows us to not just monitor but also effectively manage our server's compliance posture while spending less time on managing and more time innovating solutions. Remember, automation is your friend, and in infrastructure management, it's more than a convenience, it's a necessity. Now go ahead and harden those servers like a pro. To create an engaging video script on the topic of automating Ansible playbook runs with GitHub Actions and Azure DevOps, let's dive into the technology while keeping the tone light and educational. This will allow us to effectively explain the processes and techniques involved while keeping our viewers involved. Running Ansible playbooks automatically is not just a cool trick, it's a game changer in the realm of DevOps. Today, we're going to explore how we can integrate our beloved Ansible with GitHub Actions and Azure DevOps to automate running our playbooks. Are you ready? Let's get started. Now let's look at this figure. It displays a GitHub repository titled Learn Ansible 2nd Edition, Chapter 15. This interface provides us with an overview of the repository, which is currently set to private. The top section features navigation tabs like Code, Issues, Pull Requests, Actions, Projects, Wiki, Security, Insights, and Settings, allowing users to easily interact with the various aspects of the repository. You will notice the prominent Code section, which is where users can clone the repository or explore its contents. Below this, there are options to start coding with code spaces, where users can create a secure development environment directly within the GitHub interface. The prominent button invites users to create a code space, highlighting GitHub's capability of providing an integrated development environment. At the bottom of the figure, we see a quick setup prompt that guides users on how to get started with the repository. It suggests options for setting it up via desktop app or through HTTPS and SSH links. This information streamlines the process for users who may have previous experience with GitHub, ensuring they quickly understand how to clone or contribute to the repository. The note about including a README, license, and .gitignore emphasizes best practices for maintaining a well-structured repository from the outset. Overall, this figure serves as an important visual aid in our discussion about leveraging GitHub for running Ansible playbooks effectively, emphasizing cloud-based collaboration and streamlined development workflows. In this GitHub Actions workflow, we define a process that automates the execution of an Ansible playbook whenever there is a push to the main branch. The workflow begins with a name declaration indicating its purpose, followed by an event trigger that specifies it will initiate on pushes to the main branch. The Jobs section outlines the tasks to be executed. Here we have a job named Run Ansible that runs on the latest version of Ubuntu. The first step in this job is to check out the code using the actions/checkout at v2 action, which retrieves the content of the repository at the moment of the push. This step is essential as it prepares the environment with the latest code base before executing the subsequent tasks. Next, we set up the Python environment necessary for the playbook execution. This is done through the actions/setup Python at v2 action, where we specify that Python version 3.8 should be used. This configuration ensures that the required Python version is available for any scripts or applications that may be run as part of our Ansible automation. Overall, this workflow establishes a robust foundation for automating tasks in response to code changes in the repository. The provided code snippet is part of a GitHub Actions workflow designed to set up Ansible and its required dependencies. In this specific step, the workflow begins by installing Ansible, which is a powerful automation tool used for configuration management, application deployment, and task orchestration. It utilizes the Python package installer, pip, to perform the installation. The command python mpip install Ansible ensures that Ansible is installed in the environment where the workflow is executed. Following the installation of Ansible, the snippet installs the Azure Ansible collection using the command Ansible Galaxy Collection install azure.az collection. This collection is essential for users looking to manage Azure resources seamlessly with Ansible. By incorporating it into the workflow, you're allowing Azure management tasks to be automated within your playbooks, enhancing efficiency. This step essentially lays the groundwork for your automation tasks, ensuring you have both Ansible and the necessary Azure tools ready for use. With this configuration complete, you're set up to deploy and manage Azure resources effectively using Ansible playbooks. In this section, we focus on executing our Ansible playbook using a command within our GitHub Actions workflow. The key line of code here is the instruction to run the Ansible playbook. Ansible-playbook-inventory.ini playbook.yml. This command specifies two critical components, the inventory file and the playbook itself. The -i inventory.ini tells Ansible where to find the inventory file, which contains the list of servers and hosts that the playbook will target. By clearly defining this, we ensure that our tasks will be executed on the intended machines. The second part of the command, playbook.yml, refers to the Ansible playbook that outlines the tasks to be performed on those specified hosts. By integrating this command into our GitHub Actions workflow, we automate the deployment process. This means that every time a change is pushed to the main branch of the repository, the defined playbook runs automatically, allowing for seamless updates and management of your infrastructure. Essentially, this process simplifies and streamlines operations, making it a powerful addition to any development workflow. In the provided YAML configuration for Azure DevOps, we start by defining a trigger, which is crucial for automating our pipeline. The trigger specifies that the pipeline should run whenever there are changes pushed to the main branch. This ensures that our application is always built and tested in response to the latest code modifications. Next, we specify the pool, which determines the environment our pipeline will run in. In this case, we are using an Ubuntu-based virtual machine image by setting VM image Ubuntu latest. This selection provides us with a reliable Linux environment, which is commonly used for various CI/CD processes. Moving on to the steps section, the first action is to check out the repository's source code with the command checkout self. This step is essential as it fetches the code that triggered the pipeline, enabling subsequent tasks to run on the latest version. Finally, we have a task that utilizes a specific version of Python. The Use Python version at 0 task is set to use Python 3.x, ensuring that the correct Python interpreter is available for the build process, allowing us to execute any scripts or applications written in Python seamlessly. The first part of the code is a script that installs Ansible and the necessary Azure collections. It begins by using Python's package manager, pip, to install Ansible, ensuring that you have the latest version available for automation tasks. Following Ansible installation, the script utilizes the Ansible Galaxy command to install the Azure collection, Azure.az collection, which provides modules and roles to manage Azure resources. This step is crucial for integrating Azure with Ansible and allows for seamless automation of deployments. The second part of the code is responsible for executing the Ansible playbook. The command Ansible Playbook-I inventory.ini playbook.yml specifies the inventory file and the playbook to be run. The inventory file, inventory.ini, lists the servers or cloud resources to be managed, while playbook.yml contains the automation tasks defined to be executed on those resources. This execution step brings together all the configurations and setups into action, effectively allowing you to deploy and manage cloud resources through Azure DevOps using Ansible, enhancing the efficiency and reliability of your automation workflows. But wait, there's something crucial we should cover. Security. When using either platform, you likely want to manage your secrets like your Azure credentials or SSH keys. With GitHub Actions, you can securely store these in the repository settings under Secrets. Similarly, Azure DevOps has a section for Library where you can define your variables securely. Now, real quick, let's take a moment to check the output logs from both GitHub Actions and Azure DevOps after the run's complete. Whether it's GitHub or Azure DevOps, there are visual options available to help you monitor the status of your playbook runs. Both platforms will show you detailed logs so you can easily troubleshoot any issues. Wouldn't it be nice to have the ability to run a scanner for security vulnerabilities like KICS within our pipelines? That's a fun little bonus you could implement. KICS can be set up as another step in your workflow or pipeline, giving you insights into your code's security before deploying anything. It's kind of like seeing a spell check before you submit your report. So let's recap. Today we've learned how to automate the execution of Ansible playbooks using GitHub Actions and Azure DevOps. We covered the step-by-step creation of workflows and pipelines, and we even touched on security practices for managing sensitive information. Remember, automation is your friend, and these tools can save you tons of time while ensuring consistency and reliability in your deployments. As we wrap up, I hope you found this tutorial not only informative but also exciting. If you have any questions, more topics you want to discuss, or just feel like sharing your own experiences, feel free to comment below. Remember to like, share, and subscribe for more awesome content. See you next time, and happy automating. The provided code snippets demonstrate how to deploy the AUX operator on an Azure Kubernetes service AKS cluster using Helm. The first part of the code instructs you to add the AUX operator repository to your Helm configuration. By running the command helm add AUX operator app.ansible.github.io/AUX operator/, you are informing Helm where to find the AUX operator charts. Following that, the Helm repo update command refreshes your local Helm repository cache to ensure you have the latest charts. Next, the Helm install command is executed to deploy the AUX operator in a new namespace called AUX. The parameters include -n-AUX to specify the namespace and -create namespace to automatically create it if it does not exist. Finally, this command installs the AUX operator with a specific version 2.12.1, which ensures compatibility and stability in your deployment. After initiating the deployment, it's essential to monitor the pod status. The second command, kubectl get pods abex, allows you to check the status of the running containers, where you should see various components, including the database and web interface, initializing successfully. To deploy the Ansible AWX, you need to create a YAML configuration file that clearly specifies how AWX should be set up. This configuration begins with the API version and the kind of object you are creating, which in this case is an instance of AWX. The metadata section, including the name and namespace, identifies your AWX deployment within the Kubernetes environment. The specification details the service type, indicating that you want AWX to be externally accessible via a load balancer. Once your configuration file is ready, you apply it using the kubectl apply command, followed by the URL of your YAML file. This instructs the Kubernetes cluster to process the file and set up the AWX instance according to your specifications. After deploying, you'll need to retrieve the admin password for your AWX instance to access the dashboard. This is done using a kubectl get secret command, which extracts the admin password from the Kubernetes secrets in the AWX namespace. The password is base64 encoded, so an additional pipe is used to decode it, ensuring you have the necessary credentials to log in and manage your new AWX environment efficiently. Now let's look at this figure. It displays the terminal output from a command that installs the AWX operator using Helm. The command executed is helm install AWX create namespace a-operator /AWX version 2.11. This command is crucial for setting up AWX in a Kubernetes environment, creating a dedicated namespace for it in the process. The output provides key information regarding the installation status. It indicates that the AWX operator was successfully deployed as of March 25, 2024. The namespace field shows that the AWX components are functioning within the AWX namespace. The status field confirms that the deployment is currently running, and further details about the revision and associated notes highlight that the AWX operator has been installed with a specific Helm chart version. Additionally, the command kubectl get pods and AWX demonstrates the next step in verifying the installation. The listing shows the names of pods within the AWX namespace and confirms that the AWX-operator controller manager pod is currently running, with a readiness state of 2.5, indicating both containers within the pod are operational and ready to manage AWX resources. This information is critical for ensuring the deployment is correctly configured before proceeding with further automation tasks in your Azure environment. Now that we have our project set up, it's time to configure the necessary credentials that AWX will use to access Azure. Click on Credentials and hit the Add button. Fill in your Azure details, such as the subscription ID and service principal credentials. This grants AWX access permissions to deploy resources in Azure. You will also need to add the private SSH key for Azure VMs, as well as any vault passwords if you are encrypting sensitive information. Fill in the respective fields, and make sure to click Save after each addition. That's a lot of configuration already, right? Don't worry, we will reward ourselves once we finish setting everything up. Let's not forget about inventories, which are crucial in managing your Azure hosts. In AWX, go to Inventories and click on Add Inventory. For the inventory details, use Name, Azure Inventory, Description, Azure. Once created, we can add groups within this inventory to organize our machines. Navigate into your newly created inventory and click Groups to add different groups, such as VM Group for managing your Azure virtual machines. Now our inventory is ready, and it's time to incorporate the actual playbooks. AWX allows you to create job templates that define how to execute playbooks against your inventory. Go to Templates, click Add, and select Job Template. Fill in the job template form with the name for our deployment, referencing the playbooks we pulled in earlier. Ensure to link the inventory and project defined previously. Once the templates are configured, you can run your playbook to deploy resources in Azure directly from the AWX interface. Simply click the launch icon next to your job template, and you'll be able to monitor the status of the playbook run. If everything runs smoothly, you should see confirmation that your resources have been created in Azure within just a few moments. It's like magic, only more technical and certainly less sparkly. In summary, we have gone through the complete process of setting up Ansible AWX on Kubernetes in Azure, configured necessary projects, credentials, and inventories, and finally executed our playbook to deploy a WordPress site on Azure. Remember to explore AWX functionality further and practice creating more complex workflows. As we wrap up this exploration of Ansible AWX, it's essential to reflect on the advantages and potential limitations of this powerful tool. Ansible AWX stands out due to its open-source nature, community-driven development, and ease of use compared to traditional CLI methods. However, when it comes to large-scale enterprise environments, there might be limitations that require the backing of the commercial Red Hat Ansible automation platform. Before we finish, let me leave you with a little tidbit. Always stay updated. Ansible AWX has a frequent release cycle, providing continual access to new features and enhancements. Just make sure to manage updates mindfully to avoid disrupting your production environments. Thank you for joining me on this journey through Ansible AWX. Hopefully, you'll now feel equipped to tackle Azure deployments with confidence and infuse your automation strategies with efficiency. Until next time, happy automating! In this, our final chapter, we will discuss how you can integrate Ansible into your day-to-day workflows. Ansible is a powerful automation tool that can streamline your operations, and the aim here is to show you how to take full advantage of it. We'll cover a variety of topics, including continuous integration tools, monitoring tools, troubleshooting strategies, and some real-world examples of using Ansible effectively. How many of you have wondered what happens after you've created some great playbooks? What next? Well, you can integrate them into your daily processes to enhance your team's productivity. Imagine running complex deployments or updates across multiple machines without breaking a sweat. Often, automation is not just about doing tasks. It's about enhancing collaboration, maintaining integrity, and ensuring your infrastructure runs smoothly. To get started with integrating Ansible and Slack, the first step is to install the necessary Ansible collection that includes the Slack module. The command you need to run is Ansible Galaxy Collection install community.general. This command utilizes the Ansible Galaxy tool, which is a repository for Ansible roles and collections, to install the community.general collection. This collection contains a wide array of modules, including those that allow Ansible to interact with third-party services like Slack. By installing the community.general collection, you're ensuring that you have the latest features and bug fixes, thus enhancing your automation workflows. It's a straightforward command that you should execute in your terminal or command prompt where Ansible is installed. Once this installation is complete, you can move on to configuring a Slack app and setting up incoming webhooks. This process will enable your Ansible playbooks to send notifications directly to your selected Slack channel, allowing your team to stay informed about job statuses in real time. In this segment, we focus on how to configure notifications for Slack using a simple Ansible playbook. The code snippet provided sets up a task that sends a message to a Slack channel, effectively keeping your team informed about the status of resources. The task is defined under the name Notify the team on Slack about resource status, which clearly indicates its purpose. A key component of this configuration is the use of the community.general.slack module, which facilitates communication with the Slack API. The token field is essential, as it authenticates your requests to Slack. Here, it leverages a securely stored token, represented by slack.token, ensuring that sensitive information is not hard-coded in the playbook. The message itself is crafted using the attachments attribute, which enhances the formatting and visual appeal of the notifications. The attachment includes a title that specifies Ansible task status and a message stating the playbook has completed running. Additionally, the color field is set to good, which helps communicate a positive outcome visually. This attention to detail not only keeps the team informed, but also embeds best practices around security and message clarity in automated workflows. In this code snippet, we are executing a health check on a web application using Ansible's URI module. The task begins with the name Check Application Health, which clearly indicates the purpose of this action. The URI module is used to make an HTTP request to the application, specifically a GET request to the /health endpoint on port 8080 of the target host. By referencing inventory host name, we ensure that the check is dynamically performed on each host listed in our inventory. The return content yes parameter tells Ansible to capture the response content from the HTTP request. This response will be stored in a variable named health check, allowing us to analyze it later in the playbook. After the playbook runs, and if any issues arise, these results will help us determine whether the application is functioning as expected. If the health check variable indicates a failure, immediate alerts can be configured, enabling prompt troubleshooting and remediation of any potential problems. This process creates a robust monitoring strategy to ensure application reliability post-deployment. In this sample playbook, we begin by defining a play that targets the local host. The core objective here is to demonstrate the use of Ansible's built-in debugger to troubleshoot issues effectively. The playbook consists of a single task designed to intentionally cause an error. This task employs the debug module to print a simple message. By using the register keyword, we capture the output of this task into a variable named result. However, the key feature highlighted in this playbook is the debugger onFailed directive. This directive instructs Ansible to drop into an interactive debugger session if the preceding task fails for any reason. This functionality acts like a safety net, allowing users to inspect live error contexts and troubleshoot effectively. In essence, if something goes wrong during task execution, you can immediately interact with the debugger, gaining insights into the issue and the playbook's current state. This is an invaluable tool for developers, especially when dealing with complex playbooks where understanding the context is crucial for resolving issues. The code snippet provided illustrates an Ansible playbook task designed to fetch logs from a remote server. The task is initiated with a descriptive name, fetch logs from the remote server, which clearly indicates its purpose. Following that, the fetch module is employed to achieve this goal. The src parameter specifies the source file path, which in this case is var log application.log. This is the log file that is typically critical for troubleshooting application issues. The dest parameter indicates the destination directory on the control node set to /tmp log/. This is where the fetched logs will be stored locally for further analysis. Finally, the flat option is set to yes, which means that the directory structure is not preserved and the log file will be saved directly in the specified destination. This playbook task streamlines the process of log retrieval, enabling administrators to quickly access relevant logs without manual intervention, thus enhancing efficiency in the troubleshooting workflow. In the provided code snippet, the use of roles in Ansible playbooks becomes evident. Each role represents a specific component of the application that needs configuration, allowing for organized and modular deployments. The lines you see, starting with -include role, indicate that we are integrating distinct roles into the playbook sequentially. The first line, -include role name database, specifies that the database role should be included. This role would contain all the necessary tasks and configurations required to set up and manage the database component of the application effectively. Next, -include role aim cache server follows the same structure, bringing in the cache server role, which encapsulates logic for configuring the caching mechanism critical to application performance. Lastly, the line -include role name application server adds the application server role, integrating the main application services. By structuring the playbook in this manner, each component is modularized, promoting clarity and reusability. It allows developers to manage complex application deployments more effortlessly, as configurations and tasks are neatly organized within their respective roles. Lastly, I want to emphasize the true power of community contributions and acceptance of innovations through Ansible Galaxy. It's where you can find roles and collections that others have built and shared, which can dramatically speed up your development. Instead of reinventing the wheel, you can look at how tasks were tackled by others in the community and utilize those roles in your own playbooks. Get strolling through Ansible Galaxy. New ideas could be lurking around every corner, and they just might be the spark of brilliance you're looking for. As we draw this chapter to a close, We hope you see that the possibilities for integrating Ansible into your daily workflows are practically endless. By utilizing third-party integrations, monitoring, troubleshooting, and effective deployment strategies, you can simplify operations, ensure smoother workflows, and ultimately deliver better applications and infrastructure. And there you have it. From the integration of notification systems like Slack and monitoring tools, to employing robust troubleshooting processes and sharing resources through Ansible Galaxy, the journey with Ansible is just beginning. Embrace these capabilities and watch your automation soar. So, all aboard this automation train, and let's roll toward greater efficiency together. At its heart, Ansible is a simple framework that pushes a small program called an Ansible module to target nodes. Modules are the unsung heroes of automation, quietly doing the heavy lifting without much fuss. Picture modules as tiny building blocks. They are small scripts designed to perform specific tasks on the nodes you're managing. Think of them as your little helpers that wake up when you need something done, and then quietly retreat back into the shadows once the job is complete. This unique push mechanism allows Ansible to operate without agents on the target nodes, keeping your system clean and clutter-free. Ansible's simplicity is one of its most endearing features. You don't need to install any agent software on the target machines, which sets it apart from many competing tools. Instead, Ansible communicates over standard protocols like SSH or WinRM, utilizing existing systems without requiring any special handling or additional installations. This is like showing up to a party without needing to bring anything along, just your charming personality and your knowledge of automation. Now let's look at the figure. This illustration represents the architecture of Ansible's automation engine, outlining its key components and how they interact. At the center, we have Ansible's automation engine, which acts as the core that integrates everything needed for efficient automation. On the left, users are depicted interacting with Ansible Playbooks. This indicates how users initiate automation tasks through Playbooks, which serve as scripts outlining the desired configurations or state changes. These playbooks are essential for defining the steps Ansible will take. Moving towards the center, the figure highlights several vital elements of the automation engine. The inventory component is crucial as it holds information about the hosts being managed. This dynamic inventory management allows for real-time updates in response to changes in the infrastructure, effectively ensuring Ansible has the latest view of resources. Next, we see the API symbol, which facilitates communication between Ansible and other systems. This feature allows for integration with external services, further enhancing Ansible's functionality and automation capabilities. Two additional components are modules and plugins. Modules are the building blocks of Ansible operations, executing specific tasks on target hosts. Meanwhile, plugins extend Ansible's capabilities, providing customization through connection options, logging formats, and more. This flexibility enables users to tailor their automation experiences to meet specific needs. Finally, the figure also depicts the interaction with hosts and networking, showcasing how Ansible connects to various infrastructures, whether in public or private clouds. This comprehensive view illustrates the interconnected nature of Ansible's ecosystem, highlighting its adaptability and powerful automation capabilities. Now let's talk about the pièce de résistance, Playbooks. Playbooks are where Ansible shines the brightest. They are YAML files that define the tasks you want to execute on your nodes. With Playbooks, you can orchestrate complex automation across multiple machines, bringing a symphony of cooperation to your automation efforts. They allow you to define various tasks, manage configurations, and deploy applications, all in a way that's readable and maintainable. But don't let the simplicity of YAML fool you. This format packs a powerful punch. The structure is straightforward enough for anyone to pick up quickly, yet it is capable of expressing intricate sequences of operations. When you start writing your playbooks, you'll likely find yourself channeling your inner Shakespeare, crafting stories of automation that bring order to the chaos of IT operations. Now let's look at this figure, which illustrates the command line help interface for Ansible. This interface provides users with an overview of the various options available when executing Ansible commands. The initial command, Ansible help, prompts the interface to display a range of flags and arguments. Each option is detailed with its specific purpose, which allows users to customize their Ansible experience. You'll notice a set of common options at the top, including flags like -h for help, -version for displaying the version number, and -b for becoming another user. These flags are essential for users to understand the capabilities of the Ansible command line. Following this, various parameters such as inventory, poll interval, -p, and timeout settings provide additional control over how tasks are executed, emphasizing the flexibility of Ansible in managing automation tasks. Moreover, the figure highlights advanced options for users with specific needs. Options like bash private key, bash u for remote user specification, and bash ssh common args are available for fine-tuning the connection and execution settings. This detail showcases Ansible's dynamic capabilities, allowing you to adjust parameters based on your operational requirements, similar to altering ingredients for a perfect recipe. In essence, this figure serves as a key resource for understanding the breadth of control Ansible provides. It illustrates the framework within which users can operate, making it clear how to leverage the command line to execute automated tasks effectively. This playbook snippet showcases a straightforward approach to installing Apache on a group of specified hosts. The first line begins with 3 dashes, which indicates the start of an Ansible playbook. Following that, the -name install Apache line provides a brief description of the playbook's overall purpose, helping users quickly grasp its intent. The host's web servers directive specifies the target machines on which the tasks will be executed. In this case, web servers is a group defined within the Ansible inventory, meaning that all machines in this group will be affected by the subsequent tasks. The tasks section outlines the actions to be performed on the specified hosts. Here, the first task is named Update Apache, which clearly describes what the task aims to achieve. The task utilizes the ansible.builtin.app module, designed for managing packages in Debian-based systems. By specifying name Apache 2 and state latest, the playbook ensures that the Apache web server package is installed and updated to its most recent version. This encapsulates a clear and efficient method for automating web server installation with Ansible. Now, one of the defining features of Ansible is the state management of your systems. Ansible is designed with the philosophy that tasks should only make changes when necessary. When you run a task like the one above, Ansible checks if the current state matches the desired state. If Apache is already up to date, it will simply report OK. However, if it needs to perform an update, it will report changed. This leads to a more efficient and reliable infrastructure, as unnecessary changes and potential service interruptions are avoided like the plague. Imagine running a caterer for your party who only brings out the food that guests actually want to eat. If nobody's going for seconds, they won't refill the buffet. This attention to detail keeps your systems running as smoothly as your perfectly planned dinner party. As you get more adventurous with Ansible, you'll want to delve into some advanced topics such as roles and collections. Roles allow you to further decompose your playbooks, organizing them by functionality, making it easier to reuse code and collaborate on automation. Think of roles as mini playbooks that you can plug in and out of your larger playbooks, like modular furniture pieces, super flexible. Collections, on the other hand, provide a way of grouping various Ansible content like roles, modules, and plugins. This is particularly useful when working on larger projects or within teams, as it helps maintain consistency and simplifies distribution. It's like putting all your kitchen tools neatly into a designated drawer, rather than scattering them throughout the house. Now let's look at this figure that illustrates the architecture of Ansible in a multi-site setup. On the left side, we have Ansible Site 1, which is designated as the active site, and it contains the automation controller and a private automation hub. Each component is structured with a cluster consisting of 3 nodes. This robust configuration ensures high availability and load distribution among the active nodes. Moving to the right side, Ansible Site 2 functions as the passive site, paralleling the setup of Site 1. It also includes a cluster with its own automation controller and private automation hub, ensuring redundancy and failover capabilities. Both sites utilize PostgreSQL databases for storing essential data, which helps maintain a consistent state across environments. At the center, we see an automation mesh connecting the various components. This mesh enables communication and data exchange between execution nodes 1 and 2 across both sites. This architecture not only facilitates efficient task execution, but also enhances the overall resilience of your automation framework. On the lower part of the figure, there are Git repositories for both the automation controller and the private automation hub. These repositories enable version control and help manage the scripts and playbooks that drive automation. Additionally, the figure highlights the replication processes via webhooks, ensuring data integrity between the PostgreSQL databases across both sites. Lastly, a centralized logging mechanism is depicted, which consolidates logging data from all sites and components. This feature is crucial for monitoring and troubleshooting, providing a comprehensive view of operations and performance across your Ansible environment. As you engage with this setup, remember that understanding this architecture will empower you to leverage its full potential in automating your IT operations. Congratulations, you now have your very first Ansible playbook. This is a moment to celebrate as you're stepping into the world of automation and configuration management. Today, we're diving deep into the creation of your initial playbook, which is a foundational aspect of using Ansible effectively. A playbook in Ansible is essentially a blueprint of how to achieve a certain task or set of tasks on your servers. With this playbook, you'll be able to manage your web servers more efficiently. The playbook you're about to run will iterate through all the web hosts in your inventory. It will check if the Apache web server package, Apache 2, is installed or needs updating, and then only restart the service where changes are made. Simple enough, right? But let's break it down step by step. The first line of the code starts with 3 dashes, which is a key indicator in YAML that signifies the beginning of a document. This is essential for any YAML file, as it informs both humans and machines that the content that follows is structured data. Following the header, we have a list item marked with a dash, which is standard YAML syntax for defining elements in a list. Next, we encounter the keyword name, which defines the playbook's name. In this case, it is called My First Ansible Playbook. This name is essential, as it provides a clear and descriptive label for the task the playbook is intended to accomplish, making it easily identifiable in larger projects. The line hosts all specifies the target hosts for this playbook. By stating all, this means that the instructions contained within the playbook will be executed on every host listed in your Ansible inventory file. This plays a crucial role in ensuring that automation tasks can be performed across multiple servers seamlessly, without any additional configuration needed for specific hosts. In this segment, we incorporate administrative privileges with the line become yes. This configuration signifies that the tasks following this line will be executed with superuser permissions, essential for actions like installing or updating software packages that require elevated access. Next, we define the tasks to be carried out within the playbook. The segment tasks signals the beginning of our task definitions. The subsequent line, which begins with name, serves as a brief description, clearly stating that this task is focused on installing or updating the Apache web server to its latest version. We then specify the Ansible module used for package management, ansible.builtin.apt. This particular module is designed to manage packages on Debian-based systems, including Ubuntu. The name parameter indicates the package to be affected, in this case, Apache 2. The directive state latest ensures the package is always kept up to date, installing it if it's not already present. Finally, the notify clause ensures that the Apache service is restarted only if the installation or update causes a change, thereby promoting efficient service management. In this section, we focus on handlers, an essential feature in Ansible that enhances the efficiency of your automation tasks. Handlers are distinct from regular tasks because they are only executed when notified by another task, typically following a change. In our example, we have a handler defined to restart the Apache service, ensuring that any updates or installations to the service take effect immediately. The handler is specified under the Handlers section of the playbook, highlighting its unique purpose. The mash name attribute clearly describes the task as restart the Apache web server, which makes the playbook more readable and maintainable. Following that, we utilize the ansible.builtin.service module to manage the service. Here, we indicate the specific service we want to control by setting the name parameter to Apache 2. Finally, the state parameter is set to restarted, which instructs Ansible to restart the Apache service whenever it receives a notification from the preceding tasks that modify or install the Apache server. This ensures that any changes are immediately applied, resulting in a smoother and more efficient deployment process. To execute your Ansible playbook, you will utilize the Ansible Playbook command, which is the primary method for running automation scripts using Ansible. The command begins with Ansible Playbook, followed by several options that customize its behavior. The first option, iHosts, directs Ansible to your inventory file, which lists the hosts that the playbook will target. Proper configuration of this inventory file is crucial, as it defines the environment where your playbook will operate. Next, the -limit web option plays a vital role in scope management. By using this parameter, you can restrict the execution to only those hosts whose names start with web. This allows for focused updates and changes, ensuring that only the relevant systems are affected, which can be particularly useful in large environments with multiple host types. Finally, you specify the playbook file you want to execute, in this case, playbook.yml. When you run this complete command, Ansible springs into action, gathering facts about each designated host. It will then proceed to install or update Apache as necessary and restart the service only if updates were made, all done effortlessly with a single command. Now let's look at the figure. This diagram illustrates the architecture of an Ansible setup, highlighting the relationship between the Ansible management node, playbooks, inventory, and host groups. At the top, we have the Ansible management node, which serves as the central point for executing tasks and managing configurations across multiple hosts. The figure shows that the management node interacts with both playbooks and inventory. The playbook is an essential component that defines the tasks to be executed on the managed hosts. It outlines what needs to be done, such as installing or updating software, configuring services, or managing files. Below the management node is the inventory, which lists the hosts under specific groups. In this case, we see two groups, Group A and Group B. This logical grouping helps in organizing hosts based on roles or environments, allowing for tailored configurations. Connecting the management node to the hosts are the SSH lines depicted in the diagram. This signifies the secure shell SSH connections that Ansible establishes with each host specified in the inventory. Each host is represented here, such as host 1 from Group A, host 2 from Group B, and additional hosts in Group B, ensuring that Ansible can communicate securely and perform the tasks defined in the playbooks. Understanding this structure is vital for effectively utilizing Ansible. When you run a playbook, it communicates through these SSH connections to the designated hosts, executing the tasks and returning the output to the management node, which provides the status feedback that you see in your terminal. This intuitive layout exemplifies how Ansible organizes and manages tasks across multiple systems efficiently. Now you might be wondering, what if I run this again right after? Well, if you try that, Ansible will recognize that everything is already up to date on the next execution, and you can expect to see more OK statuses with no changes needed. This idempotency, as it is called, means you can run your playbook multiple times without fearing unwanted changes or downtime. With that being said, as you get more comfortable with Ansible, you can start to branch out and explore additional features like variables, conditionals, and looping, which are all integral to writing more advanced playbooks. Now let's look at the figure. This flowchart outlines a process with the start node positioned at the top left, indicating the initiation of a task. From this starting point, two primary paths emerge, one leading to the test actions job template, and the other branching towards Project 5 DF91 D7. Each box represents a distinct component in this workflow, emphasizing variations in tasks or actions. The path marked with I illustrates a connection to an external inventory source, highlighting the integration of external resources into your Ansible workflow. This reinforces the importance of external dependencies and how they can influence your operations. Conversely, beneath the Project 5DF951D7, we see the WFJT-TB node, suggesting a follow-up action stemming from earlier project configurations. The use of arrows between these boxes emphasizes the flow of actions and decisions throughout the process. This diagram serves as a visual representation of the potential paths and actions within your automated tasks. As you explore and refine your playbooks, consider how these components interact, ensuring clarity and efficiency in your automation strategies. The connections depicted here also echo the necessity of understanding your system's architecture and how Ansible fits into the broader landscape of your operations. In closing, congratulations once again. You've just taken an incredible step forward into automation with Ansible. The playbooks you'll create will empower you to manage systems with ease and precision. Keep learning, keep experimenting, and most importantly, keep automating. It's time to make your life easier, one line of code at a time. As we discussed in the preceding 2 chapters, Ansible cannot do anything until you tell it which hosts it is responsible for. This is the bedrock of how Ansible operates. I mean, can you imagine having a highly automated kitchen where all the chefs decide to cook at once without knowledge of who's responsible for what dish? Total chaos, right? In Ansible, this chaos is deflected by clearly identifying the inventory of hosts Ansible will manage. Now, defining your inventory is not only about listing machines, it's fundamentally about establishing control over your automation infrastructure. Let's dive into this crucial aspect of Ansible so we can truly appreciate its capabilities. Now let's look at this figure, which depicts the configuration details for the Ansible Cobbler plugin. This specific setup allows Ansible to retrieve inventory hosts from the Cobbler service, acting as a bridge between your automation engine and your server management service. You'll notice the directive at the top, which indicates that this configuration must be specified in a file ending with either .cobbler.yml or .cobbler.yaml, pointing to the necessity of adhering to certain naming conventions for successful integration. In the main body, the text details how to effectively harness this plugin. It emphasizes the importance of adding primary IP addresses to host variables, specifically Cobbler IPv4 address and Cobbler IPv6 address. This is critical, as Ansible uses these variables to identify the correct hosts for automation tasks. The statement clarifies that the primary IP address can be determined through the management interface, or alternatively, it can look up DNS names to match against system host names. If these conditions aren't met, the plugin defaults to using the first available interface, ensuring some level of functionality even in less than ideal configurations. As we dive deeper, the notes highlight that this feature was introduced in version 1.0 of the community.general collection. Additionally, it outlines configurable options, starting with the mandatory cache toggle, enabling users to control whether the inventory source will be cached. This caching option can optimize performance in scenarios where rapid changes are made to the inventory, allowing Ansible to quickly adapt without unnecessary delays. This figure encapsulates key elements of configuring an effective Ansible inventory, particularly when integrating with Cobbler. The details provided serve not only as instructions, but also as guidelines that help streamline the management process, ensuring that automation stays responsive and efficient in dynamic environments. In this example, we create a static inventory using the INI format. The inventory begins by listing the host names of our servers, organized into 2 groups: web servers and databases. The web servers section includes web01.example.org and web02.example.org, representing the members of our web server team. This structured approach aids in the clarity of our server management. Following that, we outline the databases group, which comprises db01.example.org and db02.example.org. Similar to how a company assigns responsibilities to each department, organizing our servers into these groups allows us to manage them more efficiently. When executing tasks with Ansible, we must specify which group we wish to target. The given command directs Ansible to send a ping to all hosts within the web servers group. This is comparable to sending a quick message to our web team to confirm they are prepared for the next task. By directing commands at specific groups, we streamline our process and uphold an organized method of server management. In this segment, we define specific variables for each host directly within the Ansible inventory. The code snippet outlines two web servers, web01.example.org and web02.example.org, and assigns each a unique database connection URL using the variable dbURL. For web01, the connection string points to mongodb/db01.example27017, while web02 uses mongodb/db02.example.org277. This approach allows for individual configurations tailored to each server's requirements. By defining such host-specific variables, you ensure that each web server connects to the appropriate database corresponding to its role. This is especially important in environments where distinct configurations are not just preferred but necessary to guarantee proper functionality and security. Utilizing host-specific variables significantly enhances management efficiency in your deployments. When changes to these configurations are required, you can easily update the inventory without having to dig through playbooks or scripts. As a result, you maintain a clean and organized setup, much like a well-arranged kitchen where every ingredient is precisely where it should be, ready for use at a moment's notice. In the provided code snippet, we define a key called regions, which is part of a configuration for a dynamic inventory in Ansible. Here, the specific region listed is US East-1, a commonly used area in Amazon Web Services, AWS. By specifying this region, we instruct Ansible to focus its inventory gathering efforts on EC2 instances running in that geographic location. This configuration is crucial for automating the management of cloud resources. By indicating which region to target, Ansible can dynamically retrieve information about all active instances in that area. This eliminates the need for manual updates when instances are created or terminated, as the inventory will automatically reflect the current state of resources in the specified region. Consequently, you can effectively manage your cloud infrastructure, ensuring that tasks are executed only on relevant resources, thus saving time and reducing errors. In essence, this simple line of code is the gateway to a more efficient and streamlined cloud management process. Now let's look at this figure. This figure displays the output of the command Ansible inventory-graph at all, which presents a structured view of your dynamic inventory in Ansible for the AWS environment. The lines represent various groupings of hosts and instances, allowing you to visualize the organization of your resources effectively. At the top of the figure, we notice the main group labeled @AWS_EC2, which encapsulates all EC2 instances in the specified region. Below this, the subgroup AOS region US West 2 indicates that the instances listed are specifically located in the US West, Oregon region. This segmentation helps users quickly identify where their resources are deployed. Further into the hierarchy, we see several instance types categorized within their own groups, such as instance type T2 micro, instance type T2 nano, and instance type T2 small. Each of these labels helps distinguish between the different types of EC2 instances in use, providing clarity on the resource types at a glance. Additionally, the figure showcases tagged instances under the @tag name Ansible category. This labeling system can be extremely useful for organization and management within Ansible, allowing for more precise commands and targeted operations based on tags. The presence of these tags offers insights into how resources can be filtered and managed efficiently. Overall, this visual representation enhances your understanding of the dynamic inventory being leveraged in your Ansible setup, illustrating both the functional groupings of hosts and how they relate to the broader architecture of your cloud environment. In the provided code, we are defining a simple inventory for a server setup utilizing groups. The first part lists individual web servers, web01.example.org and web02.example.org, highlighting the hosts that fall under the general category of web servers. Following that, we define a group labeled backend, which includes the backend servers, app01.example.org and app02.example.org. This segmentation allows us to organize servers based on their roles in the application architecture. Furthermore, we have a group called App Servers Children that references the previously defined backend group. By designating backend as a child group under app servers, we create a hierarchical structure that simplifies management and enhances clarity. This relationship illustrates how we can establish a broader group, app servers, that effectively includes the backend servers, streamlining operations across different server roles. This type of grouping is particularly beneficial for organizing larger inventories, allowing for efficient control and monitoring of host systems within various environments. In this section, we will examine how to leverage Ansible's robust pattern mechanism for targeted inventory management. The command given illustrates this capability well. By utilizing the command ansible inventory.ini frontend backend -m ping, you indicate the inventory file named inventory.ini, which holds the definitions of your hosts. The pattern frontend backend directs Ansible to focus on all hosts categorized within the frontend or backend group. This level of flexibility enables system administrators to efficiently run commands across various servers without the need to specify each host individually. It simplifies the management process, particularly in settings that involve a large number of machines. The mping portion of the command identifies the module to be executed, in this case, the ping module, which is utilized to verify connectivity with the selected hosts. If the command runs successfully, Ansible will send a ping request to each host, matching the pattern, confirming their status. This example showcases Ansible's versatility, highlighting how it allows for a quick assessment and management of specific subsets of your inventory with ease. This example demonstrates the effectiveness of Ansible's inventory specifications by allowing the exclusion of certain hosts from a command. The provided command is crafted to ping all hosts listed in the inventory while excluding those identified as databases. By utilizing the syntax all databases, you can instruct Ansible to focus solely on the desired web servers, ensuring that your essential database servers remain unaffected. This capability is particularly valuable during maintenance or upgrades, as it helps prevent any unintended adverse effects on database performance or data integrity. It guarantees that operational tasks can be carried out on the web servers without compromising the stability of the databases. The command makes use of the Ansible ping module, which serves as a straightforward method to verify connectivity to the designated hosts. By employing the inventory file, inventory.ini, you can systematically manage your server groups. Consequently, this command allows you to effectively manage your infrastructure while minimizing risks to critical services, in line with best practices. Now let's look at the figure. This diagram illustrates the structure of organizations within Ansible, providing a clear overview of how different components are interconnected. At the top of the hierarchy, we have organizations, which serves as the overarching category encompassing all other elements. Directly beneath organizations, we find three main sections: inventories, teams, and projects. Each of these areas plays a crucial role in managing and organizing your Ansible environment. The inventories section is subdivided into groups and hosts. This subdivision allows for a fine-tuned organization of resources, making it easier to manage different environments and configurations. To the right, we see the teams section, which emphasizes the importance of collaboration within Ansible. Here, we have credentials and permissions, indicating that managing access is essential for team functionality. Additionally, the inclusion of users under teams highlights the collaborative aspect, ensuring that team members can effectively work together while adhering to security protocols. Moving on to the projects section, this area encompasses playbooks and job templates. Playbooks are a fundamental element of Ansible, defining tasks and configurations, while job templates streamline the execution of these playbooks. This structure makes it easy to organize your automation workflows, keeping everything organized and efficient. Lastly, we have the jobs section, which focuses on the execution aspect of Ansible. This encapsulation of different components reflects Ansible's robust capability to maintain a tidy and efficient management system for your automation tasks, similar to an orderly kitchen where every item has its designated place. As you now see, defining your inventory isn't just a simple task. It's a cornerstone of effective Ansible operations. It allows you to manage your hosts efficiently, automate tasks seamlessly, and scale your infrastructure effortlessly. The right inventory setup can make your automation more efficient, leaving you with more time to focus on the fun stuff, like creating those fantastic playbooks. As we wrap up this discussion, remember, Ansible inventories are your foundational building blocks. Ensure they are well-defined, and you'll set the stage for a successful automation journey. Happy automating! Creating an inventory file and adding hosts in Ansible is one of the foundational skills you must master if you want to take full advantage of this powerful automation tool. When you come across a reference to creating an inventory in Ansible, you're typically looking at what's known as a static inventory. This means that the information you're working with isn't dynamically changing, but is instead a defined set of data that you manually maintain. In simple terms, you're telling Ansible what hosts it will interact with by explicitly listing them out. So, buckle up, because we are about to dive deep into the world of Ansible inventories. In the first example, we see an INI formatted static inventory for Ansible. This format is user-friendly, especially for those comfortable with spreadsheets. The inventory begins by listing two hosts, web01.example.org and web02.example.org, under the default group, often called all. After that, we see a section labeled Databases. Under this heading, we define two database hosts, db01.example.org and db02.example.org. This straightforward structure allows you to easily group hosts together, making it simple to manage and visualize different environments. In the second example, a YAML-formatted inventory is presented. YAML is known for its readability and hierarchical structure, which is particularly beneficial for complex configurations. Here, the inventory begins with the all key, which encompasses everything. Under Children, we define two groups, web servers and databases, each containing their respective hosts. The indentation clearly shows the relationships and hierarchy, providing a cleaner and more organized way to structure the inventory. Both formats ultimately serve the same purpose, clearly defining the machines that Ansible will interact with during automation tasks. In this snippet, we define a variable called app version and assign it the value 1.2.3. This variable represents the version of an application that may be commonly used across multiple web servers in a static inventory setup. By utilizing this variable, you avoid having to specify the application version for each individual host, leading to a streamlined configuration process. When you declare a variable like app version, you can easily refer to it in your configurations or playbooks. For instance, if you need to update the application version in the future, you only have to change the value of app version to the new version number. This method not only enhances consistency across your deployments, but also drastically reduces the chance of errors that can occur from manually updating the version on each host. Furthermore, should the environment grow to include more web servers, the simplicity of managing shared variables allows for easier scalability. This practice of using group variables is a best practice in configuration management that promotes better readability and maintainability within your infrastructure setup. To construct your inventory file, begin by outlining the hosts in the INI format. The provided example features two web servers, web01.example.org and web02.example.org, both utilizing the admin user for Ansible connections. This aspect is essential since it determines how Ansible authenticates with these servers. Additionally, there is a databases section that includes db01.example.org and db02.example.org, which are set up with the dbadmin user. Grouping your hosts in this manner simplifies Ansible commands, making it straightforward to target specific groups of machines. After saving your inventory file at the indicated path, you can verify your setup. The suggested command uses the ping module for all hosts listed in your inventory file. By running this command, Ansible will send a ping message to each machine, allowing you to check connectivity. If your configuration is correct, each server should respond with a pong, signaling that Ansible is prepared to manage them efficiently. This process confirms not only connectivity, but also ensures that your inventory file operates as expected. In this inventory configuration for Ansible, we define two groups of servers, web servers and database servers, each with specific SSH ports and user credentials. The first part of the code outlines the settings for the web servers, Web01 and Web02, indicating that they will be accessed through SSH on port 2222 instead of the traditional port 22. Both servers utilize the same user, admin, for SSH authentication, which is specified for each entry. The next section of the configuration is dedicated to the database servers, DB01 and DB02. These servers are set to communicate over SSH using port 3306, a common port for database services. The user credentials for these database servers are designated as dbadmin, allowing for secure access with appropriate permissions. By organizing your inventory in this manner, you can easily manage various servers with different configurations within a single file. This flexibility makes it straightforward to adapt to varying deployment scenarios, ensuring that the Ansible playbooks can be run smoothly with the specified settings for each server group. In this YAML configuration file, we define the inventory for an Ansible automation setup. The structure begins with the top-level key all, which indicates that this inventory applies to all hosts listed underneath it. The hosts key acts as a container for individual host entries, allowing us to organize our infrastructure more hierarchically. Within the host section, each host is represented by its fully qualified domain name. For instance, web01.example.org and web02.example.org are defined as web servers. Each host includes specific parameters. In this case, Ansible user specifies the SSH user that Ansible will use to log in, while Ansible port indicates the port number for its connection. Both web servers are set up to use the same credentials, facilitating a consistent connection process. Similarly, the database servers db01.example.org and db02.example.org are listed with their own configuration. Notably, these servers use different user credentials, dbadmin, and a distinct port 3306, which is the default MySQL port. This well-structured approach in YAML not only enhances readability, but also eases the management of more complex inventories by clearly defining parameters associated with each host. As you warrant deeper into managing configurations, you may encounter the need for dynamic inventories. Don't worry, we will save that for another day. For now, focusing on static inventories is crucial because they are straightforward and often used during the initial stages of setting up Ansible. Finally, one of the last tips before we wrap up this segment is the mention of variable files. For extensive environments where host and group variables start becoming overwhelming, consider separating them into files. You can have a host vars folder where you create individual .yml files for each host, and a similar group vars folder for group variables. Ansible will automatically recognize and apply these when running your playbooks. Now, shift into a practical mindset. Your task is to create an inventory file based on your specific settings, including a couple of servers with their respective SSH configurations. Test it out by pinging them through Ansible. Remember, mastery of inventory handling is the first step toward becoming an Ansible expert. So practice makes perfect, and with time, you'll find managing your Ansible inventory to be as easy as pie. Or should we say, easy as pushing a button to automate your tasks. A playbook serves as a powerful tool for managing multiple configurations and complex deployments across numerous machines, all with a level of simplicity and ease that many other frameworks can only dream of. This marked strength of playbooks, especially in the context of Ansible, is that it allows for the logical organization of tasks. Think of it as creating a recipe where each ingredient must be added in a particular order for the dish to come out just right. In this case, the tasks will be executed sequentially by default, lending a structured flow to your automation processes. To get into the nitty-gritty of how playbooks work, let us unpack some core concepts. Each task represents a specific action, something akin to a single command in a script, perhaps installing a software package, starting a service, or copying a configuration file. The beauty of playbooks is not just in running commands ad hoc, it's in their ability to harness the power of orchestration. You can define a sequence of operations that might involve multiple systems without having to manually intervene at each step. Take, for example, deploying a web application. You would first need to install the necessary web server software, configure it, possibly set up a database, and then ensure all services are running. Instead of executing these commands one after another in the terminal, you can encapsulate all of them into a playbook, saving time and reducing the risk of error. Now let's look at the figure, which illustrates an output from an Ansible playbook execution. This specific example focuses on tasks executed under the frontend's play. At the top, you see the command that was run to initiate the playbook, indicating that it is applied to the specified hosts, followed by the file name of the playbook in YAML format. Each section of the output corresponds to distinct tasks within the play. The first task, labeled Gathering Facts, confirms successful execution on two hosts, web01.example.org and web02.example.org. This task indicates that the playbook has gathered necessary information about the environments on these hosts, establishing a foundational state before any additional actions are performed. Next, the output displays a simple connection test task. This section also shows successful results for both hosts, affirming that the playbook can connect to these hosts reliably. This step is crucial, as it verifies network connectivity and accessibility before any further commands are issued. The subsequent task, Run a Simple Command, presents challenges. Here, errors are reported for both web01.example.org and web02.example.org, indicating failure to access a non-existent file or directory. The output provides detailed diagnostic information, including the command attempted, return codes, and error messages. These details can help troubleshoot the issue, revealing that the execution did not go as planned due to the specified file not being found. Finally, the Play Recap section summarizes the outcomes. It highlights the status of each host, showing that while the gathering of facts and connection tests were successful, the command execution attempted resulted in failures. Notably, the recap specifies task counts, showing that one task was changed, indicating modifications were made on the hosts, and one task was ignored due to the previous errors. This information is vital for understanding the overall success and potential issues within the playbook execution process. This playbook defines a single play that targets hosts classified as web servers. The primary goal is to install and start the Apache web server. The directive become yes signifies that the tasks will be executed with elevated privileges, which is often necessary when installing software or managing services. The first task within the playbook is focused on installing the Apache package. It utilizes the ansible.builtin.app module, which is specifically designed for managing packages on Debian-based systems. Here, the name parameter specifies the package to be installed, Apache 2, and the state latest parameter ensures that the most recent version of the package is installed. Following the installation, the second task aims to start the Apache service. This is accomplished through the ansible.builtin.service module, which manages system services. The task specifies the name parameter as Apache 2 to target the correct service, while state started ensures that the service is up and running. Together, these tasks facilitate the seamless setup of an Apache web server on the defined host machines. Executing the playbook is straightforward, typically done via a command like Ansible playbook-i inventory myplaybook.yml. In this command, Ansible Playbook is the tool we use to run the playbook, which contains a series of tasks to be executed on the target hosts. The -i flag specifies the inventory file where Ansible will look for the hosts on which the tasks will be executed. The inventory file is crucial as it defines the environment and the specific machines to which the playbook applies. The myplaybook.yml portion refers to the YAML file that contains the specific tasks and configurations that Ansible will apply to the listed machines. When the playbook runs, Ansible communicates with each specified host and executes the defined tasks in the playbook. Feedback is provided throughout the process, allowing you to see what actions were taken, such as whether services were started or packages were installed. This feature enables effective monitoring and troubleshooting of any issues, ensuring you are always informed about the outcomes of your automation efforts. Additionally, the idempotency of playbooks means that running them multiple times won't inadvertently alter already established configurations, thereby maintaining system stability. In this Ansible playbook, we establish a conditional task that enables the installation of the Apache web server specifically on Ubuntu systems. The playbook begins with the definition of its scope, targeting all hosts in the inventory. The task is named Install Web Server Only on Ubuntu to clearly convey its purpose. The heart of this task lies in the use of the Ansible.builtin.apt module, which is responsible for managing packages on Debian-based distributions, such as Ubuntu. We specify that we want the Apache 2 package to be installed and to ensure that it remains updated by setting its state to latest. However, the real power of this playbook is in its conditional execution, denoted by the when statement. This clause checks whether the underlying host's distribution matches Ubuntu. If true, the task will proceed. If not, it will be skipped. This approach allows for a flexible and dynamic playbook that adjusts its behavior based on the host environment, showcasing the ability to tailor automation efforts to varied setups efficiently. In this Ansible playbook, we define a task aimed at configuring a firewall on web servers. The primary objective is to enable access for web traffic by opening common ports used for HTTP and HTTPS. The playbook begins with specifying the target hosts, which in this case are labeled as web servers. Within the task section, we create a single task dedicated to opening the firewall for both HTTP and HTTPS traffic. This is accomplished using the Ansible built-in.firewalld module. The critical aspect of this task is the use of the port parameter, which dynamically assigns its value based on the items provided in the loop. By employing a loop, we efficiently iterate through the specified ports, 80 for HTTP and 443 for HTTPS, without having to write separate tasks for each port. This not only reduces redundancy, but also enhances the clarity and maintainability of the playbook. By encapsulating the logic in a loop, the playbook demonstrates a reusable and elegant approach to managing firewall configurations, showcasing the power of automation in IT processes. In this Ansible playbook, we define a task to install a web server stack on all targeted hosts. The tasks are organized within a block, which allows for better control over the execution flow. The block contains two primary tasks. The first task installs Apache using the Ansible.builtin.apt module, specifying that the latest version of the Apache 2 package should be installed. The conditional logic applied here ensures that these tasks will only run if the target system is using the Ubuntu distribution. This is done using a when statement linked to the Ansible facts variable, which dynamically checks the distribution of the host. By utilizing blocks, if the installation of Apache fails for any reason, the subsequent task to install MySQL will not execute. This prevents further complications that may arise from attempting to install dependent services when a prerequisite task has failed. Employing blocks in your playbook enhances error handling and provides a clearer structure for managing complex workflows. Ansible also supports extensive error handling capabilities. For instance, tasks within a block can utilize rescue and always clauses, providing clean ways to handle failures. This way, you can execute certain fallback tasks if something fails during the block execution, while ensuring some tasks are always run regardless of success or failure outcomes. When deploying configurations across many environments, documenting the process with playbooks not only helps ensure consistency, but also aids future debugging. With every command written down, along with its intended outcome, even if you run into obstacles later on, you can refer back and understand where things may have diverged from the intended path. As you become more proficient with Ansible playbooks, you will find yourself developing entire hierarchies of playbooks and roles for advanced automation setups. This modular approach allows for reusability while keeping the playbook series streamlined and maintainable. Roles help encapsulate configurations, making it easier to manage and streamline your tasks. In summary, the understanding of the playbook framework is foundational to leveraging Ansible's full potential. Mastering playbooks will empower you to automate and manage infrastructure more seamlessly, while also giving you the ability to build complex applications and configurations efficiently. As you write and refine your playbooks, remember that they not only serve as functional automation tools, but also as living documents of your infrastructure architecture, easy for others to follow and adapt when needed. So in conclusion, if you are looking to tame the wild world of configurations and deployments across multiple machines, give playbooks a serious consideration. They offer simplicity, consistency, and power, allowing you to orchestrate activities that are not just more manageable, but are also aligned perfectly with best practices of operations. In the ever-evolving landscape of technology, mastering Ansible playbooks today might just save you a lot of headaches tomorrow. Understanding roles in Ansible is a crucial aspect of automating your IT infrastructure tasks efficiently. Remember, roles are designed to enable you to efficiently and effectively reuse Ansible code. This is not just a matter of convenience, it's also about maintaining clarity and organization in your automation tasks. So let's set off on this exploration and dive deep into the functionalities, benefits, and structure behind Ansible roles, ensuring you grasp everything along the way. Roles provide a structured way to organize your playbooks. Imagine you're at a restaurant and the menu is simply a list of single items. You might find it overwhelming to decide what to order. Now picture a well-organized menu where items are grouped by category: appetizers, main courses, desserts. That's what roles do for your Ansible playbooks. They streamline tasks into manageable and reusable units. Each role encapsulates a segment of functionality that can be independently tested and modified, making your automation workflows much more resilient and less prone to errors. In this section, we illustrate the directory structure of an Ansible role named Install Apache. At the top level, the role consists of several important subdirectories that contribute to its organization and functionality. The tasks directory is vital as it contains the main.yml file, where you'll define the sequence of operations that Ansible will perform when the role is executed. Alongside tasks, the handlers directory serves a critical function by also containing a main.yml file, which defines actions that will be triggered by specific events, ensuring that changes are applied only when necessary. The defaults directory is where you can set default variables for your role, allowing for flexible configuration. Similarly, the vars directory holds variable definitions that can be customized as needed. In addition to these functional components, the templates directory is included for Jinja 2 templates, which enable dynamic file generation. Finally, the files directory allows you to include static files that can be copied to remote hosts. This structured approach to organizing your role makes it easy to develop, maintain, and reuse across different projects. In the tasks folder, we have a file named main.yml that serves as the entry point for the tasks when the role is invoked. This file allows for organized management of tasks associated with specific roles. In this case, we are focusing on installing and managing the Apache web server. The first task in the file specifies the installation of the Apache package using the ansible.builtin.apt module. Here, we define the name of the package as Apache 2 and set the desired state to latest, ensuring that the most current version of Apache is installed on the system. The second task is responsible for starting the Apache service, utilizing the ansible.builtin.service module. We again specify the service name as Apache 2 and set its state to started. This guarantees that the Apache server is not only installed but also running properly. Overall, this structure allows for efficient reuse of the role across various playbooks, streamlining the process of web server installation and management without duplicating similar code in multiple locations. In this section, we define a handler within our handlers directory that is specifically responsible for restarting the Apache service. The handler is identified with a descriptive name, Restart Apache, which clearly indicates its purpose. When triggered, this handler utilizes the ansible.builtin.service module to manage the state of the Apache service. The key portion of the code specifies that the name of the service to be manipulated is Apache 2, which is the standard name for the Apache HTTP server in many Linux distributions. By setting the state parameter to restarted, the handler ensures that if this task is called, it will stop the Apache service if it is running and then start it again. This is particularly useful in scenarios where changes to configuration files necessitate a restart of the service to apply those updates. Handlers are advantageous because they are only executed when notified by other tasks, ensuring that the Apache service is not restarted unnecessarily. This on-demand nature of handlers allows for more efficient Ansible playbook executions while maintaining the desired service state effectively. In the context of Ansible roles, the code snippet Apache port 80 indicates that a variable named Apache port is being defined and assigned the value of 80. This variable typically represents the default port on which the Apache HTTP server listens for incoming connections. By defining this variable in the appropriate YAML file, users can ensure that the web server operates on a predictable port, making configuration and deployment more straightforward. The distinction between placing this variable in the defaults directory versus the vars directory is crucial. If Apache port is placed in the default/main.yml, it would act as a sensible starting point that could be overridden by other variables defined in the vars/main.yml file. This variable precedence allows for greater flexibility, as the default value can be adapted depending on the environment or specific deployment requirements. Thus, by utilizing such variable organization, Ansible roles can be more modular and easily adjustable to meet varying needs across different infrastructures. In this section, we focus on a specific line of code that demonstrates the use of Jinja2 templates for dynamic content generation within configuration files. The line reads, server name, Apache server name. In this example, server name is a directive used in Apache configuration files to specify the host name of the server. When Apache processes the configuration, it needs to know which server name to use in various contexts, and this is where Jinja2's templating capabilities come into play. The variable Apache server name is a placeholder that gets replaced with the actual value assigned to it during the execution of the playbook. This means that instead of hard-coding a server name into the configuration file, we can dynamically inject the correct value based on variables defined elsewhere in our Ansible role. Consequently, when deploying to different environments, this approach eliminates the need for manual alterations to the configuration file. By leveraging these templates, roles become more versatile and adaptable, enabling a streamlined deployment process while maintaining consistency across various setups. In this Playbook snippet, we are configuring web servers by targeting a group of hosts identified as frontends. The Playbook starts with a clear and concise declaration of its purpose through the name, Configure Web Servers. This immediately informs anyone reading the Playbook about its intended functionality. One important aspect of this Playbook is the use of the Become directive, which elevates privileges to run the tasks defined within the roles. This is especially useful when tasks require administrative permissions, ensuring that the configuration is applied correctly. Rather than detailing every individual task within the playbook, we leverage the abstraction of roles. In this case, we call the Install Apache role. This decision simplifies our playbook, as it encapsulates all the necessary tasks associated with installing and configuring Apache Web Server into a single, reusable unit. As a result, the playbook remains clean and readable, allowing for easier maintenance and reusability in future deployments. By organizing tasks into roles, we enhance clarity and effectiveness in our automation efforts. Moreover, roles also enhance collaboration within teams. They enable developers to work on specific roles without worrying about the rest of the playbook's structure. This not only fosters teamwork, but also speeds up the development process. Imagine a team with members dedicated to different aspects of a project. Each can work on their role independently, merging their contributions without chaos. But wait, there's more. Ansible has a robust community support mechanism known as Ansible Galaxy. This is a library of community-contributed roles where you can find existing roles that address common automation tasks. If you're thinking about implementing something standard like setting up Nginx, you might find a role on Galaxy that suits your needs perfectly, saving you development time. You can simply download and include it in your own playbooks. In the provided code snippet, we see a declaration of role dependencies within an Ansible roles meta directory. The line dependencies role PHP signifies that the current role, presumably named web server, is reliant on another role called PHP. This structure is essential for managing complex configurations where multiple functionalities are intertwined. When you specify a dependency in this manner, it streamlines the role execution process. Specifically, when the web server role is invoked, Ansible automatically recognizes the dependency on the PHP role and executes it as part of the process. This automation eliminates the need for manual invocation of the PHP role separately, saving time and reducing the potential for errors. By clearly defining such dependencies, you ensure that all necessary components are in place before the main role runs, thereby creating a more reliable and efficient deployment process. This approach not only simplifies your playbooks, but also enhances clarity, as it is evident which roles are interconnected and need to be executed in tandem. Continuing our exploration, let's not forget about testing. Testing your roles is as crucial as the development process. You should always test your roles in various environments to ensure they function correctly. This could mean running your roles in a staging environment before rolling them out to production. You can also create unit tests for your roles that validate functionality using tools like Molecule. Additionally, consider version control practices through Git, allowing you to track changes over time and roll back if necessary. Having a solid version control strategy also enhances collaboration by providing a clear history of changes. Lastly, don't forget best practices. Naming conventions for your roles and keeping related files together help maintain clarity over time. For example, if your role is intended for Apache installation, using install Apache is meaningful. Also, document your roles aptly. Explain what each role does within a README file inside your roles directory. This documentation is invaluable for users who may utilize your roles in the future, helping them understand how to get the most out of your work. Now let's look at this figure. The output displayed demonstrates the successful execution of an Ansible playbook, highlighting various tasks involved in configuring both front-end and application servers. The first section outlines the play targeting the front-end servers. Here, we can see the initial task, gathering facts, which confirms the successful inventory of the front-end servers, as indicated by the OK status for both web servers listed. Next, we observe the task for installing the Apache package. Notably, the output highlights that changes were made on both web servers, showing that the installation was performed correctly. Following this, the playbook continues with the task of starting the Apache server, again confirming it executed successfully on both servers. Shifting to the second play, which focuses on the application servers, we see another instance beginning with the gathering facts task. This task has also completed successfully, as shown by the OK status for both app servers. The output then progresses to the installation of Tomcat, where similar results indicate that both application servers underwent the installation process without any errors. The final part of the output showcases the Start the Tomcat server task, reflecting successful execution once again. The recap section at the bottom summarizes the results for all servers involved. Each entry notes the number of tasks that were executed successfully, changed, or ignored, providing a concise overview of the playbook's effectiveness. This figure effectively illustrates how organized and structured Ansible playbooks can enhance your automation workflow, reflecting the importance of roles in managing complex configurations. Throughout this book, we have almost constantly referred to and made use of Ansible modules. If you've grazed through our discussions, you might wonder, what exactly are Ansible modules? Think of them as specialized tools in your toolbox. Each module has its function, like a hammer is for driving nails, while a screwdriver is for turning screws. Similarly, Ansible modules handle specific tasks, from executing commands on remote systems to managing cloud resources or configuring firewalls. They are designed to carry out operations in an efficient manner without us needing to dive into the underlying complexities. This makes automation swift and accessible. So why should we care about Ansible modules? With over 3,300 modules available as of the current release, they range from simple tasks like copying files to intricate operations on cloud infrastructures. Moreover, they empower users to create their own functionalities, expanding Ansible's capabilities beyond the out-of-the-box features. In this segment, we will explore the world of Ansible modules, their structure, their working, and most excitingly, how to create your own. In the provided example of an inventory file, we outline our target machines. We designate frt01.example.com as a front-end and include app01.example.com within the app servers group. This organized structure enables Ansible to easily categorize and target specific hosts for various operations. Next, we demonstrate how to execute an Ansible module. By running the command ansible-i hosts appservers-m ping, we instruct Ansible to utilize the inventory file named hosts, while specifically targeting the app servers group and invoking the ping module. Upon execution, we receive a response that confirms a successful connection to app01.example.com. The output is presented in a structured format similar to JSON, detailing the Ansible facts and the ping result, which indicates that the host is reachable with a PONG response. The presence of discovered interpreter Python points to the version of Python that Ansible will employ on the target machine. This interaction not only showcases the command execution, but also demonstrates the simplicity and convenience of performing connectivity checks within Ansible's framework. In this scenario, we demonstrate the use of Ansible's command module to run a basic shell command. By executing the command ansible-i hosts appservers-m command-a/bin echo hello modules, we are directing Ansible to connect to a specified set of inventory hosts, referred to as our app servers. The -m command option indicates that we are leveraging the command module, while the -a flag is used to provide the arguments to be executed, which, in this instance, is a command to display the message hello modules. Once the command is executed, Ansible handles the command and interacts with the target machine. The output received reflects the outcome of the operation. app01.example.com changed rc=0 hello modules. This result indicates that the command was successfully carried out on the designated host app01.example.com as denoted by the change status. Additionally, the rc=0 confirms a successful return code, suggesting that no errors occurred during the execution. This clear example highlights how Ansible modules can streamline tasks, enabling users to run commands remotely without needing extensive back-end programming knowledge. Now that we've established how modules operate, how can we efficiently locate the right module for our needs? With thousands available, it might feel daunting. Thankfully, Ansible provides a well-structured module index that can act as a roadmap to guide you. Consider this. If you were looking for a module to manage your AWS S3 buckets, you'd start at the core module index available, docs.ansible.com nf/latest/collections/index module. For example, searching for Amazon.aws in the index will unveil a goldmine of modules specific to AWS management. Once you identify a potential candidate, the documentation for each module provides detailed descriptions, options, and practical examples, thus ensuring you can utilize them effectively. In addition, leverage the command line tools at your disposal. The Ansible doc tool is particularly handy. By executing the command ansible doc-l, you can get a comprehensive list of all modules with a concise description beside them. You can then filter through the list, seeking something like S3 to narrow down specific functionalities. Now let's look at the figure. It showcases an Ansible cheat sheet that serves as a quick reference guide for users. This visual presentation is designed to streamline the process of accessing essential commands related to Ansible operations. At the top, we see the title, Ansible Cheat Sheet, clearly labeled and emphasizing its purpose. The content on the cheat sheet is segmented into distinct sections, each highlighting key commands. For instance, the section on Ansible ad hoc commands illustrates how to check connectivity to hosts using the Ansible group-m ping command. This is crucial for administrators who need to ensure that their target machines are reachable before executing further tasks. Additionally, the figure includes commands for executing shell commands on hosts, reinforcing the versatility of Ansible in managing remote systems. An example command is shown as Ansible group-a shell-c command, providing a clear syntax that users can adopt for quick execution. Moreover, the cheat sheet also features Ansible inventory commands, which provide users with methods to list hosts and visualize inventory. Commands such as Ansible inventory list and Ansible inventory graph are succinctly presented, showcasing the capabilities of Ansible in organizing and managing inventory efficiently. This figure serves as an invaluable resource for both beginners and experienced users, allowing them to reference important Ansible commands quickly without needing to navigate through extensive documentation. The code begins with a shebang line, pointing to the Python interpreter that will execute the script. It then imports the Ansible module class from the ansible.moduleutils.basic module, which is essential for creating custom Ansible modules. The main function is defined as the entry point of the module, encapsulating its primary functionality. Inside the main function, an instance of Ansible module is created. This object is initialized with an argument spec dictionary that defines the parameters the module will accept. In this case, two parameters are defined: name, which is a required string, and state, which indicates the desired state of the resource and accepts either present or absent. The commented section is a placeholder meant for implementing the core logic of the custom module. This is where the main operations and tasks would be handled based on the provided parameters. Finally, the function calls module.exitJSON to send a response back to Ansible, indicating that changes have been made and returning the name parameter passed to the module. The script concludes with a standard conditional to execute the main function when the script is run directly. To give you a clearer picture, let's examine how to execute some internal logic. Let's say you want to manage files on remote machines easily. Your custom module could check for a file's existence and create or remove it based on user input. Continue building upon your module by leveraging Python standard libraries such as os or shutl for file operations. With those tools, you can define actions to carry out effectively based on the specified conditions from the user input. This flexibility is crucial. Once you've tested your module and validated its potential, your next move could be to contribute it back to the Ansible main repository, helping other users in the community. From here, the excitement only builds. The future of your automation project can expand dramatically as you confidently manage your infrastructure and applications, whether that's alongside existing modules or through your custom creations. In conclusion, Ansible modules form the very backbone of automation in Ansible. By understanding how they work, how to find the right ones, and how to create your own, you significantly enhance your ability to leverage Ansible for efficient systems management. Each module you create not only addresses immediate needs, but also contributes to an ever-growing ecosystem that you and many others can benefit from. So, whether you are executing existing modules or diving into developing your own, always remember that Ansible has a rich collection of tools waiting for you to discover and leverage in your automation journey. Armed with the knowledge you've gained, you're now ready to embark on an exciting journey into creating custom modules for Ansible. Imagine the power you'll wield, crafting tailored solutions that extend the capabilities of Ansible beyond the standard offerings. It's like being a wizard in a world where automation reigns supreme. Before we roll up our sleeves and dive into the mechanics of module creation, let's set the stage. Ansible's modular architecture is not just a nice-to-have feature, it's central to its flexibility. You see, with over 3,300 modules readily available, there's a good chance that many common tasks are already covered. But what happens when you hit a wall? When you find yourself needing functionality that no existing module provides? This is where your creativity and Python skills come into play. From file management to interacting with APIs, the possibilities are vast. To begin setting up your development environment, you'll need to install Python and its development components based on your operating system. For Fedora users, the command sudo dnf install python devel will install Python alongside the necessary development libraries. This ensures you have the core features required for module development. If you are on CentOS, the process is slightly different. The command sudo yum install python 3 devel is used to install Python 3 along with its development files, allowing you to compile and build additional modules that you might need. For Ubuntu users, you'll execute a more extensive procedure. First, you run sudo apt-get update to refresh your package list, followed by sudo apt-get install python 3 pip, python 3 dev, build essential. This command installs Python 3, the pip package manager for handling Python packages, and essential build tools to facilitate development. Finally, macOS users should take advantage of Homebrew with the command brew install Python to install the latest version of Python seamlessly into their system. With the installation completed, you will be ready to create your development space and start building your modules. Creating a clean virtual environment is an essential first step in ensuring a smooth development process and avoiding potential conflicts with other projects. To establish your virtual environment, navigate to your Ansible workspace and run the command python vemv module dev. This command creates a new directory named module dev that contains a self-contained Python environment. Once the virtual environment is set up, you need to activate it. This can be accomplished by executing the command source module dev/bin/activate. Activating the environment allows you to work within that isolated space, ensuring that any Python packages you install or scripts you run will not interfere with your system-wide Python installation or other projects. Now that your environment is ready, it's time to clone the Ansible repository to access valuable resources for your development. By executing the command git clone https:/github.com/ansible.git, you create a local copy of the repository which holds numerous scripts and modules that can significantly aid in your module development. With everything set up, you are now poised to start creating your first simple module. In the first line of the code, a shebang usr bin n python is included at the top of the file. This line serves as an instruction to the operating system to use the Python interpreter to execute the script, ensuring that the correct environment is used regardless of how Python is installed on the system. Following the shebang, there is a copyright notice and licensing information, which is best practice for any publicly shared code. It credits the author and states the terms under which the code may be used, specifically citing the new General Public License v3.0+. This openness promotes transparency and encourages collaboration while protecting the author's rights. Additionally, the code initializes a dictionary named Ansible Metadata, which holds metadata about the module. This dictionary includes details such as the version of the metadata, its status, and the community support level. Such documentation is crucial for users, as it clarifies the module's purpose and informs them about its current development stage, fostering a better understanding of how to effectively utilize the code. The provided code snippet is a documentation string for a module named Remote File Copy, which is intended for use in automation tasks. This module was introduced in version 2.5 and is designed to facilitate file copying on remote hosts. The short description gives a concise overview of the module's primary function, copying a file from one location to another on a remote machine. The description section clarifies the purpose of the module, emphasizing that it enables users to transfer files seamlessly between hosts. The options outlined in the documentation specify the parameters required for the module's operation. The source option denotes the path to the file that needs to be copied from the remote host, which is marked as mandatory. Similarly, the dest option indicates where the file should be saved on the destination remote host, also marked as required. Lastly, the documentation credits the author, providing space for them to include their name and GitHub identifier, ensuring that users can recognize the source of the module and reach out for further information or contributions. In this code, we begin by importing the necessary components from the ansible.moduleutils.basic module, specifically the Ansible module class, which is crucial for defining the structure and functionality of our Ansible module. The main function is defined next, which will serve as the entry point for the execution of the module. Inside the main function, we create an instance of Ansible module. This instance is initialized with an argument spec dictionary that outlines the expected input parameters for the module. In this case, two arguments are required, source and dest, both of which must be provided as strings. This setup ensures that users of the module supply the necessary information for it to perform its task correctly. Following the argument specification, a comment is included to indicate where the logic for copying the file will be implemented. This serves as a placeholder for the core functionality of the module. Finally, we check if the script is being run as the main program, and if so, we invoke the main function to kick off the process. This structure is essential for modularity, allowing the code to be both reusable and easily testable. In this section of the tutorial, we will explore how to utilize the Python util library for copying files between specified locations. This operation is fundamentally driven by the shuttle.copy method, which takes two arguments: the source file location and the destination where the file should be copied to. Within the context of a larger application, this functionality is integrated into the main function after all necessary inputs have been gathered. The provided code is wrapped in a try-except block to handle any potential exceptions during the file copy process. When the copy operation is successful, the module.exitJSON method is invoked with a parameter indicating that a change has occurred. This is particularly important for communicating with Ansible, as it allows the script to report back the success of the operation. Conversely, if an error arises during the file copy, the exception is caught, and the module.failJSON method is called with an appropriate error message. This dual handling ensures that users are informed about the outcome of their operation, whether successful or not. In the provided code snippet, we focus on defining the output of a module using a structured return section. This section is vital for documentation, as it clarifies the specifics of what users can expect when they execute the module. The return section contains detailed information about two primary elements: source and dest. For the source, it outlines the description, indicating that it refers to the source file utilized for copying. It confirms that the expected outcome of this operation is a successful return, specifying the data type as a string. An example of a typical output for the source file is provided, illustrating the potential path format, /path/to file.name. Similarly, the dest element describes the target destination for the copy operation. Like the source, it affirms a successful return and notes the expected type as a string, with an example path such as path_to_destination.file. This structured output not only serves to inform users about the expected results, but also enhances the usability and clarity of your module, ensuring that users have a clear understanding of its functionality. In the provided YAML playbook, the main objective is to test a custom Ansible module designed for remote file copying. The playbook begins with the standard structure, which includes defining the play and specifying the target hosts. Here, the local host is designated as the target host, meaning the operations will be executed locally. The first task in the playbook is named Test Remote File Copy. It utilizes the Remote File Copy module to facilitate the transfer of a file from a specified source path to a destination path. The source parameter indicates the location of the file to be copied, while the dest parameter specifies where the file will be placed on the target system. The result of this task is registered in a variable named result, allowing subsequent tasks to reference the output. The second task is designed to display the outcome of the previous file copy action. By employing the debug module, it outputs the contents of the result variable, providing insights into the success or failure of the file transfer. This structured approach ensures that the module's functionality can be easily tested and verified, thereby enhancing the reliability of the custom code. In this section, we will focus on running your Ansible playbook using the command line. The command you see here is quite straightforward and consists of the command to invoke Ansible along with the necessary parameters to execute your playbook. By typing $Ansible playbook -I localhost your playbook.yml, you are instructing Ansible to execute the playbook file named your playbook.yml. The -I localhost portion specifies that the inventory is localhost, meaning Ansible will run the tasks defined in the playbook on the local machine. This is particularly useful for testing and development purposes, as it allows you to simulate the execution of your module without affecting any remote systems. Once you run this command, you should expect to see results displayed in the terminal, which will indicate whether your module executed successfully or if there were any errors. The output will provide specific feedback, confirming if the tasks performed according to your intentions. This process is essential for validating that your configurations and scripts are working as expected. So there you have it. From the initial setup to writing and testing your first custom module, you are now equipped with not just knowledge, but practical skills to dive deeper into the world of Ansible. Remember, the beauty of open source lies in sharing. Consider contributing your module back to the Ansible community. There's always someone out there who can benefit from your hard work and creativity. As you move forward, keep an eye on things like code quality, effective error messages, and helpful documentation. The more robust your module, the more valuable it will be, not just for you, but for the entire community. Happy coding and welcome to the world of Ansible module development. Although we've mentioned some of this earlier in this book, our goal is for this to be a complete one-stop source of information for collections. Thus, if you've skipped directly to this chapter, don't worry, we've got you covered. Let's start with some history, as this is important to understand the intention behind collections. With Ansible releases prior to 2.9, everything was managed in one huge monolithic code base. While the core Ansible team owned this code base, the modules, which really form the lifeblood of Ansible, were not. Imagine a scenario where a network device vendor wanted to release a new module. They might have added a new feature or fixed a bug in a previous release, but the process to submit these contributions was a significant undertaking. They would need to make the changes, test them, and submit them as a pull request to the main Ansible repository. This long process could seriously slow down the release cycles, creating unfortunate bottlenecks. As the popularity of Ansible grew, this way of working became increasingly untenable. Consider a large enterprise user of Ansible who suddenly encounters a critical problem with a module just weeks before a major launch. They need a fix now. Or perhaps a vendor has an exciting new feature ready to be integrated into Ansible but has to wait weeks or even months for the next release cycle. Such situations are not just frustrating. They can hinder progress and negatively impact business operations. Recognizing these challenges, the Ansible team introduced collections. Collections allow individual teams and vendors to develop, test, and release their contributions independently and at their own pace, without being tied to the core Ansible release cycle. In brief, a collection is a bundle that packages various types of code. This includes roles, plugins, modules, playbooks, and even documentation into a single package for simple distribution. The design of collections is straightforward. At its core, a collection is simply a set of directories containing the relevant files. These files are then packaged into a gzip tarball for easy sharing. Notably, collections can be managed and installed locally or via Ansible Galaxy, making them a more flexible solution compared to the older Ansible setup. If you're familiar with Ansible from its pre-collection days, you might know that roles were distributed via Ansible Galaxy and were managed using the Ansible Galaxy command line utility. So this begs the question, if you develop your own role, should you distribute it as a role or as a role within a collection? Currently, both methods are viable, but it's clear that the future is leaning toward collections, given their broader scope for expansion. Now let's look at the figure presented. This visual represents the Ansible Automation Hub interface, specifically focusing on the Collections section. On the left side, there is a navigation menu where Collections is highlighted, indicating that you are currently viewing this part of the platform. This section is vital for managing and exploring various collections of Ansible roles and modules. In the main viewing area, a search bar allows users to filter collections by typing in keywords. In this instance, the keyword RAI is entered, hinting at a search for specific collections related to Red Hat Enterprise Linux or similar. This feature provides an efficient way to locate the desired functionality quickly, demonstrating the user-friendly design of the Automation Hub. Below the search bar, two collections are showcased, AAP Utilities and ACI. Each collection entry includes essential information such as the provider's name, indicating who maintains the collection. Notably, the AAPOR Utilities collection is provided by Red Hat and is described as a set of utility roles for use with Ansible automation. The second collection, ACI, is identified as a certified module suite for managing Cisco ACI, further illustrating the diversity of available functionalities within the Ansible ecosystem. Additionally, icons next to each collection indicate their status. For instance, the validated and signed icons signify that the AAPOR Utilities collection meets specific quality standards, ensuring reliability for users. This guidance on visual elements helps users discern the quality and credibility of the collections quickly as they navigate through the Automation Hub interface. Before collections, every module had to possess a unique name to avoid naming conflicts. Hence, names such as iOS BGP and Fortios Route Escorter BGP became the norm. All three modules modified the Border Gateway Protocol (BGP) configuration, but needed unique identifiers to maintain clarity and organization. However, collections remove the need for these cumbersome module names. This new flexibility allows contributors to create modules with overlapping names, significantly simplifying naming conventions. Despite its advantages, this shift does pose a degree of risk. For example, if you created your own collection with a module named Debug, similar to the built-in Ansible debug module, you could inadvertently introduce errors or unexpected behaviors in your playbooks. This potential for confusion highlights the importance of using fully qualified collection names going forward. In the provided YAML snippet, we see a task defined to print debug output using Ansible, a popular automation tool. The task begins with a descriptive name, print debug output, which clarifies its purpose in the broader context of the playbook. Following this, we invoke the debug module found under the Ansible.builtin namespace, specifically calling it as Ansible.builtin.debug. This practice exemplifies the use of a fully qualified collection name, FQCN, which helps clearly identify the module and minimizes the risk of conflicts that could arise from modules with similar names. The actual functionality of the debug module is to output messages, making it invaluable for testing and verifying playbook behavior. In our example, we specify the message to print as Hello World within the MSG parameter. This simplicity highlights one of the core strengths of Ansible, its ability to deliver clear and concise messages during automated processes. By structuring tasks in this way, users achieve improved clarity and maintainability in their playbooks, ensuring better understanding and collaboration within their automation efforts. The command you see here, Ansible Galaxy Collection Build, is a critical step when creating and packaging your own Ansible collections. When you execute this command, Ansible scans the structure of your project directory to identify all relevant components, such as modules, roles, and other files that you intend to include in your collection. This automates the process, allowing you to focus on developing your code instead of getting caught up in configuration details. Upon successful execution, the command generates a .tar.gz file that consolidates all your project's artifacts into a single package. This package collection is essential for distribution, making it easier to share your work with teammates or across different environments. The standardization achieved through this process is crucial for teams, ensuring that everyone adheres to a uniform structure while utilizing shared playbooks and collections. Ultimately, Ansible Galaxy Collection Build simplifies the management of Ansible projects, enhancing collaboration and efficiency within your organization. Managing collections in Ansible is essential as your projects grow in complexity. This is where the command Ansible Galaxy Collection Install Collection Name comes into play. This command allows you to easily install a specific Ansible collection, which can include modules, plugins, and roles essential for your automation tasks. By specifying the collection name, you can quickly acquire the latest features and capabilities offered by that collection. Moreover, it's important to maintain compatibility with previous versions, and this command facilitates that by allowing you to install specific versions if necessary. After installation, you can run the Ansible Galaxy Collection List command to view all installed collections and their corresponding versions. This capability is crucial for managing dependencies within your environment, as it helps identify any mismatches or outdated components that may arise during troubleshooting. Thus, using the Ansible Galaxy Collection Install command not only streamlines the process of managing these collections, but also ensures that your automation is both current and functional. As we continue our journey into the world of Ansible collections, we'll venture beyond the foundational concepts and delve into the practical side of creating, using, and maintaining collections effectively. Consider what happens when you want to distribute your code within an organization, or perhaps contribute back to the wider Ansible community. It's here we see the real power of collections materialize. With this foundational understanding in place, we can now expand our exploration to practical examples, allowing you to form your own collection tailored to the specific needs of your environment or project. Once you have built your first collection, you might feel a sense of achievement akin to cracking a tough programming challenge. Trust me, it's real. Let's shift our attention to this figure, which illustrates Ansible's automation engine. At the center, we see the core components that drive Ansible's functionality. This includes the inventory, API, modules, and plugins, all essential for effective automation tasks. Surrounding the automation engine, we can identify various key elements that interact with it. On the left, the user represents those who engage with Ansible, deploying playbooks to automate processes. Below, the Ansible playbook serves as a blueprint for the automation tasks you'll define, ensuring clarity and structure. On the upper side, we find the CamDB, highlighting the importance of configuration management databases in maintaining an organized view of your infrastructure. Moving to the sides, hosts indicate the machines where tasks will be executed, while the public, private cloud, and networking elements reflect the environments in which Ansible can operate, showcasing its versatility. Together, these components create a comprehensive ecosystem that facilitates smooth and efficient automation workflows. The interplay among them demonstrates how consolidating roles, plugins, and modules enhances project manageability. This figure encapsulates the foundational framework that you'll build upon as you delve into creating and implementing your collections in Ansible. Creating your own collections can be an exciting journey into the world of automation using Ansible. We've come a long way in understanding collections, how to manage them, and their importance in the larger Ansible ecosystem. Now, we'll dive headfirst into the practical aspects of creating your very own collection from scratch. This hands-on process will not only give you a deeper understanding of how collections are structured, but also equip you with the skills to utilize them effectively. You might be wondering, what exactly is a collection? Collections are essentially organized sets of files and directories that contain everything related to a specific functionality in Ansible. Whether it's roles, modules, plugins, or documentation, everything you need for a particular purpose can be housed in a collection. This approach makes it easier to package and distribute your Ansible code. Now that we've established the groundwork, let's get our hands dirty and start creating. To begin creating your Ansible collection, the first command, mkdir collection development, creates a new directory named collection development. This is where you will develop your collection, helping to keep your workspace organized. The following command, cd collection development / navigates into that directory, preparing you to execute the next steps for initializing your collection. Once inside the directory, the command Ansible Galaxy collection init practical ansible.examples is utilized. This command initializes a new collection with the specified namespace practical Ansible and collection name examples. Upon execution, you will see a success message affirming that your collection has been created. To visualize the structure of your newly created collection, you can use the command tree. This will display the hierarchy of directories and files generated within practical ansible.examples. You'll notice the top-level namespace, followed by the collection name, and several essential files including readme.md for documentation and galaxy.yml for metadata. This organized structure helps facilitate easy navigation as you work on your collection's components. The first step in creating our Ansible module is to establish the directory structure, specifically by making a new folder called plugin/modules. This organization helps keep the module files separate and easily accessible. Next, we create our module, named remote-file-copy.py, which is structured to copy files from a source to a destination on a remote host. Within this file, we import the necessary Ansible module class from ansible.moduleutils.basic. This class simplifies the process of defining modules by managing input arguments and output results. We define a function called runModule, where we specify the parameters expected by the module, namely source and dest, both required string parameters. We initialize a result dictionary to track the operation status. In the try block, we simulate the file copying logic, preparing messages that indicate success or any potential errors. If the operation completes successfully, the module returns a JSON response with the results. In case of an error, we invoke fail.json to capture and return the error message. Finally, the main function calls run module, ensuring our module is executed when the file is run as a script. To properly document your module, you need to focus on the galaxy.yml file. This file contains essential metadata about your Ansible collection. In this section, you will define dependencies, tags, a version number, a description of the collection, and the license type. The version number is particularly important as it aids in tracking changes and updates to your collection over time. After updating the galaxy.yml file, the next step is to build your collection into a distributable format. You can conveniently achieve this using the Ansible Galaxy Collection Build command. This command compiles all your organized code into a single package, making it easier to share or install on different systems. Upon executing the build command, you will receive a .tar.gz file, which encapsulates your entire collection. This file is ready for installation or distribution. You can install it locally using the Ansible Galaxy Collection Install command, specifying the path to your newly created .tar.gz file. By completing these steps, you successfully create and install your first Ansible collection, setting the stage for a reusable and organized automation framework. To ensure our custom module functions correctly, we will create a playbook named collectiontest.yml. This playbook is designed to execute a simple task that utilizes our module to copy a file from the source path /tmp/foo to the destination path /tmp/bar. The playbook begins by specifying the hosts, which in this case is set to localhost, meaning the task will run on the local machine without gathering any facts to streamline the process. Within the tasks section, the first task uses the custom module practicalansible.examples.remote file copy to perform the file copy operation. It specifies the source and destination paths, registering the output of this operation in a variable called result. Following this, the second task employs the debug module to display the contents of the result variable, allowing us to see whether the file copy was successful. To execute this playbook and test our module, we simply run the command Ansible Playbook collection test.yml. Upon successful execution, we will receive an output confirming that our custom module has performed as expected, ensuring it is working correctly in practice. In conclusion, we have navigated through the exciting journey of creating your very own Ansible collection. From setting up the initial directory structure to writing a module, packaging your code, and testing it with a playbook, you've taken the essential steps necessary to harness the power of collections within Ansible. Creating custom collections is not merely a useful skill. It's an empowering ability that allows you to share, maintain, and deploy automation tasks more efficiently. As you get more comfortable with this process, you'll find ways to expand your collections with plugins, roles, and improving the documentation, further enriching both your projects and the community. So go ahead, experiment with your collection, and consider sharing your creations with others. The world of automation is vast, and by contributing your collections, you can help others tap into the same powerful tools you have developed. It's time to let your creativity flourish in the automation world. With that, I hope you enjoyed this tutorial and can't wait to see what you create next. Happy scripting! Ansible's code has always been designed to be modular. Indeed, this is one of its core strengths. When we talk about modularity in Ansible, it shines through the various components that constitute its functionality, allowing users to mix and match components to suit their specific needs. This modular approach not only enhances flexibility, but also makes Ansible an incredibly powerful automation tool. At the heart of this modularity lies a sophisticated system of plugins, which we will explore in depth in this tutorial. Ansible plugins are essentially extensions that help you customize and enhance the inherent capabilities of Ansible. Similar to how modules perform specific tasks, plugins perform various functions that support modules by adding functionality or customizing the behavior. However, unlike modules, plugins often operate behind the scenes, silently handling essential features that might otherwise go unnoticed during playbook execution. For instance, when you run an Ansible playbook, Plugins manage SSH connectivity and parse inventory files, which are pivotal to the successful automation of tasks. Now, why should we care about plugins? Well, understanding them opens up a world of customization that can greatly enhance how you use Ansible. Familiarity with plugin architecture aids in troubleshooting, optimizes your automation processes, and can even allow you to develop your own custom plugins tailored to your specific automation challenges. To bring this concept into focus, let's dive into the various types of plugins Ansible supports. One of the simpler types is the connection plugin. This type of plugin manages how Ansible communicates with remote machines over various network protocols such as SSH or WinRM. Each connection plugin addresses unique communication needs, making it important that you understand the connection type to use in your automations. Additionally, there are lookup plugins that enable Ansible to retrieve data from various sources. This can be anything from reading variables from a plain text file to accessing a database. Lookup plugins help streamline the integration of external data into your playbooks, which can be crucial for dynamic configurations. Another interesting category is callback plugins, which allow you to customize the output of your playbooks. For instance, if you want to change how task results are displayed, a callback plugin can modify the output format to better suit your needs. This makes it easier for teams to analyze results in a preferred format, enhancing collaboration and efficiency. When it comes to variable plugins, these are instrumental in sourcing variables from different configurations. They help organizations maintain a structured and scalable approach by leveraging host vars and group vars. Utilizing variable plugins can significantly simplify the management and retrieval of variables in complex environments. Now let's look at this figure. It presents a list of various Ansible plugins, providing insight into the capabilities that can be leveraged to extend Ansible's functionalities. Each entry in this list corresponds to a specific plugin, detailing its primary function or the environment it interacts with. The inclusion of both built-in and community plugins underscores the versatility that comes with using Ansible in different contexts. For instance, plugins like Ansible.builtin.ssh and Ansible.builtin.paramiko.ssh illustrate how Ansible can establish connections using SSH, highlighting different methods for executing tasks. This capability is crucial for managing remote systems, ensuring that users can tailor their connection strategies to meet specific use cases. Similarly, the community.docker.docker and community.docker API plugins focus on managing tasks within Docker containers, showcasing Ansible's strength in orchestrating containerized environments. In addition to these core functionalities, the figure also depicts specialized plugins such as community.abus.aws.nm, which enables integration with AWS Systems Manager, and community.lib.libvirt.lxc, allowing for interactions with LXC containers. This variety illustrates how Ansible can be applied across different platforms and technologies, facilitating seamless management in multi-cloud and hybrid environments. Overall, this diverse set of plugins emphasizes the customization potential within Ansible, enabling users to adopt the tools that best fit their operational needs. The ability to write custom plugins further enhances this flexibility, allowing organizations to fill gaps in functionality and tailor Ansible to their specific workflows. First, we start by creating a new Python file named customfilter.py. It is essential to include a header comment at the top of the file. This comment indicates the authorship and the licensing information, which is critical for open source projects to ensure proper attribution and compliance with licensing terms. Next, we define the core functionality of our filter. In this case, we implement a simple function named replaceWord, which takes an input string and replaces occurrences of the word Ansible with automation. This capability illustrates how filters can modify strings for various use cases in automation tasks. After defining our function, we proceed to create a class called FilterModule. This class plays a crucial role as it is recognized by Ansible as the mechanism for plugins. Within this class, we define a method named filters. This method returns a dictionary that maps the filter name, replaceWord, to the actual function we defined earlier. This structure allows Ansible to invoke our filter seamlessly when processing templates, enabling users to leverage the functionality we have just implemented. In this section, we will validate our custom filter by integrating it into a simple Ansible playbook named testplaybook.yml. The playbook is structured to run on the local host, and it defines a variable called statement, which holds a string. Ansible is a powerful automation tool. Within the tasks section, we utilize the debug module to output the value of statement after applying our custom filter, replace word. This filter is intended to demonstrate its functionality by modifying the original statement. Once we execute the playbook, Ansible processes the task and the output reflects the changes made by our filter. In this case, the output confirms that the string has been altered to automation is a powerful automation tool, thus showcasing the successful invocation of our custom filter. This illustrates the seamless integration of custom plugins within Ansible to suit specific automation needs, enabling users to enhance their playbooks with tailored functionalities. As we proceed to dig deeper, it's crucial to understand the testing and validation process for our plugins. Ansible encourages thorough testing. After all, a well-tested plugin ensures that automation remains robust and reliable. You can use standard Python testing libraries such as PyTest for this purpose. Testing plugins not only confirms functionality, but also ensures that any further modifications or new features don't inadvertently break existing functionality. To sum up, Ansible plugins are a powerhouse feature enabling extensive configurability and customization, allowing you to tailor automation to your precise needs. By taking advantage of existing plugins and developing your own, you can significantly enhance your automation workflows. Engaging in plugin development also opens the door to contributing back to the Ansible community. If you've created a plugin that you feel could benefit others, consider submitting it to the Ansible project as a pull request. This not only enriches the broader community, but also helps you gain recognition in the open source world. Plus, it's an excellent opportunity to refine your skills and collaborate with other talented developers. In conclusion, Ansible's modular design powered by plugins offers immense flexibility and capability, making it a robust tool for automation. Understanding the types and functions of available plugins, along with the process of creating your own, can dramatically enhance not just your productivity, but also the overall efficiency of your IT operations. So why not dive in and explore the world of Ansible plugins today? The possibilities are limitless. Now let's look at this figure. It presents the Ansible connection plugin for Paramiko, which is specifically designed to facilitate SSH connections in Ansible. This plugin is crucial for connecting to target hosts using the Paramiko library, particularly in environments where native SSH options may have limitations, such as older distributions. The parameters highlighted in this figure include key options that can be configured to optimize the connection experience. For instance, the banner timeout option specifies the duration in seconds that Ansible will wait for the SSH banner before timing out. This is manageable through environment variables or configuration files, allowing flexibility and easier management of SSH connections. Another vital option is Host Key Auto Add, which automatically adds host keys. This feature streamlines management by ensuring that newly encountered hosts are recognized without manual intervention, enhancing automation efficiency. Additionally, the host key checking setting controls whether to bypass the host key verification process. Setting this to false can help avoid connection interruptions due to unmatched host keys, but it should be used with caution due to security implications. Each of these options is tied into their respective sections, allowing you to adjust configurations seamlessly within Ansible. By understanding and utilizing these settings, you can enhance your automation workflow and ensure smoother connectivity to your target machines. Let's get started with creating a plugin. Although there are many similarities between coding modules and plugins, there are also fundamental differences. Each type of plugin that Ansible can work with is coded slightly differently and has its own specific recommendations. Today we'll dive into the world of custom plugins in Ansible, and I promise you'll walk away with the knowledge to craft your own. First, let's clarify what a plugin is within the context of Ansible. Plugins are essential components of Ansible's modular architecture. They extend functionality, interact with different systems, and facilitate various tasks like parsing inventory files and managing SSH connections. Unlike modules which execute specific actions, plugins perform background tasks and enhance the capabilities of your automation scripts. Before we jump into creating our custom plugin, ensure you have a Python 3 development environment set up. For those of you using Mac OS, Linux, or FreeBSD, you're in luck. You likely already have what you need installed. In our example today, we'll create a filter plugin, which is one of the simplest plugin types you can build in Ansible. So why a filter plugin, you ask? Well, filter plugins allow for data manipulation right within your playbooks by modifying variable values at runtime. Think of it as seasoning your dishes in the kitchen. A bit of spice can take your automation to the next level. To create your filter plugin, begin by establishing a directory structure that organizes your files effectively. You'll need a folder named Filter Plugins alongside your playbooks, as this is where Ansible will search for your custom plugins. Within this Filter Plugins directory, you should create a Python file, such as customfilter.py, to house the code for your filter. This clear and structured organization helps maintain your project and makes it easier for others to understand where to find specific components. In your Python file, it's essential to include a well-crafted header comment at the top. This comment serves multiple purposes. It credits the author yourself, includes the year of creation, and specifies the license under which your code is released. Utilizing an open-source license, like the new General Public License, demonstrates your commitment to sharing your work while protecting your rights as a developer. By adhering to these practices, you establish a professional standard in your code, fostering collaboration and transparency in your projects. In this section, we are defining a filtering function that will be used in our custom filter plugin. The replace word function is designed to take an input string and replace all instances of a specified word, old word, with a new word, new word. This simple yet effective function utilizes Python's built-in string method, replace, to accomplish this task seamlessly. To integrate this function with Ansible's filter system, we need to encapsulate it within a class named filter module. This class serves as a bridge between our custom logic and Ansible's filtering capabilities. Inside the filter module class, we define a method called filters, which returns a dictionary. This dictionary maps the name of our filter, replace word, to the actual replace word function we created earlier. By doing this, we are informing Ansible about our custom filter and making it available for use in playbooks and templates. Once you save this implementation in the customfilter.py file, you have effectively created a functional filter plugin that can be utilized within your Ansible automation workflows. In this section, we will walk through a simple playbook named myplaybook.yml that showcases the functionality of our custom filter. The playbook is designed to be executed on the local host, meaning it will run on the machine where you're executing the command. The gather facts directive is set to no, which speeds up execution by skipping the gathering of system facts. Within the playbook, we define a variable, myString, which holds the text, "This is an old word that needs to be replaced." The primary objective here is to demonstrate the usage of our custom filter, replace word. The task specified in the playbook utilizes the debug module to display a message. The message constructed through the debug task applies our replace word filter to myString. When the playbook is executed, the output should reflect the original string with old word replaced by new word. This clear example illustrates how you can easily extend Ansible's capabilities and create a practical filter plugin with minimal coding effort. In the provided code snippet, we see a documentation block defined as a multi-line string, which is essential for creating a clear understanding of what the plugin does. This documentation follows a structured format that gives users important insights into the plugin's functionality. The first line introduces the author, allowing users to see who is responsible for the code, which can be particularly helpful for feedback or inquiries. The short description quickly summarizes the purpose of the plugin, stating that it is designed to replace a specified word in a string. Such succinct information is crucial as it allows users to grasp the core functionality at a glance. Further down, the detailed description elaborates on how the plugin operates, It specifically mentions that the filter will replace all occurrences of old word with new word. This ensures that users understand the exact behavior of the plugin before utilizing it. Lastly, the options section outlines the parameters accepted by the plugin. In this case, it specifies an input string that the user must provide, highlighting the requirement for this input to ensure proper functionality. This structured documentation ensures users can effectively implement and utilize the plugin. In this code snippet, we define a function called replace word, which is designed to replace occurrences of a specific word within a string. The first step in our function is to validate the input to ensure it meets the expected criteria. We use the isInstance function to check if the provided argument input string is indeed a string. This is a crucial error handling measure because it anticipates potential issues with user input. If the input is not a string, the function raises an Ansible error, providing a user-friendly error message that clearly indicates the requirement for the input to be a string. This proactive approach prevents confusing error messages that could arise from incorrect input types, thereby enhancing the user experience. When the input validation passes, the function then proceeds to replace all occurrences of the word old word with new word using the replace method. The result is returned to the caller, allowing the user to receive the modified string as intended. This concise structure of the function emphasizes both functionality and robustness in handling input errors effectively. Now let's look at this figure, which displays the GitHub repository for Ansible. At the top, we can see the repository name, Ansible, along with the user or organization it's associated with, providing a clear identification of the project. Notably, the figure presents key repository details such as the current branch, which is set to Devel. This indicates that the development branch is actively maintained and is the focus for upcoming features and fixes. To the left, we see important metrics related to the repository. There are 50 branches and 497 tags, showcasing the project's active development and release managed metrics. The figure lists various folders and files, such as GitHub, Docs, and lib/Ansible. Among these, the lib/Ansible/plugins filter directory stands out, as this is where our custom filter plugin, customfilter.py, needs to be placed for proper integration into the Ansible ecosystem. On the right side of the figure, there's the code button, which allows users to clone or download the repository. This feature is essential for anyone looking to contribute to the project. Below that, we can see a commit history that highlights recent changes, including a notable commit by memkrizek preventing arbitrary attribute settings on Jinja 2 environments via overrides. This level of detail underlines the collaborative nature of the project, where developers can track contributions and modifications over time. As we move down, the folder structure reveals additional directories such as examples and hacking, which may contain useful resources for both developers and users. The organization of these folders indicates a well-structured project where contributors can easily find the necessary components to enhance their understanding and contributions. This figure serves as a visual representation of the essential steps and organization required when sharing your custom plugin with the Ansible community, emphasizing the importance of adhering to the established project structure for successful collaboration. With that, you are now armed with the knowledge to create compelling custom plugins within Ansible. You've learned the essentials of plugin structure, development best practices, and the importance of documentation and error handling. So go ahead and try creating more complex plugins. Maybe consider a lookup plugin that interacts with an external database, or a callback plugin that accumulates performance metrics during Playbook runs. The opportunities are endless. And remember, the community thrives on your contributions, so don't hesitate to share your unique solutions. There you have it, folks, a complete guide to creating custom plugins in Ansible. If you found value in this tutorial, be sure to give it a thumbs up and subscribe for more insightful content. I can't wait to see what plugins you all come up with. Until next time, happy automating. Ansible can help you automate almost all your daily IT tasks, from mundane tasks such as applying patches or deploying configuration files, to deploying entirely new infrastructure as code. The use of and engagement with Ansible has been growing year by year as more and more people realize its power and simplicity. You will find many examples of Ansible playbooks, roles, blog articles, and so on across the internet, and combined with resources such as this book, you will become proficient at writing your own Ansible playbooks. However, with this power comes the need for best practices to ensure that your Ansible code remains manageable, effective, and efficient. This video will guide you through the essential coding best practices for Ansible, equipping you with the knowledge to optimize your automation efforts while avoiding common pitfalls. The provided directory structure for an Ansible project is organized into several essential components that enhance clarity and efficiency. At the top level, you have the Inventories folder, which is crucial for defining the target hosts for your automation tasks. Inside, the Development subdirectory contains the Hosts file, where the actual inventory of machines is listed, and the Group Vars folder, which holds variable files like app.yml, allowing for easier management of variables associated with specific groups of hosts. Next, the Roles directory is a vital feature of Ansible, promoting reusability and modularity. Within it, the Install App role consists of several subdirectories. The Tasks folder includes a main.yml file that outlines the steps necessary to install the application. Meanwhile, the Templates, Handlers, and Vars directories serve to manage files, notify services when changes occur, and define additional variables, respectively. Finally, the site.yml file at the root level acts as the primary entry point for executing all playbooks, thereby unifying the project structure and facilitating clarity in automation workflows. This organized layout not only aids initial navigation, but also simplifies future scaling and maintenance efforts of your automation project. Next, let's discuss the importance of differentiating environments. In a typical development lifecycle, you'll likely have separate environments for development, testing, and production. It's critical to keep these environments isolated, not just for safety's sake, but also to facilitate testing and scalability. If you're working with Ansible, aim to use the same playbooks across your environments. For instance, consider the differences in an application deployment between development and production environments. Configuration files, database connections, and API endpoints might change, but the core code should stay the same. By structuring your inventories accordingly, you can redefine only the variables that need to be different between environments, preserving consistency and reducing the likelihood of human error. In the provided example, we define a variable HTTP port for a web application using Ansible's variable management system. In the group variable file located at Inventories Development Group Vars app.yml, the HTTP port is initially set to 8080. This configuration serves as a default value for all hosts within the defined group. However, to allow for more granular control, we have a host-specific variable file at inventory/development/host-vars/app01.devexample.com.yml. In this file, we redefine HTTP port to 9090 for the server app01.dev.example.com. This demonstrates Ansible's variable precedence where host-specific variables take priority over group variables. When the playbook is executed, querying the HTTP port variable on app01.devexample.com will reflect this host-specific value, returning 9090. This flexibility enables the customization of settings on a per-host basis, while still maintaining a general configuration at the group level, ensuring a streamlined management experience across different environments. Another key aspect of Ansible best practices is the implementation of version control. Using a system like Git, you can manage changes to your playbooks and roles, which allows you to keep track of revisions, collaborate with team members, and quickly revert changes when something goes wrong. Your Ansible automation code is often critical to your operation, as a broken playbook might lead to downtime or service interruptions. A best practice here is to maintain your entire Ansible project, playbooks, roles, inventories, and any custom plugins or modules within a single repository. This way, your team can work on the same projects and ensure they are using the same versions of the code base, which is especially important for collaborative environments. The provided code snippet represents a basic structure of a top-level playbook in Ansible, commonly named site.yml. In this playbook, the first line indicates the start of the YAML document, which is a format widely used for configuration files. The next line specifies the play's name as Deploy My Application, signifying the primary purpose of the playbook. The host's all directive specifies that the tasks defined in this playbook should be executed on all hosts listed in the inventory file. This ensures that the application deployment is not restricted to a subset of the available machines, facilitating a comprehensive rollout. Finally, the roles section indicates that this playbook will utilize the install app role. Roles in Ansible allow for modularization of tasks, making it easier to manage and organize automation code. By calling the install app role, the playbook encapsulates all related tasks needed for the application installation, showcasing the power of roles to simplify the top-level structure and maintain clarity. This organization is particularly beneficial for new team members, as it provides a clear entry point into the automation process. This playbook is designed to install Apache Web Server on different Linux operating systems, CentOS and Ubuntu. It begins by targeting all hosts in the inventory. Within the tasks section, there are two distinct tasks aimed at installing Apache, each conditioned to run on its respective operating system. The first task uses the Yum package manager, which is specific to CentOS. It attempts to install the HTTPD package, essential for running an Apache server. The task is gated by a when clause that checks if the detected distribution is CentOS. If this condition is met, the installation proceeds as intended. Conversely, the second task caters to Ubuntu using the app package manager. Here it seeks to install the Apache 2 package. Similar to the first task, it employs a when clause to ensure that this task only executes if the system is recognized as running Ubuntu. This strategic use of conditional statements allows for a versatile playbook that adapts to different operating environments while maintaining a clean and unified codebase. As we wrap up, remember that following these best practices in Ansible coding will greatly enhance your automation efforts. Structure your directories well, differentiate your environments clearly, pay attention to variable precedence, utilize version control rigorously, and adapt your playbooks for operating system variances. Each of these practices contributes to a more manageable, understandable, and robust infrastructure management process. Through diligence and the strategic application of these best practices, you will not only improve your coding skills, but also empower your team to operate with greater efficiency and reliability in an increasingly complex technological landscape. Keep practicing, stay curious, and happy Ansible automation. Ansible has become a go-to tool for many systems administrators and DevOps engineers due to its simplicity and powerful capabilities for automation. So what happens when you've mastered the basics and are ready to delve deeper? In this session, we'll explore some advanced techniques in Ansible to help you tackle those tricky scenarios that often arise in real-world automation. Buckle up, you're in for a ride. Now, let's shift our attention to the figure. This diagram illustrates the core components of an Ansible setup, starting with the Ansible management node. This is the central hub from which all automation tasks are orchestrated. It connects to the target devices without needing any agents installed on those systems, showcasing the agentless nature of Ansible. Next, we see the two essential elements that support the automation process: the host inventory and the playbook. The host inventory is represented by a stack icon, indicating a collection of target devices that Ansible can manage, including the specific example IP address 192.168.1.201. This is where you define the devices you want Ansible to interact with. The playbook, depicted with a document icon, is where the instructions for the automation tasks are written. Within this playbook, you define specific tasks, modules, and roles that detail the actions Ansible should perform on those target devices. This structure allows for high customization and reusability of scripts, easing the process of expanding your automation strategies. Lastly, the diagram emphasizes the SSH trust connection between the Ansible management node and the target device. This trust is vital as it establishes the secure communication channel required for executing the tasks defined in the playbook on the remote system. The arrow pointing towards the target device underscores the flow of commands and the seamless execution of automation, reinforcing the efficiency that Ansible offers for managing multiple systems effortlessly. In the provided Ansible Playbook snippet, the task is to group hosts dynamically based on their operating system. The playbook initiates with a declaration of its name and specifies that it targets all hosts defined in the inventory. The first task within the playbook utilizes the Group By module, which is a powerful feature in Ansible that allows for the creation of dynamic inventory groups. Here, the key for the new inventory group is constructed using the host facts associated with each machine. Specifically, it employs Ansible Facts Distribution, which retrieves the operating system distribution name of the host, such as Ubuntu or CentOS. By prefixing this with OS scores, the playbook ensures that the hosts are organized into groups like OS Ubuntu and OS CentOS. This approach streamlines the management of mixed OS environments by eliminating the need for multiple playbooks. As a result, you can run tasks targeted at specific groups, simplifying the code base and enhancing its maintainability. The dynamic nature of the grouping allows for flexible deployments and changes within the infrastructure without requiring significant alterations to the playbook itself. The provided code demonstrates how to install web servers on different operating systems using a single playbook in Ansible. First, the code initiates a task to install Apache on CentOS, targeting the group of hosts labeled as OS CentOS. It utilizes the yum module to install the HTTPD package, ensuring that the Apache HTTP server is present and active on the designated CentOS machines. Following this, the playbook continues with a task dedicated to Ubuntu systems, where it installs Apache using the apt module. This task targets hosts labeled as OS Ubuntu and installs the Apache 2 package, also validating that it is in the present state. By structuring the playbook in this way, you can easily manage the installation process for different operating systems without the need for multiple playbooks or hard-coded commands. This consolidated approach streamlines your workflow, reduces complexity, and enhances the manageability of your server environment. This method exemplifies a practical use of Ansible to automate server configuration efficiently. In this scenario, we have two definitions of the variable HT port across different files in an Ansible playbook hierarchy. The first definition appears in the group vars/all.yml file, where HTTP port is set to 880. This value establishes a default for all hosts managed by the playbook, providing a common configuration for HTTP traffic. However, in the specific group vars/app.yml file, the HTTP port variable is redefined with a new value of 8081. This reassignment indicates that for the hosts belonging to the app group, the HTTP traffic should be routed through port 8081 instead of the default 8080. Ansible operates under a predetermined hierarchy when it comes to variable precedence, meaning that group-specific variables, such as those found in group vars/app.yml, will override more general variable definitions, like those in group vars/all.yml. As a result, when executing the playbook, any host within the app group will recognize HTTP port as 8081, allowing for tailored configurations suitable for that specific application group. The provided directory structure outlines a well-organized approach to managing Ansible inventories for different environments, specifically development and production. At the top level, there is an inventories directory that acts as a container. Inside this, you will find separate folders for development and production, each tailored to their specific needs. Within both environment directories, there is a group vars directory. This is where you define variables that will apply to all hosts within a given group. For instance, the app.yml files in both the development and production folders can have different configurations, allowing you to set environment-specific parameters such as database connections, API keys, and other settings. Additionally, each directory contains a hosts file, which lists the target machines for that specific environment. By maintaining distinct directories and variable files, you ensure that your playbooks dynamically adapt to different scenarios, enhancing your deployment's flexibility and reducing the risk of errors associated with configuration mismatches. This structure exemplifies best practices for managing complex deployments with Ansible. Now let's discuss version control. As your playbooks evolve, versioning becomes vital. Whether you're sharing code with a team or deploying across different environments, having your automation code in a version control system like Git is a best practice. With Git, you can collaborate more effectively, track changes, and even roll back if something goes awry during deployments. Here's a little humor. Remember, with version control, if it breaks, you can just go back to the future. By managing your Ansible scripts in a Git repository, you protect yourself against unplanned changes, allowing for greater confidence in the stability of your deployments. In the provided code snippet, we see a YAML representation of an Ansible playbook designed to deploy web applications. The playbook is defined under a single task named Deploy Web Applications for all targeted hosts in the inventory. The primary feature here is the use of roles, which facilitates a modular approach to automation. By specifying the roles section, the playbook outlines two distinct roles, web server and database. Each role encapsulates specific tasks and configurations related to setting up a web server and a database, respectively. This allows for organized and reusable code, enhancing efficiency and maintainability. As a result, when this playbook is executed, it ensures that both the web server and database configurations are applied seamlessly in one go. This eliminates the need to manage multiple playbooks for different components, streamlining the deployment process and making it easier to maintain complex environments. By merging roles like this, you harness the power of Ansible's capabilities to automate and orchestrate infrastructure setup effectively. Now, let's talk about porting your code between Ansible versions. As Ansible frequently updates, bringing new features and deprecating old ones, being aware of changes that might affect your playbook is essential. Always check the changelog for the version you're planning to upgrade to. For example, if migrating from Ansible 2.8 to 2.9, you might find some modules deprecated, so it's critically important to review both the porting guide and the changelogs to make necessary adjustments to your playbook. Now let's look at this figure, which illustrates the evolution of network automation over time. The horizontal axis represents time, spanning from 1960 to 2050, while the vertical axis indicates the progression in the sophistication of network automation technologies. At the beginning of the timeline, we see siloed networking, characterized by isolated systems that offer limited interconnectivity. As we move along the timeline into the 1980s, tools like NetFlow, SNMP, and syslog emerge, marking the initial efforts toward more integrated network management. These tools laid the foundation for better visibility and monitoring within networks. Progressing into the 2000s, we encounter software-defined networking. This innovation shifts the paradigm by allowing networks to be controlled through software rather than hardware alone, facilitating a more agile and dynamic approach to network management. Following this, intent-based networking comes to prominence, emphasizing the need for networks to understand user intent and automatically adjust configurations to meet specific business goals. As we near the present and future, AI-driven autonomous networking represents the cutting edge of this evolution. This concept utilizes artificial intelligence to create networks that can self-manage and adapt in real time, significantly enhancing operational efficiency. The figure also features several key tools and platforms, such as Ansible, Terraform, Puppet, and Zabbix, illustrating the diverse technologies that have contributed to this evolution. In summary, this figure encapsulates the transformative journey of network automation, highlighting how advancements in technology have fostered increasingly sophisticated systems capable of meeting modern demands. Up to this point, we have worked hard to give you a solid foundation in Ansible so that, whatever your desired automation task, you can implement it with ease and confidence. However, when you really start to ramp up your automation, how do you ensure that you can handle any condition that arises in a graceful manner? Today, we will dive into the advanced features of Ansible that will expand your automation skills to new heights. Think of these as the superpowers in your Ansible toolkit. So grab your favorite beverage, kick back, and let's get started. In this playbook, we are demonstrating how to implement asynchronous tasks in Ansible to avoid blocking operations during long-running processes. The playbook is structured to run on a group of hosts labeled frontends, with elevated privileges enabled through the become directive. Within the tasks section, we define a simulated long-running task that utilizes the shell module. This task simply executes the command sleep20, which pauses for 20 seconds. The key parameters utilized here are async and poll. By setting async 30, we indicate that Ansible should consider the task a failure if it hasn't completed within 30 seconds. Meanwhile, the poll 5 parameter instructs Ansible to check the task status every 5 seconds. This configuration allows the playbook to initiate the task and immediately move on to any subsequent tasks without waiting for the sleep operation to finish. As a result, we can seamlessly manage long-running tasks without risking SSH timeouts or blocking the deployment process. This method allows for greater efficiency when handling deployments across multiple servers. In this rolling update example, we define an Ansible playbook that targets a group of servers classified as frontends. The playbook uses the serial keyword, which is set to 2, indicating that the update will process 2 servers at a time. This batching approach is crucial for minimizing downtime during updates, particularly in a load-balanced environment. The primary task within this playbook is to update a package, in this case the HTTP server labeled HTTPD, and then restart the associated service. By executing the update in batches, Ansible allows you to monitor the process closely. After the first 2 servers are successfully updated and their services restarted, it waits for these tasks to complete before proceeding to the next pair. This method ensures that your application remains available throughout the update process, as there are always operational servers ready to handle incoming traffic. By managing updates this way, you not only reduce the risk of service disruption, but also enhance the overall user experience during maintenance activities. In this Ansible playbook, we start by controlling the maximum failure percentage during deployment, which is essential when working with multiple servers. The playbook is configured to operate on a group of hosts defined as frontends, ensuring that it does not gather unnecessary facts to streamline the process. The serial directive specifies that the playbook will process 5 hosts at a time, which helps manage load and mitigate the risks involved in deploying changes. A critical parameter here is max fail percentage, set to 20%. This indicates that if more than 1 out of the 5 hosts in a batch fails, the play will terminate. This safeguard prevents widespread failure and ensures that your service remains operational during updates. Within the tasks section, there's a debug task that might intentionally fail based on the evaluation of the condition failed when. This condition is crafted to simulate failure selectively, determining if the current host is part of the first 2 hosts in the batch using the Ansible playBatch variable. This setup allows for controlled testing of failure scenarios while still adhering to the defined limits on failures. This playbook demonstrates the concept of task delegation within Ansible, specifically targeting operations that need to be run on the control machine rather than on the individual hosts listed in the play. The playbook is designed for the frontends group of servers, where the first task involves removing a server from the load balancer. By using delegate to localhost, the execution of the remove from loadbalancer.sh script occurs on the control machine, ensuring that the load balancer commands are handled efficiently and centrally, rather than being run on each front-end server. Following the removal of the server, the playbook includes a debug task that serves as a placeholder for deployment actions. This indicates where additional code could be implemented as needed. Finally, the playbook concludes by adding the server back to the load balancer, utilizing the add to loadbalancer.sh script, again leveraging delegate to localhost. This setup exemplifies how Ansible can effectively manage services across multiple servers while executing specific tasks on the control node, leading to more streamlined operations and improved resource management. In this playbook, we define a task that is intended to run only once across a specified group of hosts, specifically the frontends. The run once directive is crucial when you want to avoid redundant execution of a task that needs to be performed only a single time, regardless of the number of hosts being managed. The task included in this playbook focuses on upgrading the database schema. By utilizing the debug module, the Playbook generates a message indicating that the database schema is being upgraded. Even though this playbook may be executed across multiple hosts, in this case, potentially 10, the upgrade message will display only one time. This ensures that the database schema is upgraded without unnecessary repetition, thereby streamlining the process and reducing workload. In scenarios such as setting up a cluster or performing system upgrades, the run once directive is particularly valuable, as it enhances efficiency by preventing multiple executions of tasks that fundamentally only need to occur a single time across all targeted hosts. In this configuration snippet, we are setting up an SSH connection to a target host, referred to as myTarget, by utilizing a jump host called jump host. The host directive specifies a block of settings that apply to a particular SSH connection, in this case targeting myTarget. By defining this specific host, we can customize how we connect to it based on our network environment. The key element here is the proxy jump option, which facilitates the use of the jump host. When accessing myTarget, the SSH client first connects to jump host and then forwards the connection to the intended target. This not only helps in circumventing network restrictions, but also enhances the security of your connections by isolating direct access to sensitive environments. With this setup, any Ansible playbook executed for myTarget will transparently use the jump host without the need for additional adjustments in the playbook itself. This streamlines the management of remote servers, allowing you to operate as if you are directly connected, thus simplifying the overall process of handling your infrastructure in secure zones. In this Ansible playbook example, the vars course prompt section is employed to collect user input when the playbook is executed. First, the playbook specifies the target hosts under the hosts directive, which is set to frontends. This indicates that the tasks defined in the playbook will be executed on the front-end servers. The playbook then defines two prompts using the vars prompt feature. The first prompt requests the user to enter their username with the variable name loginid. This prompt is set to be visible to the user as indicated by private no, allowing for straightforward interaction. The second prompt requests a password defined by the variable password with the private yes attribute. This ensures that the password input is masked, enhancing security by preventing onlookers from seeing sensitive information. Once the inputs are collected, the task specified under Tasks executes a log message. The debug module is utilized here to output a message indicating the user is attempting to log in using the provided username. Overall, this setup facilitates interactivity while maintaining security for sensitive credentials. To securely store sensitive information, the first step is to create a vault file using the command ansible-vault create-secrets.yml. This command opens an editor where you can input your confidential data, such as passwords or API keys. Once the data is saved, it will be encrypted, ensuring that it does not remain in plain text. In your playbook, you can utilize this encrypted file by including it in the vars files section. The provided example demonstrates how to integrate the vault file by specifying secrets.yml within the playbook setup. The playbook is named Using Ansible Vault and is intended for the hosts labeled as frontends. When executing this playbook, Ansible will prompt you for the vault password to access the encrypted data. This mechanism ensures that sensitive information is only accessible during runtime while keeping it secure throughout the automation process. The task included in the playbook uses the debug module to display the secret data, emphasizing how to work with encrypted variables safely. As we wrap up, remember that mastering these advanced features of Ansible enhances not only your automation capabilities, but also your ability to manage complex environments securely and efficiently. Like any superhero, your Ansible skills are about to become formidable tools for managing infrastructure. You'll be the Ansible wizard of your team, solving more problems with less stress. So take these skills, practice them, and you'll soon find yourself automating with grace and precision. Thank you for joining me on this journey through Ansible's advanced features. Happy automating. Ansible Vault is a powerful tool included in Ansible that provides a secure method for encrypting sensitive data, making it an essential component when you're managing automation at scale. So let's dive in, shall we? Understanding the significance of securing sensitive data is critical. Imagine you're working on an Ansible playbook where you need to store passwords, API keys, or any secret data. Leaving this information exposed is like leaving the door wide open. There's a real risk of unauthorized access. Hence, encryption becomes our knight in shining armor. When automating tasks in a playbook, managing sensitive information such as database credentials or API keys is crucial for maintaining security. To address potential vulnerabilities, Ansible provides a feature called Ansible Vault, which encrypts sensitive data and allows you to utilize it securely within your playbooks. The command Ansible-vault create secret.yml is how you initiate the creation of an encrypted vault file. By executing this command, you instruct Ansible to create a new file named secret.yml, specifically designed to store confidential data securely. Upon running this command, you'll be prompted to enter a password that will protect the contents of the vault. It's critical to choose a strong password and remember it, as this password is your key to accessing or modifying the vault in the future. By encrypting the information within the vault, you can confidently use it in your automation processes without exposing sensitive data, ensuring both functionality and security in your operations. When you enter the password, your default text editor launches, enabling you to input variables. In this case, the variable is represented in YAML format, starting with 3 dashes, which indicates the beginning of a document. The key secret data is assigned the string value, Ansible is cool. This simple format allows for easy readability and organization of configuration data. After you save and exit the editor, you should check the contents of the secret.yml file. You will see that the data format has fundamentally changed. The information is now encrypted. This encryption is accomplished using AES 256, a robust security standard that ensures the sensitive data is protected from unauthorized access. By employing AES 256, any secrets or private information are transformed into an unreadable format, thus maintaining confidentiality. As you proceed with your tasks, it's crucial to remember that this encryption serves as a safeguard, ensuring that even if someone gains access to the file, the actual data remains secure and private. In this segment, we explore how to incorporate encrypted information into an Ansible playbook utilizing Ansible Vault. The playbook uses the vars files directive to reference a vault file named secret.yml, which contains sensitive data. By including this file in the playbook, you can access its contents as if they were regular variables. When executing the playbook, it's crucial to provide the vault password to Ansible. This is done using the ask vault pass command line option. This prompts you to enter the vault password securely, ensuring that your sensitive information is protected during runtime. After you input the password, the playbook runs and you can see the output revealing your secret data. Specifically, the task defined within the playbook utilizes the debug module to display a message that includes the decrypted secret data. This shows how seamlessly encrypted information is integrated into your Ansible workflows, enabling you to maintain security without sacrificing functionality. To encrypt a string using Ansible, you can utilize the Ansible Vault Encrypt String command. For instance, the command Ansible Vault Encrypt Score String, Ansible is cool, name secret data is used to encrypt the phrase Ansible is cool and assign it the variable name secret data. This allows you to securely store sensitive information directly within your playbooks. The output generated by this command is an encrypted string that begins with Ansible Vault 1.1 AES 256, followed by the encrypted content. In your playbook, you would represent this encrypted data under the vars section as shown. Vars and secret data vault. Here, the vault indicator indicates that the following content is encrypted. When you run your playbook, as long as you provide the vault password, Ansible will decrypt the string, and you can use secret data within your playbook seamlessly. Thus, while it's essential to secure your vault passwords, this approach allows you to handle sensitive data effectively without the need for a separate vault file. Now let's look at this figure. It illustrates the integration between Red Hat Ansible and CyberArk's Vault and Conjure solutions. At the center, we see Red Hat Ansible, a powerful automation tool that streamlines operations and enhances efficiency in IT workflows. On the left, we have CyberArk Vault and CyberArk Conjur, positioned above one another. CyberArk Vault is designed for secure storage and management of sensitive credentials, providing a reliable foundation for security automation. Below that, CyberArk Conjur extends this functionality by enabling DevOps teams to securely manage secrets across applications and environments. The arrows connecting these components emphasize the flow of data and security measures between the two CyberArk solutions and Ansible. On the right side of the figure, we can see various automation domains that this integration supports. Each domain is represented by an icon and labeled Security Automation, Cloud Automation, DevOps Automation, and Network Automation. This layout clearly conveys that by using Ansible in conjunction with CyberArk, organizations can enhance automation across multiple domains while maintaining a focus on security. This figure effectively illustrates how these tools work together to not only streamline processes but also safeguard sensitive information, reducing the risk of leaks and unauthorized access. Be sure to keep this in mind as you implement your automation workflows. In the context of managing multiple Vault files securely, using a consistent password across all files is essential when you're working with them together in your group vars directory. This uniformity simplifies the management of sensitive data and maintains a secure environment. To enhance automation in CI/CD pipelines and avoid exposing passwords and scripts, you can leverage the DAF Vault password file option with the Ansible Vault command. By specifying a password file, such as .vaultpass.txt, you automate the process of entering your Vault password. This not only streamlines your workflow, but also adds an extra layer of security by keeping sensitive information out of your code. The command ansible-vault-playbook.yml-vault-password-file.vaultpass.txt demonstrates this technique. Here, the Ansible Vault processes the playbook.yml while securely authenticating using the password stored in .vaultpass.txt. This approach allows you to execute your playbooks seamlessly and securely without needing interactive password prompts, making it ideal for automated environments where efficiency and security are paramount. The command you see, Ansible Vault edit secret.yml, is a powerful tool provided by Ansible for managing sensitive data securely. When you execute this command, you're instructing Ansible to open the specified file, in this case, secret.yml, in an encrypted form. This allows you to access and modify the contents while ensuring that sensitive information remains protected from unauthorized access. Using Ansible Vault to edit files means you can maintain your sensitive data securely, without the risk of exposing credentials and other private information in version control systems like Git. This is especially invaluable when working in teams, as it allows all team members to utilize their secure passwords without compromising security. Everyone can collaborate effectively while ensuring that sensitive information stays confidential. After editing, the data within secret.yml will remain encrypted, preserving its security even as changes are made. This workflow not only enhances security, but also simplifies the management of sensitive information, making it easier to work collectively on critical tasks while safeguarding essential data. I hope you stayed with me through this journey of understanding Ansible Vault. Remember, securing sensitive data is not just a best practice, it's a necessity. As we embrace automation and cloud infrastructures, security upholstery must remain woven into our processes. So keep your vaults locked, your passwords safe, and automate away with confidence. Thank you for sticking around, and remember to like, subscribe, and hit that notification bell for more Kubernetes and Ansible adventures. Happy automating, folks! Modern large-scale infrastructures that change rapidly necessitate the automation of network tasks. This phrase encapsulates a significant shift in how we manage networking in the tech industry. As we dive deeper into the topic, we'll explore the why behind network management automation with an engaging tutorial that's hopeful, funny, and educational. So grab your virtual hard hats and let's build our knowledge. Many of you might wonder, why should I bother automating my network management? Imagine you're trying to build a Lego set. Only this set consists of millions of tiny blocks. You could assemble it by hand, piece by piece, doggedly putting everything together one step at a time. But if you had a machine to help automate the assembly, wouldn't you want to use it? This way, you can avoid human error, keep your time focused on creative design, and finish your project more efficiently. This analogy is relevant for automating network management, where complexity and the need for speed align. Automation is the builder's machine of choice. To understand why network management automation is essential today, let's take a step back into the not-so-distant past. In the 1990s, data centers looked vastly different. Every server was a physical machine uniquely built with specific hardware and software. Each time a company needed a new machine, there was a significant lag in delivery due to the extensive provisioning, configuration, and setup processes involved. This meant several things. Many devices went underutilized, and the waiting time between identifying the need for a machine and getting it was often numerous, frustrating weeks. Fast forward roughly 30 years, and the landscape has radically changed. Companies now rely on virtualization, an elegant magic trick where physical limitations disappear into a pool of resources from which virtual machines can be spun up with just a few clicks. Fancy that. Imagine a magic wand in the IT world that conjures machines into existence. But while virtualization eases server deployment and enhances efficiency, it also creates new challenges in managing those fast-moving machines and their network configurations. As workloads shift from physical to virtual, they transition across different hosts, move to various physical switch ports, and guess what? Require persistent attention. Here lies the crux, the resemblance to our Lego problem. Manual intervention in today's dynamic and expansive environments is simply no longer feasible. With the rapid pace of infrastructure changes, humans couldn't possibly keep up without making mistakes. Hence, automation arises not only as an option, but as a necessity. Speaking of human error, let's take a quick comedic detour. Imagine trying to configure a VLAN on 100 devices manually. It's like playing whack-a-mole, right? You hit one configuration, and another pops up somewhere else, usually in the form of a typo or a missing configuration rule. Oops, sounds familiar? Even seasoned network engineers can make mistakes when performing mundane tasks repeatedly. With each manual step, the chance for typo-induced chaos escalates. Now, this brings us to another compelling reason for automation: reducing human error. A significant advantage of automating network management is the drastic reduction in these errors. When you automate the configuration across devices, you enforce consistency and standardization. Remember those strong instructions that come with assembling Lego sets? Yeah, network automation offers similar blueprints to help you avoid headaches down the line. Automation isn't merely about avoiding pitfalls, it's also about maximizing efficiency. Think about the time saved by automating mundane tasks. If a network engineer expends too much energy on simple configurations, they miss out on the creative and strategic aspects of their job. Ultimately, automation shifts the focus from day-to-day reactive tasks to proactive network management and innovation. Now, let's break this down further. We know that large-scale cloud providers have gone down the path of network automation. These organizations operate at such a scale that it boggles the mind. We're talking about comprehensive networks that change not just a few configurations, but potentially thousands of device parameters in mere milliseconds. Automation allows these organizations not only to survive, but thrive in intensely competitive environments. This Ansible playbook is designed to check the connection status of network devices categorized under the group routers. The playbook begins by specifying that it will not gather facts automatically, which can speed up execution when those details are unnecessary. The first task within this playbook utilizes the cisco.ios.ios facts module to gather essential information about each router's configuration and status. This step is crucial as it collects data that can be used to assess the overall health of the network devices before executing any commands. The second task ensures that the interfaces on each router are operational. It employs a condition using the when clause, which checks if the current interface is defined within the gathered facts. The command executed here is show IP interface brief include up, which retrieves a summary of the interface status, filtering to show only those that are currently up and operational. By automating these tasks in Ansible, network administrators can efficiently monitor the status of multiple routers simultaneously, significantly reducing the time and effort required compared to manual checks on each device. Let's also consider rapid deployment. The faster you can provision, configure, and troubleshoot virtual machines over the network, the more responsive your IT infrastructure becomes to business demands. In fact, think of network automation as your express lane in the busy, frantic world of networking. Instead of languishing in long queues of configurations and manual checks, automated configurations smoothly guide changes along. So, to recap, network automation is imperative because of its potential to eliminate human error, save time, facilitate rapid change, and allow engineers to focus on strategic initiatives rather than trivial tasks. It's no longer just a fancy tool. It's a necessity for business continuity and growth in our fast-paced digital world. Now let's look at this figure, which showcases a snippet of code related to data filters within a network management context. The focus here is on defining parameters for an Infoblox IPv4 network container. At the top, you can see the data declaration for Infoblox IPv4 network container, where Cloud Container specifies the resource type being configured. The filters block is essential as it establishes criteria for querying the network views. The first filter, Network View, pulls the value from var.network view, effectively specifying the network view in which the container exists. Following this, we see the wildcard filters, Cloud, Region, and Stage. Each of these plays a pivotal role in narrowing down results by integrating values from specific variables like var.cloud, local.cloud_region, and var.stage. This modular approach allows for dynamic querying and integration, emphasizing how automation can streamline network configurations. By using wildcard characters, the filters enable flexibility in matching various cloud configurations and stages, which is crucial in adapting to changes in real-time network environments. Such structured data management through automation not only simplifies the process for network engineers, but also empowers them to focus on more strategic initiatives rather than routine troubleshooting tasks. This illustration highlights the importance of automation in enhancing operational efficiency, pushing the boundaries beyond mere maintenance toward fostering innovation within network management. Ansible has revolutionized the way we manage our networking devices, bringing efficiency and consistency to network management. In this video, we're going to dive deep into how Ansible manages a plethora of networking devices, including giants such as Cisco, Arista, and F5, just to name a few. Buckle up, we're in for an insightful ride. Before we explore the specifics, let's set the stage. Remember a time when configuring network devices was a manual process, every command carefully typed by hand? Times have changed. With the modern IT landscape's complexity, automation has shifted from being a luxury to a necessity. The rapid pace at which environments change makes manual configuration not only impractical, but also prone to errors. Enter Ansible, your trusty automation ally. Ansible allows you to manage a diverse array of networking devices, including Arista EOS, Cisco ASA, Cisco IOS, Cisco ISXR, Cisco NXOS, and many others. Yes, we're talking about devices from various vendors like Dell, Extreme Networks, F5 Big IP, Junos OS, and even white box switches running systems like Cumulus Linux. With Ansible, the days of being vendor-locked are long gone. Instead, we have the freedom and flexibility to manage a multi-vendor environment with ease. Now, how does Ansible achieve this? It boils down to the various networking modules it provides. Unlike traditional configuration management tools, Ansible operates using modules that are designed specifically for networking tasks. One of the essential aspects to remember is that Ansible's networking modules run on the control host, the machine where the Ansible command is issued, while the commands are executed on the target device. This dual-layer approach makes it adaptable to numerous environments. Here are some of the most prominent connection types that Ansible leverages to manage networking devices. Most similar to traditional SSH, this connection method is built for managing networking devices that support CLI commands. It establishes a persistent connection, making it easy to run multiple commands without repeatedly entering credentials. Netconf. This method uses XML over SSH, ideal for applying configurations in a structured format. Think of it as a more programmatic approach to configuration management. For devices that offer a RESTful API interface, this connection type is used, allowing for a different approach to managing configurations with HTTP requests. Local. Though deprecated, local connections can still be found in older scripts. This method generally requires specific vendor utilities. Newer networking devices that run on Linux can often be managed as if they were traditional servers, using SSH for command execution. Understanding these connection modes is crucial as it lays the foundation for building effective Ansible playbooks. In the provided Ansible playbook, we are focusing on configuring VLANs for Cisco switches, which is essential for managing network segmentation. The playbook begins with the declaration of the hosts, specifically the group designated as Cisco switches, indicating that the tasks within will be applied to all devices listed in this group. Notably, the gather facts false line indicates that the playbook will not collect system information about the switches before executing the tasks, which can speed up the process if such data is not needed. The core of the playbook features a single task, Create VLAN, which utilizes the Cisco.ios to iOS VLAN module designed explicitly for VLAN management on Cisco devices. This targeted module facilitates the creation of VLANs while alleviating the stress of potential command syntax errors typically encountered in manual configurations. Here, the VLAN is configured with an ID of 10 and is assigned the name Engineering. By applying this playbook, network administrators can efficiently and uniformly create VLANs across multiple switches, demonstrating the power and versatility of Ansible in network automation. In this Ansible playbook, we define a task aimed at ensuring the Ethernet 4 interface on an Arista switch is enabled. The playbook begins by specifying the target hosts, namely the Arista switches. The first task checks the current status of the Ethernet 4 interface using the arista.eos.eos command module, issuing the command show interfaces Ethernet 4. The results of this command are stored in a variable called interface status. After gathering the interface status, the playbook proceeds to the second task, which conditionally enables the Ethernet 4 interface if it is found to be administratively down. This is done by issuing the commands to enter the interface configuration mode and execute the no shutdown command. The conditional execution is based on the statement that checks if the phrase administratively down is present in the interface status.stdout. This method not only automates the interface management, but also enhances the resilience of the network by adapting to changes without necessitating manual intervention. This approach exemplifies the power of Ansible in maintaining network configurations efficiently and intelligently. When configuring connections for managing Cisco devices through Ansible, special considerations must be made, particularly when devices are located behind a bastion host. In this case, the configuration details are specified in the group vars/bastionrouters.yml file. The first line, Ansible connection, network CLI, indicates that the playbook will utilize the network command line interface, CLI, to interact with the devices. This is essential for managing network devices effectively. The next parameter, Ansible Network OS, cisco.ios.ios, specifies the network operating system of the devices being managed, ensuring that Ansible uses the appropriate modules and procedures specific to Cisco iOS environments. By stating Ansible become true, we grant Ansible the necessary permissions to escalate privileges if required, allowing it to execute commands that may need higher access levels. Lastly, the Ansible SSH common args parameter includes the crucial -o proxy command argument, which instructs Ansible on how to connect to the devices through the bastion host. This setup ensures a secure connection to the target devices without manual intervention, thereby streamlining the automation process and enhancing operational efficiency. As we reach the end of our exploration on how Ansible manages networking devices, it's essential to appreciate the global picture it creates. Automation using Ansible not only speeds up the deployment process, but also significantly reduces human error, which is incredibly crucial in network configuration. With Ansible, the power to manage diverse networking environments, regardless of vendor, is truly at your fingertips. So there you have it. We have unlocked the world of networking device management with Ansible, blending technical wizardry with practicality and humor along the way. Now, Go ahead and give it a shot in your environment. The future of network management is here, and it's automated. Now let's look at the figure. This table compares 3 Yang-based network automation tools: netconf, restconf, and GNMI. Each column highlights different aspects such as transport methods, encoding, commands, applications, and supported devices. Beginning with netconf, we see it uses RPC over SSH for transport and XML for encoding. The commands supported include get, getconfig, and editconfig, among others. Notably, netconf is recognized as the most mature protocol for network automation, allowing users to obtain both configuration and operational data, as well as make configuration changes. It's widely supported on devices like Cisco IOS XE and Juniper Junos. Next, the restconf section outlines its use of HTTPS for transport and XML JSON for encoding. Its commands encompass get, post, put, patch, and delete. Restconf is primarily utilized for accessing configuration and operational data through an API, particularly with platforms such as Cisco ISE and Cisco ACI. However, it has limitations in bulk network automation compared to netconf. Finally, we turn to GNMI, which employs gRPC over HTTP 2.0 for transport and utilizes the protobuf JSON encoding method. The commands include get, set, subscribe, and capabilities. GNMI comes with specific limitations regarding configuration changes, but it excels at providing real-time operational data. It's partially supported by devices like Cisco IOS and Arista EOS. This figure effectively summarizes the key distinctions and use cases of these automation tools, serving as a useful reference for understanding how each tool functions within network automation. Be sure to keep these differences in mind as we explore best practices and terminology in the follow-up video. Ansible is a very flexible automation tool and can be easily used to automate any aspect of your infrastructure. One of the significant areas where Ansible shines is in container management, specifically with Docker and Podman. In this video tutorial, we will dive deep into how to automate Docker and Podman using Ansible. Let's get started by first understanding what Ansible is and why it is so useful. Ansible is an open-source automation tool that simplifies IT tasks, including configuration management, application deployment, and orchestration. Its agentless architecture is one of its most appealing features, meaning you don't need to install any software on the nodes it manages. Instead, Ansible uses SSH or WinRM for communication, making it lightweight and easy to manage. Now, why is automating Docker and Podman with Ansible beneficial? As containerization has become a standard approach in modern application deployment, managing containers manually can lead to inconsistent environments and increased risk of human error. Ansible allows you to define your infrastructure as code and automate the deployment and management of applications in containers, providing consistency and reliability across different environments. Consider this scenario. You have several microservices running in Docker containers. If you need to update or scale these services, doing so manually can be tedious and error-prone. This is where Ansible comes in to save the day, enabling you to automate common tasks such as spinning up containers, deploying new versions of applications, and managing container networking. In this Ansible playbook, we define our automation tasks for managing Docker containers. The playbook starts with a declaration indicating that it will apply to the local host, meaning the tasks will execute on the machine where Ansible is run. Under the Tasks section, we identify a specific operation, starting a Docker container. The task is named Start a Container with a Command, which helps describe its purpose clearly. We utilize the community.docker.docker container module, which is designed for managing Docker containers through Ansible. Here, we provide 3 key parameters. The first is name, where we specify test container as the identifier for our container. Next, we designate the image as Alpine, a lightweight Linux distribution ideal for container environments. Finally, we outline the command the container will execute upon startup. Instead of running a default command, we instruct it to run the echo command followed by hello world. This setup effectively demonstrates how to initiate a simple container that performs a basic task while showcasing the integration between Ansible and Docker for automating container management. In this playbook, we aim to execute a task on the local host utilizing the community.docker.docker container module, which facilitates the management of Docker containers within Ansible. The playbook specifies that we want to name our container test container, deploy it using the Alpine Linux image, and run a simple echo command upon its creation. After drafting the playbook, the next step is to execute it using the command Ansible Playbook start dockercontainer.yaml. Once the playbook is initiated, the output provides a summary of the execution process. It indicates the gathered facts, such as the successful functioning of the local host. Following the container's creation, the task aimed at starting the container reflects a change, confirming that our command was executed correctly. The final recap of the execution details showcases the overall performance, highlighting that the playbook completed successfully, with all tasks either completed or changed as intended. To verify the running status of our newly created container, we can utilize the command docker container list-a. By executing this command, we can confirm that our test container appears in the list of active containers, affirming that it is up and running. To ensure that the echo command ran successfully, you can review the logs of your container. By entering the command docker logs test container, you can access the output generated by the container, which is essential for both debugging and validation purposes. If you are interested in using Podman as an alternative to Docker, the first step is to verify that it is installed on your machine. Running the command -podman will reveal the available command options if Podman is correctly installed. Checking for these options is important to confirm that your environment is ready for additional operations. Should you receive an error indicating that Podman cannot be found, this means the software has not been installed on your system. This is a crucial step in preparing your containerization tools for effective and secure application management. Familiarity with how to check logs and verify installations will facilitate the smooth operation of your containerized applications, whether you are utilizing Docker or considering alternatives like Podman. In this section, we create a playbook for Podman called Start Podman Container.yaml, which replicates the functionality of our earlier Docker playbook. The main goal of this playbook is to start a container that will execute a simple command, echoing the phrase "Hello World." The playbook begins with a declaration of the hosts, which in this case is set to localhost, indicating that the task will run locally on the machine. The tasks section includes a single task that utilizes the containers.podman.podman container module. Here we specify the name of the container as test container, and the image to be used is Alpine, a lightweight Linux distribution. The command to be executed inside the container is specified as a list, with echo being the command followed by the message we want it to print. To run the playbook, you simply execute the command Ansible Playbook start podman container.yaml in your terminal. Upon successful execution, similar to the Docker playbook, you should receive confirmation output indicating that the task has completed successfully, confirming that your Podman container is up and running. To check if the Podman container is active, you can use the command podman container list-a. This command will show you a complete list of all containers, indicating which ones are currently running and which have stopped. Running this command in your terminal gives you a comprehensive overview of your container's statuses. If you want to view the logs for a particular container, like test container, the command podman logs test container should be used. This command allows you to access and display the log output from that specific container, enabling you to keep track of its activities and troubleshoot any potential problems. When these commands are executed, you can expect to see results in your terminal. The output will include a list of your containers along with their current status and notable log messages, such as "Hello World" if that was part of the container's output. Overall, the approach remains consistent whether you are using Docker or Podman in conjunction with Ansible. The commands are user-friendly and offer a straightforward method for managing your containerized applications. Now, let's look at the figure illustrating the Docker API configuration. This interface is crucial for connecting to a running Docker instance, which facilitates effective container management. At the top, we see the title Docker Service, Docker API, indicating its primary function of managing Docker services. In the main section of the figure, there is an option labeled Enabled, which allows users to activate or deactivate the Docker connector instance. This option is presented as a toggle, allowing the user to select either true or false based on their requirement. This flexibility ensures that users can manage their Docker connections dynamically, depending on operational needs. Further down, the Docker host URL field is highlighted. This is where users input the address for their Docker instance, which could be either a TCP address like TCP/localhost 2376, or a Unix socket path such as Unix/var/run/docker.sock. This versatility in connection options ensures broad compatibility and ease of integration with various setups. On the left side of the figure, a menu navigation structure is visible. This includes various categories such as System, Services, and specific configurations for network, security, and packages. This organized layout allows for quick access to different management features within the Docker service environment, streamlining the overall user experience. The presence of action buttons like Apply and Reset at the bottom of the figure suggests that users can easily save changes or revert to previous settings, adding an extra layer of usability to the interface. Overall, this figure encapsulates the essential components required for managing Docker instances through the Docker API, illustrating the configuration options available to users. As you embark on automating your containerized applications, consider how orchestration tools like Kubernetes can also integrate smoothly with Ansible, allowing for further enhancements and automation of your infrastructure and application management workflows. Kubernetes has become a predominant orchestration tool in the industry, and Ansible has tailored modules specifically for managing Kubernetes resources. In conclusion, Ansible is a powerful ally when it comes to automating Docker and Podman. The combination of Ansible's declarative language and playbook structure allows you to maintain a clear and consistent state of your container environments. By applying these automation techniques, you can minimize downtime, reduce manual errors, and enhance your application's reliability in production. The ability to recreate environments on demand makes Ansible particularly impactful in CI/CD pipelines and rapid application development scenarios. So, if you haven't already, give Ansible a try in your containerized workflows. You might just fall in love with the efficient, automated world it opens up for you. Thank you for watching, and don't forget to subscribe for more exciting tutorials on DevOps tools and practices. Managing Kubernetes with Ansible is a pivotal task for those keen on automating their cloud-native applications and infrastructure. In this segment, we'll dive into how you can navigate and manage Kubernetes clusters efficiently using Ansible. This tutorial will take us through several key concepts, hands-on playbook examples, and tips to help you master this essential skill. So grab your favorite beverage, take a comfy seat, and let's get started. The command Ansible Galaxy Collection install kubernetes.core is essential for integrating Ansible with Kubernetes and is the first step towards utilizing the Kubernetes Ansible collection. This collection contains predefined modules, plugins, and roles specifically designed to manage Kubernetes resources efficiently. By running this command in your terminal, you're instructing Ansible to download and install the Kubernetes core collection from the Ansible Galaxy repository. This collection includes tools that allow you to interact with Kubernetes objects, automate the deployment of applications, and manage your cluster more effectively. Installing the collection is crucial, as it equips your Ansible environment with the necessary resources to execute tasks such as creating pods, managing services, and scaling deployments, thus streamlining the management of complex Kubernetes environments. Once the installation is complete, you can begin writing playbooks that leverage these capabilities, enabling you to achieve effective orchestration and automation within your Kubernetes cluster. To list all namespaces in your Kubernetes cluster, we create a playbook named KICS ns-show.yaml. The playbook connects to the cluster and utilizes the kubernetes.core.kits info module to gather information about existing namespaces. This information is registered for debugging purposes, allowing us to see detailed output about the namespaces present in the cluster. You can execute the playbook with the command Ansible playbook kits ns-show.yaml. Upon running, You will immediately receive output that includes valuable metadata about each namespace, enhancing your understanding of the cluster's current state. If you find that no namespaces are currently set up, the next step involves creating one using another playbook called K8s-ns.yaml. This playbook checks for the presence of a namespace named Mayans. If it does not already exist, the playbook will create it by calling the kubernetes.core.kas module and setting its desired state to present. To confirm the namespace's creation, you can run the command kubectl get-ns. Finally, after executing this playbook, verifying the output should show Mayans, confirming that the namespace has been successfully created. In this tutorial, we will focus on creating a service in the Kubernetes namespace mins. The provided Ansible playbook named K8s-svc.yaml is designed to ensure that the service mysvc is present in your cluster. The playbook begins by defining a task that specifies the desired state of the service as present and outlines its configuration under the definition key. The service is set up with the API version of v1 and the kind specified as service. Under the metadata, we define the service name as mysvc and associate it with the Mayans namespace. The specifications for the service are detailed in the specs section. Here, we create a selector that targets the pods labeled with app and service mysvc. The service will expose these pods over TCP, forwarding traffic from port 80 to target port 800. Before executing the playbook, it's essential to check for any pre-existing services in Mayans using the kubectl get svcn Mayans command. Once the playbook is executed with Ansible playbook K8s-svc.yaml, you can run the kubectl command again to confirm that mysvc is now listed among the services in your namespace. If successful, the service will effectively facilitate communication between your pods. In this tutorial, we focus on scaling Kubernetes deployments using Ansible. The playbook named K8scale.yaml leverages the kubernetes.core.k8scale module to adjust the number of replicas for a specified deployment. In this case, we target the deployment called myapp, located in the Mayans namespace, with the desired number of replicas set to 5. Before executing this playbook, it's crucial to ensure that the myapp deployment already exists within the Mayans namespace. You can verify the current deployments by running a kubectl getDeployments-n Mayans command, which provides an overview of the existing deployments in that namespace. After confirming the deployment is present, you can scale it by executing the playbook with the command Ansible playbook K8scale.yaml. This command will trigger the necessary changes to increase the number of replicas. Once the playbook execution is complete, you can again run kubectl getDeployments-n mins to check the status of your deployment and confirm that the myapp has successfully scaled to the specified count, enhancing your application's availability and resilience. The versatility of Ansible when managing Kubernetes does not stop at multiple object types and management tasks. You can automate entire workflows, handle secrets, manage config maps, and even deal with persistent volumes for stateful applications. The sky is truly the limit. Remember, Kubernetes is structured around the idea of declarative configuration. You declare the desired state, and Kubernetes works to maintain it. Ansible complements this beautifully by allowing you to manage your definitions, automate your deployments, and keep everything synchronized with your infrastructure as code practices. As we wrap up this tutorial, always keep in mind that rich documentation exists for both Ansible and Kubernetes modules. This resource is invaluable as you continue to expand your knowledge and capabilities. And who doesn't enjoy a good read while sipping coffee? Thank you for joining me in this deep dive into managing Kubernetes with Ansible. Happy automating, and remember, automation is not just a tool, it's a mindset. Diagnosing playbook execution problems is an essential skill for anyone looking to make the most of Ansible in their automation efforts. Ansible, while powerful and flexible, is not immune to hiccups during execution. There are cases where an Ansible execution might interrupt. Many things can cause these situations. In this audio-visual training, we're going to explore how to effectively diagnose these execution problems step by step. Let's start with one of the most common culprits, network issues. Now think of Ansible as that friend who always follows through on their plans, but sometimes forgets where they're going. If your commands are sent from one machine to another over a network, a hiccup in that network can cause a full stop to your automation efforts. Ansible playbooks rely on the network to connect and manage remote machines. Therefore, when there's a network drop, a DNS resolution issue, or even a misconfigured firewall, your Ansible playbook execution can stall and leave you scratching your head. So what can we do? In this section, we'll explore a powerful method for handling transient network issues during Ansible playbook execution. The code snippet demonstrates how to check the status of a service using Ansible's built-in shell command. Here, the command systemctl is active myService is employed to retrieve the current status of a specific service named myService. To ensure the task does not fail immediately, if the service is not in the active state, we make use of the register keyword to capture the output of the command into a variable called service status. By implementing the until keyword, we can set a condition for the task to keep retrying until the service status outputs active. If the service is not running, Ansible will automatically retry the command up to 5 times, thanks to the retries parameter. Between each attempt, a delay of 10 seconds is introduced with the delay parameter, allowing some time for the service to stabilize. This approach not only enhances the robustness of the playbook, but also ensures a smoother execution, preventing it from failing due to brief interruptions or delays. In this example, we have an Ansible task designed to execute a command that is guaranteed to fail. The task name, run a command that will always fail, succinctly describes its purpose. The command being executed is /bin false, a simple Unix command that does nothing and returns a non-zero exit code indicating failure. This situation raises an important challenge when using Ansible, as it interprets the non-zero exit code as an error by default. To handle this specific scenario, the directive ignore errors yes is included. By adding this directive, we instruct Ansible to disregard the failure of this command and proceed with the rest of the playbook without interruption. It's crucial to remember that while this can be a convenient workaround for non-critical failures, it's advisable to investigate and resolve the underlying issues in production scripts whenever possible. This practice ensures that the playbook remains reliable and effective in the long term, thereby minimizing potential disruptions in automated tasks. This playbook, named printfacts.yaml, is designed to gather and display all the facts about the target hosts managed by Ansible. The playbook starts with a header that specifies it will target all hosts in the inventory specified at runtime. Under the Tasks section, there is a single task defined with the name Display All Variables Facts Known for a Host. In this task, the module Ansible built-in debug is utilized to print information. The parameter var, host var as a hostname is crucial here. It instructs Ansible to access and reveal all variables and facts associated with the currently running host. Essentially, when this playbook is executed, it iterates through each host and outputs a comprehensive view of its specific details, such as CPU architecture, IP addresses, operating system, and installed packages. This detailed output can be invaluable in diagnosing configuration issues or discrepancies when troubleshooting playbook execution, as it provides clear visibility into the state of each target machine and helps to align it with Ansible's expected configurations. The provided Ansible playbook, named debug.yaml, is designed to execute a simple command on the local host and capture its output for debugging purposes. It begins with the declaration of the play, specifying the target hosts, which in this case is set to localhost. This means that the commands within the playbook will run on the local machine. Within the Tasks section, the first task uses the Ansible.builtin shell module to execute this use-bin uptime command. This command provides information about how long the system has been running, along with the current load averages. The output of this command is registered and stored in a variable named result. The second task utilizes the Ansible.builtin.debug module to print out the value of the result variable. This output not only shows the command's results, but also helps in identifying any potential error messages that could arise, thus facilitating effective debugging. By using this playbook, you can gain insights into the command's behavior and ensure everything is functioning correctly in your automated processes. In this section, we explore how to create a simple Ansible playbook that utilizes command line arguments to pass variables. To begin, a YAML file named printvar.yaml is created, which defines a playbook targeting the local host. Within this playbook, a task is included that employs Ansible's debug module to display the value of a variable called variable. This setup allows for easy examination of the variable's content during execution. Next, we focus on how to invoke the playbook from the command line. By using the Ansible playbook command followed by the playbook name, we can add -extra vars to directly pass a value to the variable. In this example, we assign it the string hello world. This technique not only simplifies testing and debugging, but also enhances code reusability, since the same playbook can be executed with different variable values as needed. Overall, this approach supports better validation of inputs and helps troubleshoot potential issues by ensuring that your variables are correctly set before execution. When running Ansible playbooks, it's essential to manage the number of hosts that are targeted, particularly during debugging sessions. The command presented here utilizes the -limit option to focus the playbook's execution on a specific host, thereby streamlining the process and mitigating potential distractions from other machines. In the given command, Ansible-playbook-inventory hello-world.yaml-limit equals host3.example.com, the -I inventory flag specifies the inventory file that contains the list of managed hosts. The hello-world.yaml denotes the playbook being executed. The -limit host3.example.com part restricts the execution to only the specified host, host3.example.com. This focused approach enables you to quickly test and debug your configurations in playbooks without the noise of multiple hosts executing simultaneously, which can lead to confusion or overwhelming outputs. By honing in on a single machine, you can identify issues more efficiently and ensure that your playbook behaves as expected before deploying it more broadly. Flushing the Ansible cache is an essential step when working with dynamic inventories or frequently changing configurations. The command presented here, Ansible-playbook-inventory hello-world.yaml flush cache, is designed to ensure that you're operating with the most current data available. When Ansible executes playbooks, it sometimes retains old variable values in its cache. This can lead to unexpected behaviors or results based on outdated configurations. By including the /flush cache flag in your command, you instruct Ansible to clear its existing cache before running the playbook. This action helps eliminate any residual information that might skew the desired outcome of your automation tasks. It's particularly useful in scenarios where inventory details or variable definitions may have changed since the last run. Using this command not only promotes a clean and accurate execution environment, but also minimizes potential errors. Therefore, when executing this specific command, you can be confident that the job will be executed with the latest, most relevant information at hand. To ensure your Ansible playbook is free of syntax errors before execution, you can utilize the built-in syntax checker feature. The command provided demonstrates how to do this effectively. By executing the command Ansible-playbook syntax-check.yaml syntax check, you instruct Ansible to analyze the specified playbook file syntax-check.yaml for any potential syntax issues. The jest syntax check option is particularly valuable as it helps catch any errors that might otherwise slip through unnoticed. Running this command will result in Ansible verifying the structure and syntax of your playbook, allowing it to identify any mistakes. If the playbook is correctly formatted, you won't see any errors. However, if there are issues, Ansible will provide clear feedback on what needs to be corrected. This proactive approach not only streamlines your workflow, but also saves you significant time once you proceed to execute the playbook. Embracing these tools not only builds your confidence in automation tasks, but also enhances the overall quality of your code, transforming potential frustrations into a rewarding development experience. One of the most complex aspects of the IT field isn't the creation of software or systems, but rather debugging them when problems arise. Ansible, as a powerful automation tool, is no exception to this reality. No matter how adept you become at writing Ansible playbooks, you will eventually encounter situations where a playbook behaves unexpectedly or fails altogether. This is where effective testing and debugging strategies come into play. In this tutorial, I'll walk you through the crucial aspects of testing and debugging Ansible playbooks, making the process engaging and perhaps even a bit amusing along the way. In this playbook, we are focusing on displaying all the variables and facts associated with a host in an Ansible inventory. The playbook begins with the specification of the target hosts using the line hosts all, which indicates that the task will be executed on all hosts listed in the inventory file. Moving into the tasks section, we define a single task named display all variables facts known for a host. This is accomplished using the ansible.builtin.debug module, which plays a crucial role in testing and troubleshooting your playbooks. The var hostvar's inventory hostname directive instructs Ansible to display the entire set of variables and facts related to the current host being processed. Using the debug module in this manner provides valuable insights into the host's configuration, helping you identify potential issues in your playbook or environment. By running this playbook, you can easily observe the state and configuration of each host, allowing for more informed debugging and optimization of your Ansible playbooks. In this playbook named debug.yaml, we target the local host to execute a series of tasks. The first task uses the ansible.builtin shell module to run the command /uabin uptime. This command provides essential information about the system, including the current uptime and load averages. By registering the output of this command with the variable result, we can store the command's execution details for further analysis. The second task utilizes the ansible.builtin.debug module to display the contents of the result variable. This step is crucial because it helps us visualize the output obtained from the previous command directly within the Ansible execution context. When you run the command with Ansible playbook debug.yaml, you'll see the results on the screen, giving you immediate insights into your system's performance. Testing your playbooks with this method ensures that you not only confirm their correct execution, but also gain a deeper understanding of how your code interacts with the system. This approach aids in writing resilient Ansible scripts, ensuring they are reliable before being applied in production environments. In this section, we demonstrate how to utilize Ansible's check mode, which acts like a rehearsal for your automation scripts. We begin by creating a playbook named checkmode.yaml. This playbook contains a single task designed to touch a file located at /tmp/myfile. By specifying the state as touch, we instruct Ansible to update the timestamp of the specified file without altering its content or creating a new file if it doesn't exist. To execute this playbook while ensuring no changes are made to the system, we utilize the -check flag in the command ansible-playbook checkmode.yaml check. This command allows you to see which tasks would be carried out without actually executing them. Therefore, it serves as a valuable preview tool, helping you understand potential impacts before applying any changes. However, it's important to note that not all modules support check mode. Particularly, the command and shell modules report changes unconditionally, since they can't accurately predict what changes they might introduce. In the given code snippet, we define a simple Ansible playbook that is designed to gather essential information about the target hosts. The playbook starts with declaring the hosts it will operate on, specifying all, which means it will run on every host in the inventory. This flexibility is crucial for administrators who need a holistic view of their environment. Next, we move to the task section, where a single task is defined. The task is labeled as Gather Facts About the Host, which succinctly describes its purpose. It employs the Ansible.builtin setup module, a built-in Ansible feature specifically designed to collect various facts or details from the host machine. These facts include vital system information, such as operating system type, network interfaces, and installed packages. Executing this playbook not only helps in diagnosing the root causes of failures in your Ansible deployment, but also provides a wealth of information that can assist in troubleshooting network issues or misconfigurations on the target machine. By understanding the host's environment, you can better address any challenges that may arise during playbook execution. When troubleshooting connection issues with Ansible, a useful command to execute is ssh-user@host.example.com-vvv. This command initiates an SSH session to the specified host, allowing you to verify connectivity and authentication. Here, user represents your username on the remote system, and host.example.com is the target machine's hostname or IP address. The inclusion of the -VVV flag is particularly important as it enables verbose output during the SSH connection process. This detailed output can provide crucial insights into what might be going wrong, such as incorrect credentials or network-related issues like firewalls blocking access. For instance, if you encounter messages like permission denied, it indicates possible authentication problems, requiring you to check your login credentials or SSH key configurations. Additionally, if the command fails with could not resolve hostname, this suggests an issue with hostname resolution, prompting a review of your inventory settings and the correctness of the hostname provided. By using this command effectively, you can systematically diagnose and resolve connectivity problems before delving back into your Ansible playbooks. When working with Ansible, it's crucial to ensure that your YAML files are free from syntax errors, as these can lead to unexpected behavior during execution. One effective way to check for such errors is by using the syntax check feature provided by Ansible. Specifically, you can run the command Ansible Playbook myplaybook.yaml-syntax check in your terminal. This command will analyze the specified playbook, in this case, myplaybook.yaml. As it processes the file, it will look for any syntactical issues that may exist, such as indentation errors, incorrect formatting, or misplaced keys. The output will highlight any detected errors, allowing you to identify and correct them before running your playbook. By checking for syntax errors ahead of time, you can save yourself a significant amount of troubleshooting time later on. This proactive approach ensures that your playbook executes smoothly, ultimately streamlining your automation tasks and enhancing your overall experience with Ansible. In the provided command, the Ansible Playbook utility is used to execute the specified playbook, which is myplaybook.yaml. When working with Ansible, playbooks are essential as they define the tasks to be performed on targeted hosts. In this scenario, an inventory file, indicated by -i inventory, is used to list the hosts that Ansible can manage. This inventory file contains the information about the machines on which the playbook's tasks will run. One crucial aspect of this command is the -limit parameter. By utilizing this option, the user can restrict the execution of the playbook to a specific host, in this case, host3.example.com. This targeted execution is particularly advantageous during debugging and testing phases. It allows developers and system administrators to isolate issues and verify changes without inadvertently impacting other systems within the same environment. As a result, this command demonstrates a practical approach to managing host execution in Ansible, ensuring that you can focus on specific machines when necessary. In summary, testing and debugging Ansible playbooks is a critical skill that requires a mix of strategies, from utilizing the debug module to print variable states, running playbooks in check mode, and gathering host facts, to verifying connections and managing syntax. These practices form the bedrock of successful automation with Ansible. So, next time you find your playbook behaving unexpectedly, don't panic. Remember these tools and techniques, and you'll have your playbook up and running in no time. Debugging may not be the most glamorous part of deployment, but with practice and the right mindset, you can turn those pesky errors into stepping stones toward mastery of Ansible. Thank you for watching, and happy automating. AWX and Ansible Automation Controller are powerful tools that can elevate the experience of using Ansible in enterprise or team-based environments. Today, we will embark on a journey to demystify these tools and get started with the Ansible Automation Controller. So whether you are new to Ansible or looking to streamline your operations, this tutorial is for you. Buckle up, because it's going to be an exciting ride filled with automation, organization, and maybe a joke or two along the way. Before we dive into the technical aspects, let's lay down some foundational knowledge. Ansible is a powerful automation tool, but it often requires the user to interact with a command line interface, which can be challenging for team members who aren't as tech-savvy. Enter AWX and Ansible Automation Controller. These complementary tools not only simplify the process of managing Ansible, but also provide a robust web-based user interface that allows users to manage and delegate tasks efficiently without needing deep technical skills. Pretty cool, right? AWX serves as the upstream and open source version, while Ansible Automation Controller is the official Red Hat supported version. Understanding this contrast establishes why enterprises often lean towards Ansible Automation Controller. It comes with business support that is necessary for managing sensitive automations across larger organizations. To kick off the installation process, we first need to start our Minikube cluster. This is done using the command minikube start CPU equal 4, memory equals 6G, add-ons ingress. Here, we allocate 4 CPU cores and 6 GB of memory to ensure our cluster has enough resources to run efficiently, much like how proper tools are essential when assembling intricate furniture. The inclusion of the -addons ingress flag enables the ingress controller, which allows us to manage access to services running in the cluster, similar to how a door lets you enter a room. Once our Minikube cluster is up and running, we need to configure the kubectl command, which is essential for interacting with Kubernetes. This is achieved by creating an alias with alias kubectl equals minikube kubectl-. This command simplifies our workflow, ensuring that every time we use kubectl, it knows to direct those commands to our Minikube instance, rather than to any other Kubernetes setup. This step is crucial, as it underscores our commitment to efficiently managing the resources that we are about to deploy, specifically the AWX setup. To begin deploying the AWX operator, we need to create a file named customization.yaml. This configuration file plays a crucial role in defining our application's deployment, specifically indicating the resources and images needed for the AWX operator installation. The first part of the file sets the API version and specifies that we are using customize, along with the kind of resource we're defining. Under the Resources section, we include the AWX operator's configuration from a GitHub repository, pointing to a specific version, 2.3.0. This ensures that we are deploying a tested and stable version of the AWX operator. Additionally, we specify the image that will be used for the AWX operator, including its repository and the corresponding tag that denotes the version. Here, we are setting the image to quay.io/Ansible AWX-operator with the tag of 2.30, indicating the exact version to pull. Once we've filled out the customization.yaml file, we apply the configuration using the command kubectl apply k. This command tells Kubernetes to process the resources defined in our customization file and deploy the AWX operator accordingly. As a result, you should see the AWX operator pods starting up, bringing your application to life. Once you've got the AWX operator running, we now shift our focus to creating an AWX instance. To accomplish this, you start by creating a file named awx.yaml, which defines the necessary specifications for your AWX deployment. The API version and kind fields specify that this is an AWX resource, while the metadata section names your instance. In the spec, we define the service type as node port, allowing access to the service via a port on the node. After defining the AWX instance, the next step is to update the customization.yaml file. This file is essential as it allows Kubernetes to manage configurations by including your new awx.yaml file within its resources, ensuring that all components can be deployed together seamlessly. Once your configurations are updated, you apply them to your Kubernetes cluster using the command kubectl apply k. This applies the entire set of Kubernetes resources defined in your customization.yaml. Finally, to access the AWX service, you can run a command that provides the service's URL, enabling you to connect via your web browser. As the login page appears, it's a rewarding moment, showcasing the successful automation of your deployment. Now, let's look at this figure that represents the procedure for creating a new project in AWX. The interface is divided into various sections, where the most prominent field at the top is the name. Here, you should enter Sample Project, which will be the identifier for your project. Below that, there's a designated area for Organization, where you can select a predefined option or specify one that applies to your setup. Next, focus on the Source Control Type drop-down menu. This figure illustrates that you should select Git, as this is the version control system we will be using. Below that, you'll find the Source Control URL field. This should be filled with the URL provided, https:/github.com/ansible/tower samples. This link points to the repository where your playbooks are stored. Further down, the figure highlights several additional options. While they may be less crucial for creating a basic project, you should ensure that the checkbox for Update Revision on Launch is marked. This feature is crucial as it guarantees that whenever you execute the playbook, it pulls the latest updates, much like keeping your software up to date. Although not shown in the figure, remember to review other fields such as source control branch, tag, commit, and source control credential, which may be required depending on your access permissions. This comprehensive overview of the figure allows us to smoothly transition into configuring our AWX project with all necessary details. In this section, we define the inventory configuration for Ansible to interact with the specified host. The YAML structure begins with a common indicator, nye, which denotes the start of a new document in YAML format. The first configuration item, Ansible connection, is set to local, which tells Ansible to execute tasks on the local host directly, rather than connecting over SSH or another protocol. This is particularly useful for running playbooks that apply to the local machine itself. The second line specifies Ansible Python interpreter, which is crucial for ensuring compatibility with the Python environment. The variable Ansible Playbooks Python is a dynamic placeholder that automatically resolves to the path of the Python interpreter used by Ansible at runtime. By using this variable, you ensure that the correct Python version is used, allowing for smoother execution of playbooks that may depend on specific Python features or libraries. Together, these configuration settings enable Ansible to function effectively and efficiently with the local host, paving the way for seamless automation and configuration management. Now let's create a job template. Job templates are like the blueprint or the recipe for running your playbooks. In AWX, navigate to the Templates section and click Add. Choose Job Template and fill in the required fields. Name, Hello World, Inventory, select your sample inventory, Project, select your sample project. Playbook, choose the Hello World.yml playbook available in your project. Once you have everything filled out, hit Save. If you were excited for this moment, you should now be doing a little happy dance, because it's about to get even better. Now, we are ready for the grand finale, running a job. Navigate back to the Templates section, find the job template you just created, and click on the little rocket icon. This signifies liftoff. You will begin to see the real-time output of your job running. It's exhilarating, like watching a suspenseful cliffhanger unfold live. Once the job finishes, AWX retains the execution output in the backend. You can come back later to audit what happened during the run. This feature comes with both thrills and chills as it enhances the transparency of your automations. Imagine having logs for auditing that abolishes the need for post-it notes or frantic email chains. Oh, the joy. Now that your playbook is running, it's equally essential to control access to AWX. This brings us to the concept of role-based access control, RBAC. By managing user accounts and teams in AWX, you ensure that only the right people can perform sensitive actions. To create a new user, navigate to the Users section and click Add. Fill in the details for the new user. You can create users with different roles, such as normal users without permissions, system auditors with read-only access, or system admins who can do it all. Imagine the possibilities this brings. No more accidental mishaps. It's like having a safety net for your automation. Now let's look at this figure, which illustrates the Create New Project interface for Ansible automation. At the top, you see fields labeled Name, Description, and Organization. The Name field is where you will specify the name of your new project, while the Description field provides an opportunity to add additional context or details about what this project entails. The Organization section allows you to select the relevant organization for your project, defaulting to the default option in this case. Moving down, we see the Source Control Type field, which prompts you to choose a source control option. This is important as it integrates your project with version control systems, enhancing collaboration and project management efficiency. Below that, the Execution Environment field is present, which will be essential for configuring how your project runs in different environments. Lastly, the Content Signature Validation Credential field appears. ensuring that the content used in your project meets specific validation requirements. This adds a layer of security and integrity to your automation processes. This figure encapsulates the initial steps to set up a project, enabling you to efficiently manage automation tasks while delegating user permissions through team configurations. Finally, let's discuss organizations. If you've ever faced situations where different teams in your company need to operate independently, the concept of an organization in A2X is your friend. When you create an organization, you are essentially setting up a separate space within A2X with its own user accounts, teams, projects, inventories, and job templates. To create an organization, go to the Organizations section, click Add, provide a name, and voila! You have created an organizational unit within AWX that ensures structured operation. It's sort of like giving every department in your company their own office space, but with less coffee spillage. Now, let's look at this figure, which illustrates the interface for creating a new inventory in Ansible Automation Controller. At the top, you'll see the title, Create New Inventory, which indicates that this is the section where you configure your inventory settings. In the left portion of the figure, you can input the name of your inventory, which is currently labeled as Sample Inventory. Below this, there's a section for entering a description, allowing you to provide more context about the inventory's purpose. Next to this, you will find an Organization drop-down, which is set to default, showing that inventories can be organized by specific groups. Moving on, there's a field for labels, providing options to tag the inventory for easier management and filtering. This can enhance the organization and retrieval of your inventory within larger frameworks. The Options section includes a checkbox labeled Prevent Instance Group Fallback. This feature allows you to specify whether the inventory should prevent fallback to default instance groups, adding a layer of control over instance management. Finally, in the Variables area, a space is provided for defining specific variables associated with this inventory. This allows for further customization and flexibility in automation tasks, ensuring that parameters can be tailored to different scenarios as needed. This figure effectively summarizes the essential elements needed to create and manage your inventory in Ansible Automation Controller, highlighting the intuitive approach towards setting up automation environments.